Hey guys, my name is Lakshay and I'm a research analyst at Scalar Academy and welcome to another video of ours. Now in this video, we will be talking about stacks, queues and linked list. Now let's start. Now before we begin the session, make sure you subscribe to our channel and hit that bell icon for further notifications and you never miss any updates from us. Now let's see what you guys are going to learn today. So first of all, we will be explaining about the introduction in stacks, queues and linked list. Then we will be talking about stacks and queues in data structures and how they're implemented. Apart from this, we'll be also be talking about problems on stacks and queues. Now with this, we will be talking about queues and dequeues with some applications of queues in trees as well. Now moving on to the linked list, I will be talking about linked list and its code with the addition of new node and using recursion as well. Now after this, we will also cover reversing a linked list and palindrome in linked list as well. So now let's start with our first topic.
Let's talk about a very important topic called stacks and queues. Stacks and queues is one of the most important topic when it comes to computers programming. Recursion, for example, is based on stacks. Understanding stacks enables you to better understand how recursion works internally, and hence you can use it to optimize space of your program as well. It's extremely important for interviews. You can expect direct questions on stacks or queues. For example, if you want to find the maximum area under a histogram, you can do it using stack. The parentheses problem as well can be solved using stack. The sliding window problem can be solved using a queue. So these are important from an interview perspective. But having said that, it's also important for day-to-day activities as well. Why? You might have heard about Kafka or Redis queues. These are nothing but the data structure queue, right? At a massive distributed scale. So these are not just important in terms of an interview, these are also important in day-to-day activities as well. Hence, do not skip these topics.
Okay, so today we are going to cover stacks. So let me give you first a little introduction about stack. So first of all, the stack is very much important. It's the most favorite topic of the interviewers. Be well versed with this topic. Like first go through the basics, understand it because they are very straightforward, and then attempt as many questions as you can. There are some, standard problems that you should definitely attempt. That was the gist about stacks. Now let's get started. Cool. So stack is very much similar to the stack of objects you see around yourself. So be it stack of plates, stack of books, so stack of plates, stack of books, then stack of, let's say, bowls. So you see it and use it every day, right? So let me draw the stack of plates. So this is how a stack of plates look like. Now from this stack of plate, you can insert a plate only from this end, that is top, right? You can only insert a plate on top and you can only remove a plate from top. You cannot insert or remove a plate from in between because that will disturb all the plates, right? So you cannot do that. You can only remove and insert a plate only from top. So that's essentially the idea behind stack, that we can only insert an item from top and we can only remove an item from top. Okay, so conceptually or logically, you can think of a stack like this, where one end is open and three ends are closed. So from only this end, we are going to perform operations, that is to remove an item and to insert an item. As I was saying that we can only insert an element from one end and remove an element from that end only, and therefore stack is known as LIFO data structure. That is the last, as you can see the stack of plates over here. So this plate which was inserted at the very end will be the first one to come out. That is last in, first out. Okay, cool. So first what we are going to do, we are going to understand stack as an abstract data structure, that is ADT, abstract data structure, What do we mean by abstract data structure? In which the implementation details are hidden, but the operations are given to us. Okay, so let me write it over here, that implementation hidden. Okay, it's not there, it's not given, but only the operations are there. Only the operations are there with which, using which we can use the stack. Okay, so for example, you can see the fan on top of you, right? So you don't know how it's working internally. All you care about its operation, as in you put down the switch and it turns on, and you put off the switch and it turns off. That's what you care about. So that's an abstract. Cool. So we are given, let us understand the basic operations that are available with stack. Okay, so there are 4 basic operations. The first one, I am sure you guys, if you know about stack, you must know about all these operations. So that is push function, and then second is pop, the third is top, and the fourth is empty. Okay, so the push operation actually helps us to push an element on the top of stack. So this pushes an element on top of stack. Then here we have pop. So pop removes an element from top of stack. Then we have top, so it returns the element present on top of stack. So whatever element is present on top of stack, it just simply returns it. Okay, so don't worry, we are going to see an example over here. Is empty is the function that tells us if the stack is empty. So if the stack is empty, it returns true, else it returns false. Okay, so these are the 4 operations, that is push, pop, top, and is empty. Push pushes an element on top of stack, pop removes an element from top of stack, top tells what is on top of stack, and is empty returns true if stack is empty, else it returns false. Remember that pop simply removes an element and top does not remove an element. It simply tells what is present on top of stack. Is it clear now? Okay, so basically, while performing a question, you will have to use in C++, let's say you can use STL, right? In STL you have stack. So in C++, you declare a stack like this. You can use a stack like this, and on this object, basically, you can call all these functions. So push x, then s.pop, and so on. Likewise, in Java, you have collections using which you can use stack. So while attempting a question, you don't have to implement a stack of your own until and unless told. Okay, so but in a while we are also going to see how to implement a stack. We are going to actually implement these operations. Okay, cool. Okay, so let's actually see a dry run of these functions. So here this is a stack, and these are the operations that I would want to perform: push 2, push 1, push -1, push 5, then pop, pop is empty, top. So let's perform these functions. Okay, so it's push 2. So what we'll do, from where we'll put it? We'll put it from here. So basically 2 will come over here. Then it's push 1. So 1 will come over here. Then -1, -1 will come over here. Then there is 5, 5 will come over here. Then we are popping. So 5 will be gone, right? 5 will be gone. So we have removed 5. Now again pop is there. So -1 will be gone. So we have removed -1. Okay. Then we are checking, is the stack empty? What will it return? What will this return? It will return false, because the stack is not empty, right? The stack is not empty. Okay, so now there is top. So what will be the top function return? It will return whatever is present on top of stack. So basically top is pointing over here. So whatever is on top of stack, it will return that. So it will return 1, right? It will return 1. So that was a simple dry run of how can we use these operations. Okay, how these operations work. Now let us come to the applications of stack, which are very important. Applications of stack. So some of the applications are undo redo. Then we have arithmetic, arithmetic expression, evaluation, right? Then we have recursion. So these are some of the, then we have string reversal and so on. So these are some of the applications of stack which are very important and you must know. So try to figure out that how a stack can be used in these operations. You know, that's an activity for you, that do try to search that how we can perform an undo redo. So this is actually present in your browser, right? So whenever you go to any page, from any page and want to come back, so basically you store, for example, let me give you an example. So you are at link, let's say 1, then you go to link 2, then you go to link 3 and you want to come back to link 2. So what you can do, you can actually maintain a stack of them. So like first you are on link 1, you can put it on a stack, link 1. Then you are going to link 2. So put it on top of stack. Then you are going to link 3. Then put it on top of stack. Now you want to come back to link 2. So what you can do, you can simply remove this. And now you are back to link 2. Does that make sense? So likewise, you can also have a redo stack. Okay, so that's an activity for you, that how you can perform a redo operation. Okay, so likewise try to figure out. And we have arithmetic expression evaluation. So I think you all must be very much familiar with this. That is, you know, converting to infix to prefix or postfix, then evaluating the postfix notation. So that's where you can use stacks. Okay, and then you have recursion. Stack is a core of recursion. So you make function calls, and when you come back, so that basically those function calls get stored on top of stack. Okay, likewise string reversal. Okay, so there is another application that you may be using in your daily life. You must have seen this InShots app, right? So what happens in this, you are on this screen, okay, and so here I am actually at my feed. I am at my feed, okay, and I am watching this news. So I can only see another news if I remove it, if I remove this. So can you see that how this is an implementation of stack, right guys? Now let's talk about the implementation of stack. So could you guys tell me how can we implement a stack? So using arrays, second is using linked list. Okay, so how can we implement a stack using arrays? So basically, let's see. So we can have an array. So size of the array is, so array is A, and size of the array is 7. Okay, so what we can do, so let's say I want to push 2, push 3, push -1, pop, push 7, pop. Let's see how can we implement these operations using stack. Okay, so what we can do, basically we can actually enforce that one end of the stack will be there to perform all the operation. So you can imagine it like we are pushing the elements from here and removing the elements from here. So let's say I want to push 2, so 2 comes over here. Now you can also maintain a top variable which is right now pointing over here. That means what is on top of stack? 2 is on top of stack. Then we have push 3. So what we can do? We can simply increment this top variable and push 3 in here. Then push -1. So we can simply increment this top variable and push -1. Now how to pop it? How can we pop it? Top minus minus. So basically we are now at index 1 and we have, so basically -1 is gone. Okay. then we are at, so this was done, then we are at 7. So again we can increment the value of top and 7 comes over here. Now again pop's coming, so we can come over here and this is gone. So basically that's how we can operate a stack using arrays. Okay, and now can someone tell me the problem of stacks? So problems of stack are, which are very important if let's say an interviewer asks you to implement a stack using arrays or linked list. So if I talk about arrays, then we have problems, overflow and underflow. Let's say I want to push 1, 4, 0, 5, 6. These are the items that I would want to push. So 1 comes over here, then 4 comes over here, then 0 comes, then 5 comes, then 6 comes, and now I would also want to insert, let's say, -1. So as you can see, as I move my pointer forward, there is no space because array has a fixed space, right? So I cannot insert any more element, and that leads to the condition of overflow. Okay, and it's very important. So if interviewer has asked you, he's basically maybe judging you that will you cover these cases or not. Okay, so this is the thing. So how can you handle it? So basically here you have mentioned a size, right? You can keep a check that if size, so if top is equal to the size -1, so in that case that's an overflow. You cannot insert any more elements. So that's a drawback of arrays, and to overcome that, basically you can use something known as dynamic arrays. Okay, you can use something known as dynamic arrays. Okay, now let's say I want to pop, I am calling pop 7 times. Okay, so basically this is gone, third time, fourth time, fifth time, sixth time and seventh time, and now I am again calling. So now what will happen? Will I be able to pop any more element? No, I will not be able to pop any more element because the stack is empty. So if I attempt to do so, that will lead to underflow condition. So how can you make it all right? Basically, you can put a check that if top, so if top is equal to, let's say, -1, then print underflow. Okay, and simply return. So that's how you can manage underflow and overflow condition. Does that make sense, guys? Underflow is when you are trying to pop an element when there doesn't exist. When you are popping an element when there is no element. So how will you be able to pop? Will you be able to pop? No, right? So that's the case of underflow. So you can manage the case of underflow by checking that if top is equal to -1, that means you have no element, so you simply print underflow and return. Cool. So let's talk about linked list. So in linked list, what you can do is, so you have nodes in linked list where this is the data part and this is the address part. So basically the nodes of the linked list can be present anywhere in the memory, right? Like array, you don't have everything in a contiguous manner. Everything is scattered. Every node is scattered in linked list. Basically, if you have this as a memory, so if let's say one node is present over here, another node can be present over here. Okay, third node can be present over here. So basically, this address field actually links node. So basically, this will be linked to, let's say, this, then this is getting linked to this, and so on. That's how we store data in linked list. So basically, let's say you have 2 and 1 right now. Then you want to insert, you want to push, let's say, 7. So how you can do? Right now, top is here. So at what position, if you, so you are actually, remember, you are actually implementing stack using linked list. Where would you want to insert this node? This is your linked list. This is what you are building. This is the temp node, current node, new node that you want to insert into your linked list. So where will you insert it? That we can actually put it on top of head. So now we can actually make this its next pointer point over here. So this is how our stack would look like. Now top will be over here. Okay? So you can, in case of a linked list, you can imagine a stack like this. Like this, it's growing, right? Like this is it's growing. And when you want to pop an element, so basically you can actually shift this top to the next position, and this will be, so basically you can free up this space. Okay. So that's how you can implement a stack using linked list. Now with linked list, the concept of space, a lot of space is used in linked list. Okay, so basically you are storing pointers as well, that will take a lot of space. And pros of both stack and cons is that you will be able to perform push and pop operation in just order of one time complexity. Okay, in just order of one time complexity. Okay, cool. Let's get to the question. Okay, so the first question that we have is of very much famous question and very much asked question. It's of valid parenthesis. Okay, valid parenthesis. So the question says that you are given brackets, the round brackets, okay, and you have to tell whether the parentheses are balanced or not. Let's say you are building this compiler in which you will be writing your code, right? So basically you will be you want your compiler to check, verify your code. So in that case you will definitely want how can we check if the bracket are valid or not. So how can we do that? Let's see. First of all, let me give you some examples. Let me write down the examples. Okay, so what do you say about the very first parenthesis? What do you say about the very first parenthesis? Are these set balanced? Is it balanced? Yes, it is balanced because a corresponding opening bracket has a corresponding closing bracket. So yes, it's balanced. Then if I talk about this, is it balanced? No, it's not, because this is complete. They are balanced, but here this opening parenthesis is lacking a closing parenthesis, or you can also say that this parenthesis is lacking a closing parenthesis. So this is not balanced. This is not balanced. Likewise for this, so this is lacking an opening bracket, or you can also say that this is lacking an opening bracket. So this is also not balanced. Okay, so you have to basically tell, are the parentheses balanced or not? Let's say we want to attempt this question without stack. Can anyone think of something? Okay, so let me first actually put some observations. Let's do the question step by step. Okay, let's do the question step by step. So observations are, the first observation is that, can an opening bracket make a string invalid? As in, let's say I'm traversing the string and I find an opening bracket. So can that opening bracket make the string invalid? Well, it depends upon the future. It depends upon the future, that if I have this opening bracket, maybe in future I'll find a closing bracket and that will be valid. Or let's say I don't find a corresponding closing bracket, in that case it will be invalid. So it totally depends. It totally depends if I get an opening bracket. Okay. Now if I talk about a closing bracket, so what about a closing bracket? Can a closing bracket be a problem to us if we encounter it? Well, so if till now for a closing bracket there was no opening bracket, in that case, yes, it is a problem, because even if we move any further, the string that is given to us will not be valid in any case, right? In any case. So basically, let's actually okay, let's take look at it like this. So I have something like this. So what will happen? Let it be like this. So I am at here. I will maintain, what I can do, I can maintain a left and right count, which can be initialized to 0. Now I am at an opening bracket. So that means left actually tells a opening bracket and right tells the count of a closing bracket. So I found an opening bracket. This becomes 1. And so let this be the thing. Let this be the bracket. Now I am here. Now I am here. So what I can do? I can simply decrement the value of this and that will tell us that we actually found a match for an opening bracket. We actually found a match for an opening bracket, so we can actually set this to 0. Right, now let's say I have a string like this. What will happen? What will happen? That I am here left and right. So basically I have left 1, then I have a closing bracket. So initially both are 0. So now this is a closing bracket. So is left greater than 0? Yes, it is. That means there is an opening bracket. So we can simply decrement it, telling that we have found a match. Now next we go to the next character. This is a closing bracket. Okay. So what's the value of left? It's 0. That means there's no opening bracket. In that case, we will simply return that it's invalid, because at this point there is no use to move any forward, because this closing bracket does not have a matching opening bracket. So we can simply return from here. Does that make sense to everyone? Okay, so whosoever is saying that can we count the number of opening bracket and the closing bracket? Guys, we cannot simply count the number of closing bracket or opening bracket. Okay, let's take an example of that. Let's say I have this as a string. So now left is equal to 2, right is equal to 2. But are they valid? Are they valid? No, they are not valid, because they are not placed in the correct order. Therefore, this is not a right approach. Is that cool? The time complexity of the approach is what? What's the time complexity of the approach? So if we have this case, here the number of opening brackets, closing brackets are 2, number of opening brackets are 2. So are they valid? No, they are not valid. So this is wrong. This way is wrong. So what's the time complexity, guys? Time complexity is just order of length of the string, because we are iterating the string just once. And what's the space complexity? Just order of 1. We have not used any space. Okay, we have not used any space. Now let me make a question little trickier. Now let's say I have brackets these and these. So this is an extension of the question. Extension hai ye question ka. Now I'm saying that I have these 3 sets of parentheses. Now I have to tell, basically my string can contain these set. So I have to tell if those are valid or not. Let's take an example. Examples can be this, then we have this. So this will be given to you. Now you have to tell, are they valid or not? Now can you, how can you do it? How can you do it? So whenever in the interview you're telling the interviewer that okay, we can use stack for this, but she or he already knows, right? You have to get to it. Like how? What's the intuition? So that's is very important. Okay. Some of you are saying that we can use 3 variables. So that will be wrong, because then you won't be able to actually find the order. You cannot judge the order by taking that many variables. So first of all, I am sure that you guys understand that it cannot happen by taking just the left count and the right count, because if okay, so first of all, let's take the example of this. Now here left is 1, okay, and now I find a closing bracket, but here they are not same, right? So this will not work. Having left and right is a bad idea. Now taking 3 variables. So here I have this string. So if I take 3 variables, let's say round, or let me write first bracket, second bracket, third bracket. Now here the first type. So this is type 1, type 2, type 3. First bracket ka left, right, iska left, right, then iska left, right. First ka left is 1, okay. Third ka left is 1, okay. First ka right. So we have found a right bracket and this manages to be 0. Then we have third ka right. So this becomes 0. But is this valid? No, it's not valid, because the order is different. Order doesn't match. So therefore, that's a bad choice. Does that make sense? you should have a clear idea that why your approach is wrong. You should take as many, is like, if you are stuck, you are not able to think, take examples and try to generalize it. You guys are clear with it? Cool. So let's move forward. Now let's actually build some intuition of this. So one thing is that, let's consider these bracket. One thing is that so this is invalid, right? This is invalid. This is also invalid, right? This is also invalid. This is valid. This is valid. They have right set of pairs. Now this is also, this is what? This is what? This is also valid. Okay. This is also, as you can see, that this is also valid. So if I talk about this string, then it's a property of the valid parenthesis that if the complete parentheses are balanced, then their sub parenthesis will also be balanced. As you can see that this is balanced, this is also balanced, this is also balanced. So we are not considering all the substrings, right? We cannot consider anything like this or something. We have to choose the right set. But what it means is that whatever the parentheses are inside it, they will be balanced anyhow. So this is its corresponding pair. Then we have this, it's correct, then it's correct, then this is there. So does that make sense? That inside of it parentheses are balanced? Now, so an opening bracket does not bother us, right? An opening bracket does not bother us because in future we may find a closing bracket for it, right? But let's suppose I am at this closing bracket. Let's suppose I am done with everything and I am at this closing bracket. Now for this closing bracket, this is an opening bracket, this is an opening bracket. Does these brackets are of any use to me? No, they are not. Can I get rid of them? Then that would be great, right? So if I can get rid of them, because they are valid in itself, right? As I told you by this property. So since they are valid, if I can get rid of them, then I can actually find out if this bracket has a matching opening bracket. Okay. So let's actually see a dry run of this using stack, because stack is the data structure that helps us find. Just look at just the past. Okay, just the past. So how and what we can do? We are at this bracket. This is an opening bracket. We'll see about it in future. So push it onto the stack. Then this is an opening bracket. We'll see about it in future. Put it on top of stack. Again an opening bracket. Put it on top of stack. This is a closing bracket. Was there an opening bracket for this? Yes. Where can I see? I can see it on top of stack. If there is a corresponding match for this closing bracket, then I can simply pop it off. Next time here. This is a closing bracket. Does this have a match? And see how nicely we have removed between whatever was presented. That is here. We have removed it. We have removed it. And now we are actually comparing this. Where can we find it? On top of stack. So yes, it has a match. Remove it. So now we are here. Now we are here. Put it. So this is our closing bracket. Yes, match found. So remove it. Remove it from top of stack. Then we have an opening bracket. Push it on top of stack. Okay. Then we have a closing bracket. Is the corresponding opening bracket present? Yes, it is present. Remove it from top of stack. Now we are at the last bracket. Is the corresponding opening bracket present? See here how we have gotten rid of all of this, right? So basically, yes, it's present. From where we can find? On top of stack. Just remove it. What's the condition we have to check for validity? That if the stack is empty, then return true, right? If the stack is empty, return true. But if the stack is not empty, so we have to return false. That tells, even after iterating the string, let's say we have completely iterated the string, even if the stack is not empty, so we will have to return false, right? Because there are still left some unmatched opening brackets. So at any time, let's say you have something like this. So at any time you don't find, so okay, let's do a dry run of this as well. So this is an opening bracket, move ahead, opening bracket, move ahead, closing bracket, but no corresponding match. Simply return from here. Simply return from here. Okay, so now let's move on to the next question. But before that, let's talk about the time complexity. The time complexity of this approach is just order of n, because we are going to each and every bracket not more than twice. How? Once while pushing it and another time while popping it. So that's only 2 into n, which makes it order of n, right? That makes it order of n. And the space complexity is order of n, because in the worst case we may end up pushing all the brackets in the stack when, let's say, the string was something like this. In that case you will end up pushing all the brackets in the stack. So the space complexity is order of n. Okay, so I hope that's clear, and we'll quickly move on to our next question. So intuition is that how can we, previously clear up something to get just the, so here as I talked about that step by step we made the intuition, like, sorry, I just removed it. So as I was talking about that, inside of it will also be, balance. So if we can remove it, I will just be able to look at here. That's what I want to do. So we can simply remove it, and that is possible using stack. Okay, so let's move forward quickly. Cool. So question 2, and this is very, very famous question, which is of next greater element. Okay, so question is that, let's suppose you are given an element, you are given the elements in an array. Let's suppose 10, 13, 22, 7. For each of these elements, you have to tell that what is the next greater element to its right, just the next greater element to its right. So what's the next greater element to the right of 10? It's 13. Okay, it's 13. The next greater element for 13, it's 22. The next, is there any next greater element for 22? No, it's not. So we can put -1 over here. We can put -1 over here. Then we have 7. So next greater of 7 to right of it, it's -1. Nothing is there. Nothing is there. Okay, so let me take, this was example 1. Let me take another example as well. So we have 10, 7, 4, 2, 9, 10, 11, 3, 2. Okay, so what's the next right to the right of 10? It's 11, right? Just greater element on the right of 10. It's 11. Just greater element on the right of 7. It's 9. It's 9. Just greater element to the right of 4. 9 again. To the right of 2. 9. Just to the right of 9. It's 10. Just to the right of 10. 11. Just to the right of 11. Nothing. To the right of 3. Nothing. To the right of 2. Nothing. Okay? Okay, cool. See, if you are implementing any question, you can use STL in C++ or collections in Java. You don't have to implement push pop functions on your own. That's just for the sake of, if let's say your interviewer asks you. That's it. Okay, that's it. Cool. So if the question is clear, please tell me that how can we attempt it. At least give me the brute force approach. At least give me the brute force approach. So you will agree with me that brute force is nothing. So brute force is using 2 loops. So you can basically, let me actually write the code for it as well. So the brute force look like that. You can have an answer variable, answer array. Then you can iterate through all the elements from 0 to n-1. Then for those elements, you can again iterate from. So, okay, first you can initialize your result to -1 if let's say you don't find any element. So you can do for j that goes from I plus 1 to n-1. You can check if a of I is, so a of I is less than a of j, then simply put answer I is equal to aj, okay, and break from here. Take a break from here, because you just have to find just the larger element. You don't have to iterate any further. Okay, now what do you have to do? Actually, this should be result, and out of this for loop, you can set answer I is equal to result. Does that make sense? This is just the brute force approach. Okay, cool. Let's go ahead. So the time complexity of this approach is order of n square, since there are two nested for loops, and the space complexity would be order of n, which we can ignore because that will be just to store the. So basically this is just so we can actually make it order of 1 only, because we anyway have to take an answer array. Answer array we anyway have to take because that's how we are going to return the answer. So the space complexity for this we can assume to be order of 1, right? Cool. Now let's talk about the optimized approach and let's build some intuition for that. Let's see some observation. The first observation is that let's suppose the array elements are 12, 10, 9, 8, 7. Okay? 0, 1, 2, 3, 4. If let's suppose these were the elements, what is going to be the answer for them? What's going to be the answer for 12? Minus 1. Nothing is on right. For this, minus 1. For this, minus 1. Minus 1. Minus 1. Does that make sense? The answer for all of them will be minus 1. Now let's talk about another example. Let's say we have 5, 4, 3, 2 and 10. Now can someone tell me what is going to be the answer for 5 now? For 5 it's going to be 10. For 4 it's going to be 10. 3, 10, 2, 10, 10 minus 1. Does that make sense, guys? Cool. So the thing is that as you can see, when the sequence was in decreasing order, we got minus 1 for them. And here we also had a sequence in decreasing order. But once we got an element which was greater than them, so this element was greater than these elements, so the answer for them became 10. The answer for them became 10. Look at it like this. So let's suppose I have 5, 4, 3, 2, 10. So I start from here. This is 5, then this is 4, this is 3, this is 2. Now 10 came. So once the number came which was out of order and greater than them, so answer for them became 10. Okay, answer for them became 10. Let's look at one more example. We have 9, 6, 5, 4, 8. So this is 9, this is 6, this is 5, 4, then 8 came. So 8 is 8 to whichever element it is greater, it will become the answer to them. That is here. So this is 9, this is 6, this is 5, this is 4, this is 8. So 8 will become the answer for 6, 5 and 4. Okay? So basically now once we have got the answer for them, can I just ignore this and start by finding the answer for these now? Does that make sense? Does that make sense? Okay, giving you some intuition that here we are also ignoring whatever was redundant from the past. The idea here is that we have a monotonic sequence. We have a monotonic sequence over here. Monotonic sequence is when we have a decreasing or increasing sequence. So my point is that I had a decreasing sequence. Once I find an element out of order, so all the elements which are smaller to this will be the answer for them. This will be the answer for them. Okay? Now, so basically, let's say I have elements 11, 4, 3, 2, 10, 12. So I have 11, then I have 4, then I have 3, 2, 11, 4, 3, 2. Now 10 comes. Now 10 comes. So 10 is greater than these numbers. So answer for these will be 10. Answer for these will be 10. Now since we have got the answer for them, we can actually remove this. We can actually remove this, and now it will become such a sequence. It will become such a sequence. Now 12 comes. So this will come over here. Now whatever is smaller than answer, to them 12 will become the answer. So 12 will come over here and 12 will come over here. Now only. So we have got the answer for them. So we will remove it. And now we are just left with 12. We have completely iterated the array, and whatever we are left with, to them the answer will be -1. -1. Okay, so since we are ignoring whatever is redundant to us previously, and since this is a monotonic sequence, therefore stack will help us over here. So let's see the dry run using stack. So intuition was that we had to look at the just past, removing this just past. So whatever answer we had got, we will just ignore them, and now we'll start again from some monotonic sequence like we did over here, over above, right? Okay, so now let us go through the dry run using stack. Then again, if you guys will have some doubt, we will come to those. Okay, so I have 11, put it onto the stack. So 11 has been put onto the stack. Then we have 4, put it onto the stack. Then we have 3, put it on top of stack. Then we have 2, put it on top of stack. Then we have 10. Now this, you can see that this is a decreasing order. This is a decreasing order. Now we found an element out of order. So to whatever elements 10 is greater, the answer for them will become 10. So is 10 greater than 2? Yes. So we found the answer for 2. Answer for 2 is 10. Remove it. Is 10 greater than 3? Yes. We found the answer for 3. The answer for 3 becomes 10. Remove it. Now is 10 greater than 4? Yes. So we found the answer for 4. The answer for 4 becomes 10 and simply remove it. Now is 10 greater than 11? No. So simply push 10 onto the top of stack and move ahead and move ahead. Now we are at 12. So on top of stack there is 10. 10 is lesser than 12. So answer for 10 will become 12, right? Answer for 10 will become 12. Now, so we are at 12. Is 12 greater than 11? Yes. So answer for 11 becomes 12. Okay? So now nothing is there. Simply insert 12 on top of stack. Now move ahead. So we are done. We are left with no more elements. So whatever is present on top of stack, the answer for them will become -1. So in this case, answer for 12 is -1. Guys, does that make sense? So Anshul says that then in this solution, we need to also store index and stack. Anshul, that's what we are going to do. We actually need to store indexes on top of stack because we actually are trying to find the answer for the previous elements that we are done with. So let me quickly show you a dry run of how we can do this using indexes. Okay. So we are having the stack. We will place 0 over here. Then we will place 1, right? Then we will place 2. Then we will place 3. So basically still the array is in decreasing order. Now we found 10. So this 10 is greater than what is present on top of stack. So basically answer for this. So we will write it like this. We will write it like this. S dot top. Okay? Because this is the index. So a of 3 is nothing but 2. So 10 is greater than 2. Answer for this has become 10. Then likewise, answer for this will become 10. Element at index 1 is 4, which is lesser than 10. Answer for this becomes 10. Now 11 is not smaller than 10. So we will simply push the index of 10, which is 4. Then we are here. Now this is 12. 12 is greater than a of s dot top. So we will simply mark the answer of a of 4 as 12. So this is 12. Again, so as we remove it, then a of 0 is lesser than 12. Answer for a of 0, that is 11, will be 12. And now whatever is present on stack, whatever is present in stack, you will simply mark their answer as -1. So you will put -1 here. And the time complexity of this approach is order of n. Since we are putting an element and removing an element just twice, so again order of 2 into n, which is nothing but n. And space complexity in the worst case can be, when let's say the complete array is in decreasing order, it will be order of n. So does that make sense to everyone? Okay guys, so we have actually placed the link to the questions for the next questions. Okay, so hope you guys try it, and guys, this was it. I hope you enjoyed it. Cool. Please try them. See ya. Bye-bye.
Hey everyone, in this lesson we will discuss logical view or abstract view of queue data structure. Basically, when we talk about abstraction, we don't go over implementation details. We generally discuss about features and operations. In actual practice, queue is a structure in which whatever goes in first comes out first. So in general, queue is a FIFO structure. Whatever goes first, it should goes out first. So if we want to construct queue as a data structure, then we need to support both insertion as well as deletion in the queue. In queue, as we need to maintain FIFO property, so both removal as well as insertion should happen from different end. It means if insertion happens in the front, then deletion should happen from the end and vice versa. Let's take an example to understand this thing. Let's say this is the snapshot of the queue at some particular time. Let's say this is the snapshot of the queue. And this is the front element of the queue and this is the last element of the queue, or we can say as rear element of the queue. Now, so as we can see here that if we want to make an insertion, it should happen at the end of the queue, which we call as the rear or tail of the queue. Likewise, deletion should happen from the start of the queue, which we call front of the queue. As if I want to delete some element, it should be even because this element entered first into the queue. And if I want to insert some element, it should insert here. So this is the snapshot of a queue at some particular time. Okay, so what we have seen here, queue as a abstract data structure, a list or collection with the restriction that insertion can be performed at one end, that is the rear of the queue, and deletion can be performed at other end, that we can say here as the front of the queue. Let's discuss operations in the queue now. If we want to create a queue, what sort of operations that we need to support? The first operation is insertion, which we call enqueue in the terms of a queue, or we can also say it as push operation. We need to push an element into the queue. And also one other operation that we need to support, that is the dequeue, where we need to remove one element from the queue or pop an element from the queue. Now, if I want to create an interface for the queue, how it will be like? Let's discuss about that. If I want to create an interface for the queue, it will be something like I need to support these functions. The first function is enqueue, which supports insertion. And the second operation is dequeue. And here I am assuming that queue is maintaining integer elements, but it can be of any type. Okay, and the dequeue operation means delete an element from the queue, and where this return type symbolizes the element that I deleted. It solely depends upon the implementation that whether we want to return that element or not. We can keep it as void as well. That depends upon the implementation. Also, what sort of other things that we may need from the queue? That what is the element which is present at the front, or we can say it as peak. Is my queue empty or not? So these sort of operations that I may need in order to implement a queue. So what we can say that in high level terms, these sort of operations that we need to figure out in order to implement queue. And most of the languages has an inbuilt library which provides the interface, which may vary from language to language. And as a developer, we don't need to worry about the implementation details, and we can create a queue data structures with the help of available functions. As we have seen here that the operations can be enqueue, dequeue, front is empty. Now what we can say also as queue as a container which is open from both ends. As we have seen here that we are entering an element from this side and removing an element from this side. So it is actually an open container where element goes in from one end and element removes from other end. Now, let's say we have this operation available in the library. Let's try to simulate queue. Okay, let's say in the starting we have an empty queue and we need to insert an element 2 into the queue. That means as we have a library, so then we can simply call enqueue function of that library and we can insert queue in our 2 in our queue. So when we insert 2, it will come from here. Fine. So now, as we know that we need to maintain 2 pointers or 2 variables which keeps track of which is my front element as well as which is my rear element. so that the implementation becomes easy. But so if we have only one element in the queue, then both front and rear pointing to 2. Fine. Now let's say we are inserting one more element into the queue, that is 5, and it will go from the rear side, from this side. Now we need to update our front and rear. Let's say internally the library, it's handling all those things. Now the rear reaches here and front remains here. Now let's say we have one more operation. Let's say somebody asks one more operation to insert 3 into the queue. Then the snapshot of the queue will be something like this, where the rear is pointing here and front is pointing here. Now let's say somebody asked us to dequeue an element, that means delete an element. As we know that deletion occurs from other end, from this opening of the container. So then our front got updated to 5 and the rear will be 3. So now we have done the simulation part and we have seen and the queue in a high level way actually. Now let's discuss some real world examples to understand it better. And it is generally used when there is a shared resource that's supposed to serve some request, and resource can handle one request at one time. In such scenarios, it makes more sense to queue up the request and the request that comes first serves first. Let's consider an example. Let's say we have a printer that is being shared across the network and it can print only one document at a time. When more than one request comes to it, it cannot say that I cannot serve your request. So what printer will do? It will maintain a queue of requests and serves them one by one as long as there is a request in a queue. It will keep picking up the request one by one. Let's say we have a printer and all these computers, they are requesting to the printer for the request to print a document, but the printer can only print one document at a time. So what the printer will do, it will maintain a queue and store all the requests into the queue. And what it will do now, after serving a request, it will pick an element from the front of the queue and serve that request. In this way, it will manage everything. So this is one of the real world scenario where we can use queue. This is good for the introduction part of the queue. In the next lesson, we will see how we can implement queue. Thanks.
Hey everyone, as you can see here that we have already maintained the 8-day streak and we need to maintain a streak. So in today's class, I think we will solve some of the questions of stack and queues. Proceed at that level. Let's solve some questions. Okay, let's solve the very first question. The question is, let's say all 3 questions of this clever stack. Okay, let's start the question. We have been given an array and in that array, we need to find the nearest smaller element gi for every element ai in the array such that the element has an index smaller than I. Okay, let's say we have more boundary, gi is the element aj is greater than I. Okay, the basic question is, for each particular element in the array, we need to figure out the nearest smaller element for that particular element in the array. Okay, let's say this is our array. And for 4, as we can see that no element is less than 4 in the left side. So we have g1 is equal to -1. So for 5, as we can see that the minimum most element for 5 in the left side is 4. So our answer will be 4 for this case. Now if I can see for 2, okay, both 4 and 5 are greater than 2. So for 2 as well, I can see that there is no minimum element in the left hand side. So -1 will be for this as well. Now, okay, similarly, okay, now let's try to solve this question. Okay, how I can solve this question? Let's first think. Okay, for each element, if I do in a brute force way, what I need to do, I will just iterate over all the elements in the left hand side and I just figured out whether there is an element which is lesser than that particular element. If I figure out that element, then I found the answer. In that way, I can proceed. Let's first copy this example. Okay, okay. Now what we can do, how we can solve this question, let's see. Okay, let's say, let's start from the end. Fine. Okay, let's say in the initially we have an element 8 only. Okay, now as I move ahead, I just found an element 10, and I know that that element is greater than that element. So I haven't find the answer for 8 as well as 10 yet. So what I can do? Okay, now I just figured out 2. Okay, one thing that is clear to me that 2 is smaller than 8 as well as 10. So okay, so one thing for sure that I can say that 2 will be the answer for both 8 and 10. Okay, so what I can do, I can update my answers and I just need this data point only because I already figured out the answer for this. So I just need to maintain 2 only. Now let's say I just go into the other element. I have 5. Okay, if I found 5, when I have 2 to which I need to figure out the answer. For 2, I know that 5 won't be the answer. So I haven't found the answer for 2 as well as 5. Now I figured out 4. Now I figured out 4. I can say that, okay, 4 is lesser than 5. So for 5, 4 definitely will be the answer. For sure. But for 2, it won't be the answer. So after then, I need to store these 2 points. Isn't it? So the way if I will do in that way, I will figure out the answer. So what I just think, okay, I am appending the elements, and as I'm appending the elements, I'm checking. And if I need to check the element, what I'm doing, I am just first checking for the last element and then the second last element, and I'm doing in that way, and I'm able to solve this question. If I'm able to do in that way, then it's easy to solve. So I need some sort of data structure which helps me to maintain this information. And that data structure should be something like where I can add the element in the end such that I can also remove the element which I just added in the end. So it should be last in, last out. And we know that stack is that data structure which provides that sort of thing. So I can use stack here and just try to solve in that way. I am able to achieve, because what I am doing, I am adding an element in the stack, and when I just found an element which is lesser, what I am doing, I am just checking with all the elements in this stack, and if I figured out an element which is greater than that element, I'm just removing it to the stack. So only I am adding an element one time into this stack, and I also am removing from this stack only one time. So that means it's kind of order of an algorithm that we just achieved. Okay, let's try to think how we can write code for this question. Okay, let's write the code. Okay, let's try think what are the constraints that we have been given. Okay, we have not been given any constraint, and the thing is, if we haven't find an answer for any element, we need to return -1 for that particular case. Okay, let me first, what I can do, let me first figure out the size. Okay, let me create my answer, which is of size n, and let me have the default value as -1 for each particular element in that particular array, because we haven't find the answer, and we will follow the algorithm as I discussed here so that we will be able to achieve our solution in order of n time. Okay, let's try to think, okay, how I can do that. We just need to iterate. In the last element, I need to move till the first element. In that way, I need a stack data structure to maintain the information as I just discussed. Why? Okay, so now what I can do if I need to question, okay, one thing I need to be sure that, but what will be the edge case? If my stack is empty, or if I have my element which is at the top of my stack, okay, if I figured out an element, okay, which is greater than my top, then that means I haven't found the answer for both of the elements. So I need this data. So I need to push that element into my stack. If that is the case, if that is greater than, that is element is greater than or equal to my that element, so I need to push that element into my stack. Isn't it? Okay, now I'm done here. So I can new. Okay, if there is other case, if the element at my top is greater than AI, if that is the case, then I need to check for how many elements I have found the answer. So let's first just check the edge case, whether my stack is empty or not. While my stack is not empty and my top element in the stack is greater than AI, in that case, what I can do, I know that answer for stack dot top will be equal to AI for sure. And I can safely remove that element because I just figured out the answer for the topmost element in this stack. Now I need not need this data in the future, so I can safely remove it. By the time this thing gets ended, I can say that okay, now I'm done. Now I can safely add a ith element because I haven't found the answer for ith element yet. And in the end, what I can do, I can return my answer. And let's check once again whether I'm doing in the right direction or not. I am maintaining my answer, and I just created an empty stack, and I'm checking if my stack is empty or if it is greater. So then I need to push that element into this because it's of no use. Otherwise, I need to check if my element is lesser. So that means for that topmost element, I just figured out the answer. So what I need to do, okay, in that way, if I just do in that fashion, I can solve. Okay, that seems like a good approach. Let me test. Okay, it's giving me correct answer. So let's submit. Oh, nice. Nice. We have solved this question. Now let's move to the next question. Okay. What will be my next question? Okay, now the next question is I need to figure out the largest rectangle in the histogram. Okay, that is my question. Let me think. Okay, let me first read the question. We have been given an array of integers a of size n where a represents a histogram. That is, ai denotes height of ith histogram bar and width of each bar is 1. Okay, let's say we have been given this histogram and where the height of first bar is 2 and the height of second bar is 1 and height of third bar is 5 and fourth bar is 6 and so on. And above is histogram and width of each bar is 1. And we have been given heights like that and we need to figure out the largest rectangle in that histogram. Okay, let me think how we can figure out that thing. Okay, if that is the case, this will be my answer. Okay, they are saying this is my answer and the answer will be 5 as my height and 2 as my width. So my answer for this will be 10. Okay, so let me just copy this thing. Let's try to think how I can solve this question. Okay, so the question was we have been given an histogram where the values are 2, 1, 5, 6, 2, 3. Okay, and we have been given histogram like that. Let me first draw the histogram on the paper and then it's more suitable. Okay, 1, 5. Okay, it will be 5 and then 6 and then 2 and then something 3. Fine. So this will be my answer in this case. So what I can think is what can be the brute force way to solve this question. One thing is coming to my mind. I can solve it in a way that, okay, let me take all the contiguous segment to solve this question. Okay, and I can take all the contiguous segment of length 1, then length 2, and just try to find the answer for that contiguous segment. Let's say I just take this contiguous segment of first 3 element, which is 2, 1, and 5. What will be my answer for this contiguous segment? Okay, I know that the width will be equal to 3, but what will be my height in this case? Okay, I can surely say that if I want to build a rectangle, then the height will be the minimum height histogram available in that contiguous length, isn't it? So I can say that the height will be 1. If I do in that way, then I can solve this question. That is fine. Okay. So if I just take in a brute force way, so how much time it will take to me? I need to iterate over every contiguous segment and to I iterate over each contiguous segment. I need to take two variables L and R. So it will take order of n square time. And for each contiguous segment, I need to find the minimum most element. So the complexity will go up to n cube. So it doesn't sound me a good solution to solve this question. Can I think something else to make my algorithm better? Okay, let's think what I can do. Okay, let's think. Let's say I have an example, something like this. Okay, let's say this is my example. If I build a histogram, I have 7 here and I have 8. I have something 6. I have again 8. And I have something again like 7. Okay, if I am just considering all the contiguous segment, I will consider this segment as well. And I will consider this segment as well. I will consider this segment as well. I will definitely consider all the segments. If that is the case, that means, but I know that for all these segments, if I did in that segment, 6 is the part of that segment, then my minimum value will always be 6. Okay, can I use this idea to achieve something? Okay, why I am just iterating over all the contiguous segment? Why not that maximum contiguous segment for 6, which will give me the answer? Because in any way, other contiguous segments are waste for me. That's the waste of computation time. If somehow I just figured out for that particular 6, what will be the maximum contiguous segment if I just consider this element? So one thing I can surely say that, okay, if I just consider this element, how much elements I need to take in the right hand side that I need to consider. Okay, I can consider 8, I can consider 7, but if I have something 5 here, I can't consider that element. Okay, this gives me the idea that what I can do, I can just take the nearest minimum element for a particular element in the right side. Fine, because such that all the elements in between will be greater than 6 and I can consider those elements for this element. And likewise, I can extend my similar approach in the left side as well. So this gives me some idea. If I do in that way, I can solve my problem. Okay, so this gives me the idea what I need to do for each element. For each element, I need to figure out the nearest minimum element in the right hand side as well as in the left hand side. Because I can surely say that this will be the maximum contiguous length for that particular element, which will give me the answers. And if I take any smaller contiguous length for that particular element, they are of no use. And in the previous question, we just solved how to figure out the nearest minimum element for any particular element. And we know that we can solve this using stack in order of n time. We just solved it. Okay, I can use that approach here as well and I can solve this. And I can solve similar for the right hand side and for the left hand side and I'm done. That is sounds like a good solution. Let's write the code for this now. Okay, let's write the code for this question. Now let's say this is the case. Let's first try to dry run this. Okay, now for 2, I know that the nearest minimum element for 2 in the right hand side is 1 and in the left hand side I don't have any element. Fine, and so I just end up with the contiguous segment of one element only for 2. So that means for 2 my answer will be just 2. Now if I take 1, now for 1 I can see that for 1 5 is greater, 6 is greater, 2 is greater, 3 is greater. So I can pick all the elements for 1 in the right hand side. That is good. And in the left hand side as well, I can pick all the elements. That sounds like a good thing. So I can do like that. If I do in that way, so for 1, length available will be equal to n. So which is 1, 2, 3, 4, 5, 6 in this case. So my answer will be 6. Now for 5, if I do in similar way, I can see that for 5, the minimum length available, 6 is greater than 5. And okay, I found element 2 which is less than 5. So I can only consider these 2 elements for 5. Now if I just think of an element in the left hand side, I can see that 1 is the minimum element for 5. So I can consider only these set 2 elements for 5. So I have a length of 2, for 5. I have a length of 5. So my answer will be 10 if I take 5 as a length. Okay, now if I take 6 as a length, then my area to consider for 6 will be, I can't take this element because this is smaller than 6, and I can't even take this element. So because these two elements are the nearest minimum element for 6. So I just have a one length for 6. So my answer will be equal to 6 only. Okay, now I consider for 2. If I want to consider for 2, okay, 3 is greater than 2, so I can consider that element. Now if I move into the left hand side, I can see that 6 is greater than 2. Okay, nice. And 5 is also greater than 2. Nice. But 1 is smaller than 2. So the nearest minimum element in the left side for 2 will be 1. So I can consider only these two elements for 2. Fine. So the total elements I can consider for 2 will be these 4 elements. So my length will be 4. So my answer for this case will be 8. Now for 3, let's consider what will be my length. Okay, for 3, I can say that for 3, there are no elements available in the right hand side, but let's see what are the elements available to me in the left hand side. Okay, 2 is the nearest minimum element for 3 in the left hand side. So that means I have just of length 1 for 3 and answer will be equal to 3. Okay, I have considered all the elements by using that analogy, and I can see that if I want to consider that element, so I can just get the maximum length of 5, maximum length of 2 for 5. So that means it's okay to do like that, and in the end what I can do, I can found the maximum answer out of them, which is 10. So 10 will be my answer. Nice. If I do in that way, I can figure out the answer. Nice. And I can see that 10 is the answer for this question. Nice. So let's try to write a code for this. What will be the simplest code to write the solution for this will be, let's first have a size. Okay, I need two informations for every particular element. What will be the nearest smaller element? For that element in the right hand side, I also need the information, but with the nearest smaller element for that particular element in the left hand side. So I need both the information for any particular element. So let's say I created two vectors. The one of them is storing the smaller in right side. I need that information for all the elements. So I just initialize. I just need the size of n, and what should be the default value? Okay, I know that if for that element I haven't found any element which is lesser than that element in the right hand side, so I can say that, okay, let's just say that, okay, so in that case I may end up end of my list, so I can safely mark it as n. Okay, because that seems like a good thing. Okay, now I need one more information which is smaller in the left side. I need that information as well. Okay, if I need that information, so I need this information an element, and in similarly I know that if I move into the left side, I haven't found any element which is lesser than this particular element, so I end up with an index of -1 because something like it goes beyond 0 in the left hand side. So I can pick the default value as -1, which seems like a good thing to me. Okay, now let's fill both of these arrays. How we can fill? So this is quite simple. We need a stack for this, because what we need to do, we need to figure out the nearest most element in the right hand side as well as the left hand side. As we discussed in the previous question, we can easily do this by using stack. Let's say I created a stack. Now let's first solve it for the right side. And let's say I need to iterate. Okay, now how we can do that thing? Let's say I consider the edge case. Let's say my stack is empty, or the value available at the top of my stack is actually less than or equal to my current element. If that is the case, so I haven't found the answer for my current element yet, as well as for any element which are at this stack, because I just found an element which is greater than the element present at the top of the stack. So I need this information. So I need to push that element into the stack. So that's the only thing that I can do. So I have done. I am done here. So I can continue. Now, if that is not the case, that means what does this means that I am at the top. Okay, I need to first write the edge case. I need to iterate up till my stack is not empty, and my stack top is, if it is greater than AI, that means the ith element, it's basically lesser than the topmost element. So I can say that for the topmost element, ith element will be my answer. So as I'm moving into the right side, so I can update the answer for smaller right side, stack dot top. I can safely update it as I. Now I need not need the information for that particular element, so I can easily safely pop that element from my stack. Nice. So if I do in continue that way, I haven't figured out the answer for I yet, so I need this information. So I need to push that element into the stack. Let's say I just push that element in my stack. Fine. If I do similar way for my left side to populate this array, okay, I just need to apply the similar algorithm for this case as well. So what I can do, I just move into the left side now, and my algorithm will be something like this only. So I can just copy the same algorithm. Okay, so if that is the case, so but instead of left side, now I'm populating my left array for each element. Now, by doing these two operations, we just populated both of my arrays. We now have that information that for each particular element, what will be the nearest smaller element in the right side, as well as we have that information what will be the nearest smaller element for a particular element in the left side. We have both the information. Now, let's calculate the answer. Let's say initialize my answer as 0, because obviously my answer will be bigger than that 0, so I can update my answer for each particular element. Now, what I can do, okay, now what I can do for, let I have an element in consideration, which is element in consideration, let's say it is a of I. Now, what will be my temp answer? That temp answer is basically this answer, which symbolizes that if I take this particular element in consideration, what's the maximum area of rectangle that I can achieve? Okay, let's try to think. Maximum rectangle area that I can achieve for that particular element. Okay, for that, my length will be, height will be this, and what will be my width? I know that if I need to figure out the width, I need to find the nearest smaller element in the right side as well as in the left side. So for this, that's why I just keep the default value as -1 for left hand side and n for right hand side, so that it's easy to compute that thing. So let's say for 2, I have my nearest smaller element in the left side will be -1 and in the right side will be 1. So if I take the whole length will be equal to 3. If I take the whole length, my whole length, that is nearest right side minus of particular that element I, and I take the nearest left side, the particular element I plus 1. So this will be the total length. But in that particular length, I just include the nearest smaller element in the right side as well as for the left side. But I don't need to include these two elements, because these two elements shouldn't be included in the rectangle. So I can safely remove -2 to remove these two elements, and I can update my answer as max of my answer and temp answer. If I do in that way, I can easily achieve my answer and I safely return answer in the end. Let's see. Okay, I just initialize my array and I just keep my smaller right side as n. I just add the default value as n. For the smaller left side, I just did in the similar way. I maintain a stack. Okay, we missed one thing. Okay, what we need to do, because there are many elements. After solving it for the right hand side, for that particular elements, we haven't find any elements in the right side which are smaller than that element. So that element still remain into this stack. So I need to remove all that elements from my stack. So I need to remove. Let's say I removed that algorithm from my stack. Okay. So now let's look at the complexity part of it. This is running order of n time. This is running order of n time, and also this is running in order of n time. So the overall complexity will be 3n, which I can safely say it as order of n. Okay, nice. So we just solved this question in order of n time. Nice. That sounds like good thing. Now let's test my thing first. Okay. Let's see the errors. We have an error at 51st line. Okay, I guess the error is okay. It's not nearest. It's smaller. A smaller. And is there anything else? Okay. Okay, this is correct. And you need to push. Okay, now let's test it again. Okay, nice. Okay, this everything seems correct to me. Let's submit my code. Let's see. Oh, nice. We solved this question. Nice. So now let's look the other question for today. We have solved both this question. Now let's look into this question. What this question is saying that we have been given an array of integers. This is a sliding window of size b, which is moving from very left of the array to the very right. And you can see that w numbers in the window. Each time the sliding window moves rightwards by one position, and you have to find the maximum for each window. Okay, so the question is, we have been given an array, and in that given array we have been given a window. We need to figure out the maximum element in that window, and that window is basically a sliding window. So what does it mean? Let me explain you. That let's say we have been given a window of size 3. So in the starting, let's say we consider the first 3 element of the window, and we figure out the maximum, and the maximum value for these particular 3 elements obviously will be equal to 3. As you can see that 1, 3 and minus 1, the maximum element for this will be 3. Nice. So now let's look at the other thing. Okay, now for if I just take the other next window for this particular case, the next window will be 3, minus 1 and minus 3. Nice. So if I take this window, and then I can see that the maximum for this window will be equal to 3. Nice. If I take the next other window, then I can say that the maximum for this window, it's equal to 5. Okay. And for this window, if I go in the similar fashion, I can see that, okay, the maximum is 5. And for other window, I can see that the maximum value is 6. If I go in that way, okay, if I take the last window, the maximum value is 7. Okay, so this is my question. How I can solve this question? Okay, let's think. Okay, let me move to here. Now, how we can solve this question? Let's see. Okay, we have been given as some array. Let's say we have been given array. Let's say we pick the random array now. 4, 7, 8, 3, 2, 5, and we have been given b as 4. Let's say this is given to us, and we need to figure out the maximum element in each window of length 4. So the first window will be 4, 7, 8, 3. So the maximum value for this window will be equal to 8. Nice. Now the next window will be this, and again the maximum value is 8. Okay, the next window is this, and the maximum value is 8 again. Okay, how I can solve this question? Let me first think. Okay, I need to consider all the windows. So the brute force way will be, I maintain a window and I just keep one start and end, which is referencing my current window, and I just figure out the maximum element in that particular window and I will get an answer. That's the thing that I can do, and I will achieve the and I can solve it. But now let's look at the time complexity to solve this question. Okay, if I maintain one window, that means, what does it mean? It means if I need to find the maximum, okay, one way is what I can do. I can just find the maximum. I do the iteration from start to end, but this will lead to other order of n time, and how many updation that I need to do for start end, as there are only order of n windows. As we can see that the first window is of 4 element, then the next window of this 4, and the next window of this 4. So there are only 3 windows, and that's of order basically n. So the overall complexity will be order of n square. Can we improve this algorithm? Is there any way to improve this algorithm? Okay, the one way that we can do to improve our algorithm is, what I can do, I can maintain some sort of structure that we know, and that will tell me the maximum element within a given range. Within a given range, I can do something like that, and maybe that will solve my question. But if I need to maintain that structure, we already know that the segment tree provides that sort of flexibility that gives us the maximum value in a particular range. Okay, and this will solve my problem in order of n to order of log n. If you can use something like that, but even then my complexity will be n log n. Can I improve further if I want to solve this? Let's see. Maybe we can improve it further. Okay, let's say we have been given an example 4, 7, 8, 3, 2, 5. Okay, what we can do? Okay, what I can see here that, okay, let's say the window size is 3. Let's say the window size is 3 in this question. But I can say that, first of all, let me consider the first 3 elements of this window, which are 4, 7, 8. Okay, I just figured out one thing, that if I have only one element, I can store this information. Now I encountered an element which is greater than that element. If that particular element is greater than that particular element, so I can say that this element won't be the answer in any of the window. Why? Because this, I just found an element which is greater than this element and has a greater index as well. So that means if there is a chance that I will just need to remove an element, that will be the element of lesser index, obviously, for sure. And if I just figure out an element which is greater than this, so that's of greater use than this. So I don't need this information. So I can safely remove this information, and I can keep this information only. Now, in the similar way, if I figured out 8, okay, I can remove this information as well in a similar way, and I can just store the information 8 only to solve my answer. Okay, if I do in this way, I can solve this question. Okay, let's see. Now my answer is 8 for this. Now, okay, now let's say I now come at 3. If we figure out an element which is lesser than this element, okay, but I can't say anything now. I can't say anything now because there may be a possibility, because it has a larger index, there may be a possibility that for some other window, this will be my answer. So I need to store this data as well. So that means we are coming up with some algorithm. If we are figuring out an element which is greater than any particular element, if that is the case, so we can safely remove the element which is at the end of my some data structure. And if I figure out an element which is smaller than that element, so I just need to append that element in the end. Nice. But one thing we also need to show that if we go in some other window, we need to remove the elements which are not in that window. And as I am just adding all the elements in the increasing order of index in that data structure, in some data structure, so I can just check whether the first element is of previous window or the current window. If it doesn't belong to the current window, I can safely remove that element. So, okay, so one thing that I'm sure that I need, if I want to solve this question by using this algorithm, I need a data structure which will help me in adding in the end, also removing in the end, and also allows me the ability to remove from the front. Okay, and all those operations should be as efficient as possible if I want to make my algorithm faster. So what data structure that comes to my mind? Okay, can I use stack? If I use stack, then these two operations will perform in a good way, but not this. Okay, so what sort of data structure I can use now? Okay, can I use queue? If I use queue, I can do this operation and this operation, but I need to sacrifice over here. Okay, then what other data structure that I can use? If I'm using some complex data structure, then the complexity will be log of n. And we already know that we just build a segment rather than that data structure that will already solve us our problem in loader of log n. So we need some sort of data structure. Okay, one thing that comes to my mind, why don't we use the doubly linked list? In the doubly linked list, we can add, and we have both the pointers head and tail. We can just add the element, and then we can easily remove the element from the end in order of one time, and add that element in order of one time. And similarly, what we can do this thing in the front as well. If we follow this approach, we make our algorithm efficient. Nice. So in C++, we have this doubly linked list in a form of dequeue. So we can use dequeue in our case and we can solve this question. Nice. So now let's try to look at the example and we'll solve this question again. We have elements 4, 7, 8, 3, 2, 5. Okay, if that is true, now let's try to think. Okay, I have a window of 3 elements. Let's say I maintain a dequeue where I just, if I have a first element, I just put it and I figure out the second element. If it is greater, so 4 is of no use, I can remove that element. So I can put 7, and if of no use, I can remove that element. I can put 8. Now I just end up with the window. What will my answer? It will always be the first element in the dequeue, isn't it? Because the way we are just storing the data, the first element of that window will always give me the answer. So if we do in that way, we can just get the things done, man. That's cool. We can do in that way. Cool. So now if I want to consider a next window, it will be something this. Okay, now let's see what is the index of 8. Index of 8 is 2, but in the current it belongs to the current window, so I not need to remove that element. So what I can do, I can just add 3 here because I need to add 3 because it is lesser than this element, and this element can be the answer for other windows. So I need to add 3. Now I am at, okay, I just add 3 and the answer will be again 8. And similarly, if I do it that way, I will find the answer. Now let's try to write the code for this. Figure out everything what is required, and we just figure out the algorithm to solve this question. Okay, how we will write the code? One thing is clear to you, one thing is clear to us that, okay, let's say first take the size. We need a data structure like dequeue, and let's say it's dequeue. Okay, now I need to iterate over my link or over my array. Okay, let's first do the parts. Let's say first cover the edge cases. If my dequeue is empty, and or if I have an element in the end of my dequeue which is basically greater than my current element. In that case, what we need to do? We just figured out in that case, we may need this information. So in that case, we can add this element in the end, and that will help me to solve this question. Now, if that is not the case, what we can do, we can check while, okay, my DQ is not empty, and we are getting, okay, we need to add 4 as well. What we can do, if my element in the back, they are lesser or equal to my AI, because I just found an element of greater index and it is greater than the last element of my DQ. So that means I don't need that last element in my data structure. So I can safely remove that element. Okay, I can do in that way. So in the end, I need that ith element. So I need to add this element in the end. So I am done. But I need to remove all the elements which are not belong to my current window. As we can see that, okay, my next window will start when I becomes greater than or equal to b. So what we need to do in that case, If that is the case, okay, let me first initialize my answer as well. Okay, and so that means if I just end up with an index greater than equal to b, what does it mean? It means that we just completed our one window. So I can add the answer for that window in my answer vector, which will be the front of my dequeue, as I already discussed why it is, isn't it? So it will be my front. Okay. Now what I can do, if that is the case, now what I need to do, I need to check whether the first element of my data structure is in the current window or not. So for that, first I need to check the base case. If my DQ is not empty, otherwise it will give us the segmentation fault. And if my DQ is not empty, and we can say that the element, okay, the index of the element in the front should be, if it is, okay, if it is the first element, it's the 0th element. If I'm at the second window, then the index, if the index is 0, then I can safely remove that element. So the index will be I minus pi, because if I at the next window, my I will be b and b minus b will be 0. If I'm at the next window, my I will be b plus 1. So if in the front I have the element which is having index 1, so I can safely remove that element. So if I do it that way, I can easily solve this problem. So if I do it that way, what I can do, I need to remove my element from the front. Okay, if I do it that way, I'm done. Nice. But okay, but what about the last element? What about the last element? When I'm at the last element, I haven't updated the answer for my last element. So I need to update it here. Let's say, okay, that will be, my answer will be pq dot front. Okay, I just don't need to add the answer dot front. It will be the element for that. So I need A for that case, A for that case as well. If I do in that way, I think this should work. I need maintain DQ, I maintain vector. When I do in that way, I'm pushing my answer. I'm considering only cases. Now let's test. Oh, I need to return answer as well for sure. In that way. Okay, nice. Correct answer. Now let's submit the code. Nice, we solved this question. Now we are already ahead of our streak. We completed the 2-day streak in a really good way. Okay, nice. So this is all about today's lecture. Thank you guys.
Hi everyone, this is Recursion. Welcome back to Scalar. In this video, we are going to talk about queue data structure completely. We'll be talking about different aspects of a queue data structure, how a queue is built, what is the basic functionality of a queue, what are the different applications of a queue. We'll see how we'll build a queue using an array. We'll see how we'll build a queue using a linked list. We'll also go through QSTL, that is how we can use the standard template library to use our queue library in our questions. We'll talk about different applications, different questions of queues. Like, this is going to be an extensive 4 to 5 hours course that will take you deep dive into queues. We'll solve problems from basics to medium level to very hard problems that involve some applications of BFS. So make sure you watch this course till the very end and gain whatsoever you can get out of queues as a topic. Along with that, if you wish that you're liking this content and you want more such type of content, you can subscribe to this channel, like this video, and now let's get started. Hi everyone, this is Ashwell. So in this entire episode, we are going to discuss about queue as a data structure, how queue is important, what kind of problems we can solve using queue, and why we have switched from, like, we have started arrays. You might have studied linked lists. From linked list, we moved on to stacks. And finally, now we are discussing queues. So all these data structures, like be it arrays, be it linked lists, be it stacks, so these are known as linear data structure. What do you mean by linear data structure? Linear data structure is a data structure in which the elements are stored in a linear fashion. Let's say we were storing elements in array. So how we're storing elements in an array? So let's say we have an array
of size 5, and we were storing numbers, let's say 1 2 3 4 5, and different operations were performed on array. Let's say we need to insert a new element in array, we need to delete an element from array. So we have seen millions of operations that have been performed on arrays. Apart from that, we have also seen linked lists. We have talked about how a linked list is made. There is one node, it has a particular pointer, this is storing the address of another node, and so on. In this way, we were basically discussing how linked list, and we were talking about advantages of linked list over array. Then we moved upon to stack. So stack is a particular peculiar data structure in which elements are arranged in a particular form. Like we called stack as a lifo data structure. What do you mean by lifo data structure? It means last in and first out data structure. So last in first out stands for, like, let's say we are inserting an element at the top, and that is the element that will be removed first. So the element which is being added at the last, it will be removed at the first. So that element is particularly, we used to call it as that this element is a part of stack. So we have studied all these data structures, and now we are discussing about queue. So starting with the topic queue, let me just give you a real life example of queue. Let's suppose you are into a movie theater. So what happens in a movie theater? Let's say you are in a PVR. So you and a group of your friends, let's say 3 friends, are going to PVR, and you want to purchase the movie tickets on the movie counter. Let's say this is the movie counter, and as soon as you reach the movie center, you see that there is a long queue of people. Let's say first person is standing here, second person is standing here, third person is standing here, fourth person is standing here, and they are standing in a queue. What do I mean by a queue? Is like first person is the one who came first and he stood here, then the second person came here, then the third person came here, then the fourth person came here, and here you came. Like this is A. Let's say you are coming after fourth. So how the movie ticket counter is going to resolve the movie ticket distribution? It's like, firstly, the person who reached the movie counter first will be getting his ticket at the first, and he will be going. Then the second person will be going, then the third person will be going, and then the fourth person will be going, and then your turn will finally come and you will get the movie ticket. So what actually is happening? Let's say this is a form of a structure in which we have had these many elements like 1, 2, 3, 4, and 5. So first element to be processed from this particular data structure is this. Like this will be removed first, and let's say we have to add another element, it will be added at this ending. This is known as the rear end. Let's say I'm adding 6, so this particular end is known as the rear end, and this particular end is known as the front end. So this will be removed. Next, after first, who will be given a chance? Second will be removed, then third, then fourth, and if we need to add an element, it will be added at the rear end or at the end of that particular array. So what we can say is stack, we called stack as a LIFO data structure, that is last in first out data structure. For queues, what we are seeing here is the person who is coming at the first is going out at the first. Like if you are coming to purchase the movie ticket and you are the first one in the row, so you will be getting the movie ticket at the earliest. So queue follows the property of FIFO data structure. That means FIFO stands for first in first out data structure. Like I hope the things should be clear till here. So if we go by a formal definition of queue, so you can say that a queue is an ordered list in which insertions are done at one end, that we called as rear end, and deletions are done from another end, that is the front end. So the first element to be inserted is the first one to be deleted. Hence, we call this as a FIFO data structure. Like I have told you a very real life example of how a movie counter or a movie ticket counter works, right? But how are we going to use this particular concept of queues While programming, like what's the use of queue in programming? Is it something that we should study? Why we should study? Let me just give you one more example. So you all might have at some point of time used a printer, right? Printer, it's used to print. It is connected to our computer, we give a command and our pages are printed. We supply the pages and we get a printout from that particular printer. So let's say I have 6 pages to be printed, right? So you give a command for 6 pages to be printed. So what you will see is, firstly, the page which is there at the front, like the first page of your notebook out of 6 pages, that will be printed. Then it will move on to your second page. Then it will move on to your third page. Then it will move on to your fourth page. Then fifth, and then sixth. So isn't this structure similar to what we represent a queue as? The page which is at the front will be processed first and we'll be getting the printout of the first page. Right? So how this would have been programmed? So during, well, like while programming, writing the algorithm, like how the scheduling is being done, so there might be a use case of queue, or like this was something that was make that would have helped you to understand how we are actually using queues in our programming, right? So apart from that, queue we call queue as an abstract data type, because we'll create our queue from the very scratch, and after we have created queue from the very scratch, we can use the queue to solve different problems. So we'll create queue, we'll perform different operations. Like in stack, you have seen that we have performed different operations. Like if you remember from stack, so like this is a stack, so we can push an element, that is adding an element, so we call that operation as a push operation. Next we have seen, if we want to remove an element from the stack, we call that operation as a pop operation, right? So we have seen these particular operation, push and pop. Like the like to get the top element from the stack, we use a function named as top. So similar to these functions like push and pop, what we have in queue is, there is something known as enqueue, that is to add an element in a queue, and something known as dequeue. Enqueue stands for adding an element and dequeue stands for deleting an element. So how these enqueue and dequeue operations are performed, there are certain other operations that we'll see that are required for queue. Like we'll talk about these operations in detail. We'll also talk about enqueue and dequeue in detail going forward in this particular lecture. But I hope this much theory is clear to you, and like if you haven't, like if there is something that is still lacking, I would request you to watch this video till again till here, and you probably most of the things will be clear to you, right? So this was something known as a queue, or this is something known as a queue as an abstract data type. So now I hope you all are aware of what a queue is, what all are the operations on queue. So now let's deep dive into how a queue is made, how a queue is formed, how we'll write the basic structure of queue. But before understanding a queue, let's see how the container for queue is made, right? So before queue, we have already studied arrays and we have already studied linked lists, right? So to make the container of queue, container of the form, let's say this, we can either use an array or we can use a linked list. Like both ways are possible. An array is also possible and a linked list is also possible. So first let us deep dive into how an array can be used to form a queue. Like all the functions that we have discussed previously, like enqueue, dequeue, front, is empty, get size. So all these functions we are going to understand in detail, and we are going to write the code for each one of them so that we can better understand how we can use an array to make these particular, to implement these particular functionality. So let us just take an array. Let's take an array. Let's say this is an array. Let me name this array as a data array, right? And let's give the size to our array. Let's say it's of size 5. It is given by the user itself. So let's say we have an array of size 5. We can index it. So it has indexing from 0 to 4, and we are going to implement our queue using this particular array. Now let's suppose what I have told you about NQ operation is like when we do an NQ operation, let's say I'm doing NQ 100. So when I'm doing an NQ 100, it goes and places 100 at this position, right? Now let's say I'm doing an NQ 200. So it goes and places 200 at this particular location. The user explicitly doesn't knows or explicitly doesn't provide this information that where to add the next element, because this is the functionality of the queue that automatically if we are adding a new element, it is to be added from this end. This end was called as the rear end, right? So automatically if we are enqueuing a particular element, so it will automatically be added at the rear end, right? So what will be the value of front? Let's say I'm doing a front operation, I'm calling a front function. So front is a function that gives us the frontmost element of this queue. So this is a queue, the frontmost element is this, so front will get the output as 100. Let's say I do a dequeue. So if I'm doing a dequeue, the front element or the element from the front end will be removed and we'll get 100 at the output, and also 100 is removed. Similarly, if I do a dequeue again, it will again give the output as 200 and 200 is removed. But if we are to implement everything on our own, so we need to specify ki how insertions and deletions are to be performed in this particular array. So to perform those particular operations, I will be needing something. So I'll be needing different pointers. Let's say I'll be needing a first index, that is next index, that will store the index on which I'll enqueue a new element, right? Now let's suppose, let me just erase this. So now let's say I am doing an NQ 100. So initially next index is the pointer that is used to get the value of the next index, at which particular index we are going to add the new element in our queue. So if I'm doing NQ100, like our queue is empty, as soon as our queue is empty, the initial value of next index is 0. Initially we have made the next index as 0. Now I have written a particular function, or I am performing a particular function that is NQ100. So I'll be changing the value of next index from 0 to 1 and I'll be adding 100 here. Is it simple? Yeah. So I'll be again doing, let's say, NQ200. Now what will happen? The value of next index goes from 1 to 2 and 200 is added here. So we are keeping a check, we are keeping a value that helps us know where to add a particular new element, right? I hope this is clear. Also, let's say I am doing one more NQ operation, NQ300, 2 will be increased to 3 and 300 will be added here. I hope this is fine. So apart from NQ operations, there are other different operations. Let's say there is a front operation. If I call front, so what I'm supposed to give back is, I'm supposed to give back the element which is present at the front end. So to get the element which is present at the front end, how we'll get that? So let me keep one more index. Let me just name it as first index. So what will be the initial value of first index? Let's say our queue is empty. If our queue is empty, what will be the value of front? So there'll be no value of front, right? That means we'll initialize the front index by -1 because we will be accessing the element which is present at the front. So this first index, initially it is -1. As soon as I write this NQ100, that means I am adding one particular element in my data array or in my queue. So the value of next index increases. Also, along with that, the value of first index increases from -1 to 0. And this only happens when we are adding the first element to the queue, right? I hope this much is clear. So let us discuss about a dequeue operation also. So when I say dequeue, so what will happen during a dequeue? The element from the front end will be deleted. So if the element from the front end is to be deleted, we'll be getting the output as 100 and 100 is to be deleted. So what happens in this case is the value of first index also moves from 0 to 1. It increases by 1. We'll do first index increase by 1 position if we are doing a dequeue, right? Now first index goes on to here because 100 is already removed. Now again, if I'm doing a dequeue, so if I'm doing a dequeue, 200 is again removed. If 200 is removed and 200 will be deleted, the value of first index becomes 2. Now 200 is deleted and the value of first index becomes 2. So in this way, these operations work. Apart from that, we can also have, let's say, one more variable by the name of size. So what does this size represent? So this size represents the size of our queue or size of our queue at any point of time. So what will we do by this particular size variable is, as soon as we add a new element to our array, we'll do size plus plus. As soon as we delete a new element, that is will dequeue, will do size minus minus. So the value of size will also be helpful to us going forward. I hope this much is clear. Now let's just erase it and write it again neatly so that you can have a better understanding. So what we initially had, we had a data array. We made this data array of the form this. So we have the size of the data array as 5 and we were performing certain operations. Now we know that we have different variables, that is next index, first index and size. So we have these three factors, these 3 pointers that can help us navigate through this queue, that can help us to solve and understand different parameters of the queue, right? So when I say different parameters of the queue, so let's say I'm doing an NQ, let's say NQ 100. So initially the value of next index is 0, first index is -1, size is 0, right? So I'm doing NQ 100. So what will this operation do is 100 will be placed at the 0th position. The value of next index will increase to 1. First index will also increase to 0 and size will be size plus plus and size will become 1. Let's say I'm doing an NQ 200. So what will happen? 200 will be placed here. Next index becomes 2. First index remains the same. First index is still 100 and size becomes plus plus, that is size becomes 2. Now let's say I am doing a front operation. So front function, what front functions gives? Front function gives the element which is present at the first index. So we'll check what is the first index. The element present at the first index, that is the 0th location, is 100. So we'll output 100. That's it. Next we'll check, we'll do dequeue. So what does dequeue gives? Dequeue is the function that will remove the element that is present at the first location, whether that is present at the front end. So this element will be removed. So 100 will be removed and 100 will be given as the output. What else will happen? First index, the value of first index will be increased. The value of first index becomes 1 in this case. So first index moves to here and size will decrease by 1 and size will become 1. Right? I hope I'm clear till here. What will be the value of size? If we call our size operator or get size of function, so we'll simply get the value as 1 because we'll return this size variable. We'll check is empty. Is our queue empty or not? So how we can check that? If the value of size at any point becomes equal to 0, we can say that our queue is empty. So in this way we are going to perform all these operations, and in between there might be some challenges, there might be some constraints that can help us understand how we can make our approach a little better. So let us take another scenario. So this scenario will help us understand one more use case or one more new functionality, new feature, how we can implement our queue, right? So let's say again I'm taking this data array I'm taking again. Let's say it's again of size 5, right? And I am again adding, let's say this time I have this next index, I have this first index, and I have this value as 10, this value as 20, this value as 30, this value as 40, right? And let's say I perform, so at this particular point of time, what will be the value of next index? The value of next index initially would be 0. When we add 10, it becomes 1. When we add 20, it becomes 2, 3, 4, 5. So it will be now 5 in this case. What will be the value of first index? The value of first index is still, initially it was -1. As soon as we added 10, it becomes 0. What will be the value of size? Size in this case would be 1, 2, 3, 4. Well, 4 NK operations we have done. So size will be 4 in this case up till this particular situation. Let's say I perform a dequeue operation, and after doing a dequeue operation, this value is removed. So we'll get the output as 10, and this value is removed. The value of first index becomes 1, size becomes 3, right? I want to do an NQ. Like let's say I'm doing an NQ 50. If I'm doing an NQ 50, 50 will be added here. The value of next index becomes, what will be the value of next index? Next index will become 5, and it was initially 4. Now it becomes 5, and the value of first index becomes, it remains the same. The value of size becomes 4 again, right? Again, let's say I'm doing a dequeue operation. So if I'm doing a dequeue operation, the number that is present at the first location, it is deleted. That the value present at the first index is deleted, and we get 20 as the output. First index becomes 2, size becomes 3 again. Now let's say I again want to do an NQ. So for doing an NQ operation, let's say I want to add 60. So now I will be inserting this 60 on the next index value. So next index value here is 5, but I don't have 5 in my array. The size is full, the capacity is not there. So, but still what I can see is there are 2 spaces that are empty in my queue, but I'm still not able to add a new element, even if 2 places are already empty, because we have removed those elements. So what to do in this particular case? Let's say we can solve this particular problem in this way. Let's say now I have this particular array. So these 2 spaces are empty, and here I have 30, 40 and 50. So what if I shift this 30 here, 40 here and 50 here? Now I'll have these 2 spaces empty. So it will look something like this. It will look something like 30, 40, 50 and 2 spaces are empty, and if I'll be performing NQ 60, 60 will be added here, and 7, well, if I'm doing one more NQ operation, 70 will be added here, and it goes on like this. But do you think it's a feasible operation? Like I am moving all the elements again and again in real time to these particular places so as to support this particular approach. We can do something better, a little more better than this particular approach. Let us try to think a little more again. So you have seen we again are facing a problem that we can't shift the numbers each time. So what we'll have to do in this case is, let me take this example once again. We have this data array, and inside this data array I have 10, 20, 30, 40 and 50. I have this next index, I have this first index, I have this size, and I have 10 and 20 already removed. The value of like the indexes are 0, 1, 2, 3 and 4. Now what I want to do is, like, what will be the value of next index in this case is, next index supposedly it goes on to 5, which is not possible. So I am stuck in this particular situation. The value of first index is 2 because first index has increased, and it is here now. The value of size is 3 as of now. Now still the size is 3, but the capacity of our queue is 5. The capacity is still, the capacity is the same. Capacity is a constant number and it will remain the same throughout. But the size is 3. Still we have 2 places remaining, but we are not able to add any new element in our queue. So what we'll do in this case is, let's say let's say I'm doing an NQ operation. I'm doing an NQ 60. So I want to add 60 in my array. So what I was initially supposed to do, I was initially supposed to add this particular 60 on the next index variable. So I was to add this on fifth index, but fifth index is not available. So what I will do is, rather than simply doing next index is equal to next index plus plus, rather than simply increasing the value of next index as soon as NQ operation is happening, what I will do is I will do next index is equal to next index plus 1 mod capacity, right? So after 4, like as soon as I reach 4, rather than moving from 4 to 5, what will happen is it will be 4 plus 1. So 4 plus 1 mod capacity is 5, so 4, that is 5 mod 5, it goes on to 0. So after fourth location of, like after the value of next index become 4, it reaches to 0 rather than going to 5. Now it goes from 4 to 0, and as soon as the value of next index becomes 0, we'll add the 60 at this particular position and we are done. Now again, let's say I'm doing NQ70, what will happen? 70 will be added on the next index location. Now what will be the value of next index? So now it is 0, so it will become, according to this new formula, 0 plus 1 mod 5. So that is 1 mod 5, it's equal to 1. So the value of next index is 1. R70 will be added here and we are done. At this position, the value of size becomes equal to capacity. The value of size is 4, then it became 5. So when 5 is equal to 5, that is size becomes equal to capacity, we say that our queue is full. So this is how we will be proceeding with our NQ DQ operations, with our getting the front element, getting the size, getting the isEmpty function. So all these functions that we have written, now we are going to write the code for the same, and I hope you will be as excited as me for writing the code so that we can build upon this particular approach in the form of code. So we'll be writing the code particularly in C++ on the interview bit IDE. So let's move upon to the code editor. So now as you can see that we are on our IDE to write the code for our queue to that we are creating using an array. So for that I'll be creating a class, let's say class queue array. Queue, let's say I name it as queue using array, right? So what will happen in this class is, so I'll create all the data members of this class that we have initially used. So the first thing that was there in this, like the elements that we were using for this particular queue were, like we need a data array, right? We also need something known as a next index variable. We need something known as a first index variable. We need something known as size, capacity. So these are the operations. This is an array. So initially, rather than specifying any type of array, like which kind of elements will it contain, whether it will contain integer data, whether it will contain character data, so we'll be simply using a template. That is, we'll initialize this data member as, let's say, t star data. So we'll be initializing our array. Like generally what we do is, like for example, if it's an integer array, we initialize it as int star array. So now we are initializing it as t star array. So t here represents a template. We'll specifically initialize this template also here, right? So it is initialized as something like template type name, right? So we have this t star array, we have int next index, we have int first index, I need size, I need int capacity, right? So these are the data members that I have created. Now let me just create the constructor that is queue using array. So this constructor will take, like initially when we are initializing our array, we'll just specify the size of the array. So the input parameter for this constructor will be int s and will initialize all the data members of our array. Constructor is basically used to initialize. So data array will be initialized as new p of size s, right? Next index value becomes, initially what was the value of next index? We gave the value of next index as 0. First index value was given as -1. Size initially is 0 and capacity is equal to the size that we are specifying for our queue, right? So we have successfully initialized our constructor. Now we will start writing some functions that we have already discussed. So the first function that we are going to write today is enqueue operation. So what will be the return type of enqueue operation? The return type will be simply void, right? Because we are just adding a new element into our array. So we'll an enqueue operation. So we'll write void enqueue, and inside this enqueue will again provide the element that we want to add in our array. So the parameter input argument will be t element. So what exactly is going to happen in this enqueue array? Let me just take you back to what we discussed. Let's just erase this, right? So what we were discussing is, like, as soon as we enqueue a particular number in this array, we had this particular array which we used to make our queue. When we were, like, say, adding 10, so the value of what we were doing is we were putting the new element at the next index position. Like inside our data array at the next index location, I'll be putting the new element. That's one thing. And what else I was doing, I was increasing the value of next index. How I was increasing the value of next index plus plus. No, we saw that next index plus plus might give us some problems. So how we increase the value of next index value was increased, and we wrote it as next index plus 1 mod capacity. And I hope all of you know why we have done this particular thing, right? Why we have not written just next index plus plus, but next index plus 1 mod capacity, right? Anything else that we need to do in this particular thing, and like you can think of, we had a size variable. We used to do size plus plus also as soon as we enqueue something. So this is the third thing that we're going to write. And also, like, initially the value of first index is -1, but as soon as we add a new element, that's the first element in our queue, so we'll be initializing this. So we'll be updating this first index also. So how we are going to do all these things that I have mentioned, let's just start writing with this enqueue operation. So what exactly I'm going to do in this enqueue operation is, firstly, I'll go to the data array. I'll see what is there at next index. At next index, I'll put element, right? And I'll do next index is equal to next index plus 1 mod capacity, right? And also I'll do size plus plus. Is there something that we are missing? The first index operation, right? So I'll put a check, like whenever, like if the value of first index is equal to -1, then only I'll do first index updation to 0. In all other cases, I'll not be specifically updating this from -1 to 0. So this is the only case when we find out that the first index is -1, that means our queue is empty and I am just putting out the first element, so I'll need to update the value of first index. What else we can do? Anything else that you think we are missing at any point of time? We also discussed one thing, if you remember. So what happens if the size of our array is equal to capacity? If size is already equal to capacity, we have no place in our array. Like this is 10, 20, 30, 40 and 50. So now if I want to add 60, there's no space. So let me just cover this edge case as well. Like if the value of size is equal to capacity, I'll put out a message that is my queue is full, and I will simply return without doing anything. I hope this is a good enqueue function. This is a good enqueue function that we have written. Now let's move upon to another function that we are discussing. So there is a function that is a very simple function. Let's say size, right? So what will be int get size? Let me name this function as get size. So if I simply want to get the size of the queue at any particular point of time, what I'll do, I'll simply go and I'll simply return size. Is that fine? Yes, it's absolutely fine. There's one more operation that we have discussed, that was is empty. So what's the best way to check is empty function? So is empty will return, like it will return whether it's empty or not. So we'll have the return type as boolean return type. Boolean return type will tell us the value will be true if the queue is empty, the value will be false if the queue is not empty. So I'll simply write this operation and I'll return size equal to 0. When I say size equal to 0, what does this statement means? How this statement will give the correct answer? So in any case, when our size becomes equal to 0, what does this statement mean? This statement will be true only if our queue is empty. And whenever our queue is empty, we'll simply return this through this particular function, that is empty. Right? I hope this is clear to everyone. So there is one more function, that is the function that we were discussing, that is front. So what will be the return type of this front function? So let's just discuss a little about front function. So what we'll be doing in this front function is we'll make the return type for this front, because it's again of t type, so the return type will be t, and inside this front what will simply return, will return the element which is present at the first index. Matlab the element which is present here will simply return the element present at the first index. So what I'll do is I'll return data of first index. Anything else that I need to do in this particular function is, let's put one more check. That check will help us understand if at any case our queue is empty. So I'll check if is empty. If our queue is already empty, that means we'll see out queue is empty, and I'll return, let's say I'll return 0. Why I'm returning 0? Because I have a particular return type, so I simply can't return nothing. I'll have to return something. Let's say we are returning 0. So our front function is also done. So one function that is left is a dequeue function. So what we'll be doing in this dequeue function is, so what does the dequeue function does? So dequeue function basically, whenever I'll call a dequeue operation, it will simply remove this element that is present at the first index, and it will increase the value of first index plus plus. Along with that, there'll be certain other things happening. We'll get this 10 as the output, so I'll be having a return type again t, because I want to output that element also as soon as I am removing that particular element, right? So think again, what will this function work again this time also? Let me just erase this. So this time, like if I'm writing, like if I'm simply increasing the value of first index, so first index will also be increased using first index plus 1 mod capacity. I want you people to think on this. I've already explained how this thing works and what is the meaning of this particular thing. So I've already explained it in the case when we were increasing the value of next index, but during the dequeue operation, the value of first index, rather than doing it as first index plus plus, I will be doing it as first index is equal to first index plus 1 mod capacity. Try to think upon this particular approach on your own once again, and still you people, if you are facing any doubts, do comment in the comment section that you are not clear with this thing. I'll try to explain it to you once again, or in the comment section only, but I want you people to think on your own once, so that you have a little more clarity on this particular topic. Let's just move on to writing the code for dequeue operation. So when I say t of dequeue, So what will happen is in this particular thing is simply I'll store this value of the value present at the first index. So let's say I'm storing it as t result. So t result will give me data of first index, right? Along with that, I'll do first index is equal to first index plus 1 mod capacity, right? What else we were doing in this is, let's say I'm removing this particular element from my queue. I was reducing the size, so the size will become size minus minus, and we'll simply return this result. So is it done? Any edge case? Let's say in this also I'm putting a check for this empty condition. Once again, the same check in front that we made. Let me just copy and paste the same code so that we don't waste time. So yeah, so I'm writing if is empty, like if the queue is empty, we'll simply output queue is empty and will return 0. I think I am done with the code for our particular question. Let's just try writing out the functions, try executing it a little so that we can have a better clarity. Let me just erase it once. So inside this main function, what I'll do is I'll create queue using array. Let me just initialize the queue as queue, and I need to specify the size. So what will be the size? Let's say the size is 5. Along with that, I need to specify what is the type of data. So it is integer data because we have templated it. So that's why I'm putting this as integer. I would have put it, I could have written here char also if my queue was having character elements, right? So now queue of 5 elements is created. What I'll do is I'll nqueue nq1. Let me just copy and paste this several number of times. 1 is added, 2, 3, 4 and 5. I have these 5 elements in this nq operation in this queue. Let's say after this I just check on cout of queue dot front. So what will be the front element that we are expecting here in this case is, so I'll be expecting out 1 in this case. Let me just do cout queue dot dequeue. So it will again give me the same, that is output will be 1. Let me just cout the size now, queue dot size, get size, the function name was get size. So the size now will be 4. So let's just let me just go through if there is any mistake. There might be some typing error or so. Let me just go through the code once. If for all it is correct, then we'll try running it so that it so that we can check upon whether it is working or not. Hopefully it should be correct. Let's just try running it on the ID. So there is the class we haven't ended with the semicolon. Yeah, so exactly our code is running. The output for first is 1, the output for second is 1. Like we were removing the front element is 1, so output is 1. Then we are dequeuing front element, the front element becomes 1 again, and 1 is removed from the queue. I'm doing cout queue dot get size. So get size is giving me the 4 values because 1 is already removed. Now if I'll again do queue dot dequeue, let's say what happens. I'm again copying and pasting this 2 more times, right? So this should give us 2 and 3 as the output. So it will become 1 1 4 2 3. Let's see if it goes well. So we have the output 1 1 4 2 3. Now let's check the size also once again. So the output should be 2. Yeah, so the output we are getting is 2. So we have successfully written the code for implementing our queue using array. I hope you people have understood this code. Now let's see how we can implement our queue using linked list, right? Hi everyone, so we have already seen how we implemented our queue using array. So similarly, another container that we have for implementing our queue is linked list. So we'll see how we implement our queue using linked list. As you people are already aware how a linked list is formed, we have different nodes and a node contains two parts. First part contains the data that the node possesses and the second part contains the address of the adjoint node, the node that is next to this particular node. Let's say this is node 1, we have node 2, we have node 3. So all these three nodes are connected to each other because in this part of the node the address of second node is stored, in this part of node 2 address of third node is stored, and if this is the last node that we have, then null is stored here, and this node contains the data, this node contains the data. So this is how a linked list is formed. So how we can use this particular concept to make our queue in a much more efficient way, or you can say in another way of making a queue using a linked list. So while making a queue using linked list, we have, let's say for every linked list we'll need to create something known as head. So we'll create a head in this case also. Along with that, as we have already seen in the case of arrays, we need to maintain a size variable. This size variable will tell us what is the current size of our queue, because if we are not maintaining it explicitly what is the size of our queue, we'll have to traverse the entire list each time we want to know the size. So rather than doing that extra work, we can maintain a variable named as size that can help us overcome that limitation, right? So initially what will be the value of head? My head would be null. The size initially of my queue would be 0 if I have no elements. Let's say I want to perform some operations on my linked list. Let's say I am doing enqueue, right? So we have already seen there are different operations in linked list. So if I want to perform an enqueue operation, let's say I'm doing an enqueue10. So what do you mean by this enqueue10? So enqueue10 suggests that I want to add 10 into my queue. Like 10 is the first element of the queue. So what will be the thing that is going behind if we are creating it using linked list? So the first thing that will happen is a new node will create. So how will create a new node? Let's say I'm creating this new node with data 10 and address is null. So this is something that will be created. That's the first thing that will be created when we have an enqueue10. Next thing that will happen is we'll point our head to this new node, right? And size will increase by 1. This is the first step that we will be doing, or that will be having when we are enqueuing one particular element into our empty queue. Let's say I again perform an operation enqueue 20. So when I say enqueue20, so what will happen again? Again, a new node will be created. Let's say a new node created this time is having the data 20 and null in its address pointer. So what is going to happen this time is I'll make the address pointer of my previous node point to this new node, right? And this size is going to be increased to 2. So now I have 2 elements in my queue and the size will increase to 2 correspondingly. So now my queue looks something like 10, 20 and null. This is something that I have in my queue. Let's say I do an enqueue30. What will happen? I'll create a new node with data 30 and null. The address of the previous node will start pointing to this 30 and will name this new node. What will happen is this 20 will start pointing to the new node 30 and 30 will start pointing to null. So we'll have our queue of something like 10, 20, 30, null. So everything is all right, right? Do you feel that if there is anything that is missing or that is lagging? Let's take a scenario. So what will happen in this particular scenario is, so now let's say at one particular point of time, I want to know what is the front of my queue. So what I'll have to return if I want to know the front of my queue? Simply the node which is present at the head. So what I'll do is I'll simply return heads data, like the node which is present at the first. So I'll return that. So that is basically the front of my queue. This is standing at the first position in the queue. So if there is an operation by the name of front, we'll simply return heads data. That will give us front, right? Also, one thing more, let's say I again want to do an NQ, right? So if I'm doing this NQ again, what will, like, I'll be given only the head of the linked list, right? So only the head of the linked list. For adding 40 to my linked list, I'll have to traverse from this 10 to 30 again, right? Each time I'm adding a new node into my queue or into my, let's say, linked list, so I'll have to traverse the entire linked list up till end. Like I'll go on to 10, then I'll move on to 20, then I'll move on to 30, and I'll see there's null in the address of 30, so I'll simply put 40 in the address location of 30. I'll create a new node with the address, with the data 40 and address as null, and I'll do it something like this. But don't you think it's much of work that we are doing? Rather than doing this, I will prefer making something that is known as a tail pointer. Along with head, I'll maintain a tail pointer. So tail pointer will be the pointer that will be pointing to the last node of my linked list. So we'll have a pointer for the head also, and we'll have the pointer for the tail also. The pointer for the head will be giving us the front element of the queue, and the pointer at the tail will help us to know the rear element of our queue. So how the things will change if we are making a head and a tail pointer along with the size pointer. Now you might be clear. Now we have three things. While making our queue that we need to make. Earlier we were having only our head and our size, but now we have introduced something known as a tail, right? So what will happen in this particular tail pointer is that we will see in the next part. So now you can see that let's consider another scenario. Now you know that we have three things. First is tail, next is head, and next is size. So now I have these three things through which I can define my queue using a linked list. Now again, I do an NQ operation, right? Like let's say I do an NQ10. What will happen? Again, a new node will be created. Let's say a new node will be created in this way with the data 10 and address pointer as null. This is the new node, right? What initially head and tail both are pointing to null. Size is 0. So as soon as I NQ a new element in my queue, the value of null changes to the head. The value of head pointer starts pointing to this new node. The value of tail pointer also starts pointing to this new node, and the value of size increases by 1. Now this is my first element in the queue. Now let's say I'm doing an NQ20. So what will happen in this case? I'll create another node with the data 20 and address pointer as null. So what will happen in this case is I'll start pointing my tail to this new node, and this address will be pointing to the address of this new node. So now I have a particular pointer that can give me the last element or the rear element of the queue at the first hand. So the size will increase to 2. Similarly, if we are doing NQ operation, let's say 10 times, what I'll have to do is rather than traversing over the entire list, I'll just point my tail pointer to the new node, and tails next will be I'll do tails next will be equal to new node, and tail will be equal to new node. Like this is the basic terminology that we'll be using when we'll be creating our linked list using our queue using linked list. So apart from that, like we have seen NQ operation, we have seen a front operation that gives the front element of our linked list. Also we'll see some more operations like get size. So get size at any point will return the size of my queue, so that will just need to return the size variable. Also there is something known as isEmpty. So isEmpty will tell us whether our queue is empty or not. We'll check if size equal to 0, then the queue is empty, else it is not. There's one more operation, that is dequeue. So what happens in a dequeue is how we can delete a particular element. Let's say we have 10, 20, 30, null. My head is pointing to this. My tail is pointing to this. Size is 3. So this is a scenario. Now I call a dequeue operation. what happens in a dequeue operation is the element which is present at the front that we are going to delete, because it's a FIFO data structure. FIFO stands for first in, first out. The person who is standing at the first in the queue will be removed first, or he will be getting the movie ticket first. So now we have this particular queue. So what will happen is we'll remove this particular element, we'll store it in a temp variable. Its data will store it in the temp variable and will return, dequeue will return first thing the data of our front element. Along with that, we'll store it in a temp variable. We'll start pointing our head to the next of our current head, and we'll delete this node. So in this way, we are going to perform a dequeue operation on our queue using a linked list. I hope the things are clear, a bit more clear. You will get a little more clarity when we'll try to code this on our own. So yeah, this is a brief about how we can implement our queue using linked list. Now we'll move on to the code part. So first we'll try to understand the structure of our code, then we'll try to code, right? So what all things are required to proceed with the code of our queue using a linked list? So firstly, we need to create a node. So how this node will be created? We'll simply create a class node, and it will be similar to what we generally create in a linked list. We'll create public data members like t data. Why I'm taking t? Because again, it's a templated data. It can be anything. It can be int, it can be char, or it can be anything else. Next is we'll create a node of the type node star next, that will contain the address of our current node, of our next node. Now I'll create a constructor that will store the address, so that will help us initialize our data members. So we'll point this data to data, and currently, like, initializing next is equal to null. So this is how we'll create our class node for making our linked list. Like, node will have first data member, that is data. Like, this is our node that we want to create. It has two members. First is this will be data, and this will be next. So initializing it will point out this data to data. This is a pointer that is used to store the address of our current object. So this will be storing the address of our current node. This data will point to data that we are supplying, and next will point to null initially. So this is the initialization of the node that we want, and we will be creating different functions. So we'll create our class queue also. So when I say I create a class queue, what all different data members we can think of in a class queue? So as I've already mentioned, we have three data members. That is, I'll create a node of node head, I'll create a node tail, and I'll create int size. So these are three data members that we'll have in our queue class, and then we'll make our public functions. What all public functions that we have discussed? We'll create something known as, we'll create a constructor again to initialize different objects of our queue. We'll write int get size, that will give us the size of our queue. We'll write bool is empty. We'll check if our queue is empty or not. We'll write void enqueue, and we'll pass on one element of type t. We'll return front element, and we'll dequeue our element of the queue. So these are the functions that we're going to create. Now let's move on to the code to see how we code this particular functionality, right? So we are on the ID. We'll be starting to code our queue using linked list. So firstly, as I've already mentioned, we'll create our node. So we'll create a class node. So inside this class node, I'll have public data members. So which public data members I'll have? I'll have data. Along with that, I'll have next pointer that will point to the address of our next node. So as I've created t, that is a templated data, I'll need to specify, like, now we know how to create a template type name t, right? Along with that, we'll have a node p of data, and we'll initialize this data equals to data, and next will be initially pointing to null. So this is basically how we have created our node class. Now we'll create our class queue, and then we'll try to dry run it and see how this works. So we'll have a public function. So what is there in this public like we'll have three public data members. So first is node head. We'll also have node tail. I've explained why we need tail pointer, and we'll have int size that will have the size of our queue at any point of time. Now we'll create a public functions. Firstly, we'll create our constructor queue that will initialize different data members of our queue. So we'll point our head to null, we'll point our tail to null. Initially both of them are null, and size is equal to 0. This is something that we have to initialize in our constructor, because initially there's no element on our queue. Our head will also be pointing to null, our tail will also be pointing to null, and the size of the queue is going to be 0. We'll next create int get size function. Int get size will give us, we'll simply return size. Next, apart from that, what all things which all functions we have discussed. One was get size, we'll simply return the size. We'll check, we'll create is empty function. So is empty function will tell us whether our queue is empty or not. What we'll do in this case is we'll return size is equal to 0. If the size of our queue at any point is 0, then like we'll check on, like if this condition is true, that size equal to 0 is true, then we'll return true to our bool is empty function, and if it is false, then we'll simply return false bool is empty. Next, that is something very important that we have discussed also. It's enqueue. Yeah, it's enqueue function will pass on our element that we need to add in our queue. So what happens in this enqueue function is, like as I've already mentioned, what we'll be doing in this case is, let me just explain you a little more. Yeah, so in this enqueue function, we'll have firstly what we'll do is we'll create a new node with the data as element. This is something that we're going to do in our enqueue function. Next, what we'll do is, if our queue is empty, like in the beginning our queue is empty, then we'll simply point our head to new node and our tail also to new node. Whereas in other cases, we'll simply move on this head pointer, and we'll try to see how it goes and how we are able to write this enqueue operation, right? So let me just start writing in the code for this particular function. So what happens actually is, we'll create a new node, that is node t star new node, and inside this new node, like we'll initialize it dynamically. Right, what next I need to do is, tails next will be pointing to new node, and we'll make this tail equal to new node. These are the three steps, these are the steps that we were doing each time, and we'll do our size plus plus. But do you think it is all right? Are we missing the case? Yes, we are missing the case when head or tail both are null. So that means our queue is not yet formed. So for that case, we need to initialize our both head and tail to our new node, and things will work in that manner. Let's do that. So what we'll do is, we'll put this particular condition, we'll put this edge case. If at all our head is equal to null, then what we are going to do is, we are going to make our head is equal to new node, tail is also equal to new node, right? And this condition we can put in else, like if our head is not equal to null, then we'll move on to doing this particular operation. And in both the cases, we need to increase the size of our new node. So in this way, hopefully our enqueue operation will be working. Let's see how we will be writing our front function. So t front, it will be returning us the front element of our queue, that is the element that which is present at the top. Let's say this is our queue. We have three elements, 10, 20 and 30. So for front, it will simply return the data of the head. But do we need to check anything? Yes, we need to check if at all our queue is empty or not. If at all our queue is empty, then we can't access heads data and we'll move on to a segmentation error. So before just checking upon the heads data, I'll put this condition: if is empty, if our queue is empty, then we'll simply return, let's say, 0. Else, in all cases, we'll return our heads data. Right? I hope this is also clear. Next is dequeue function. So what happens in dequeue function is we need to remove the element which is present at the head node. So try thinking on what we will be doing in this particular cases. I'll try to show you with a help of an example, right? So make sure you check this example out. So what we are going to do in this case is we'll be having a dequeue operation. So what happens in a dequeue operation is, let's say we have this particular queue, 10, 20, 30 and null. So for dequeue operation, this head is to be removed. So when this head is to be removed, so we're discussing about the dequeue operation. Dequeue operation will have the return type as t because we'll return the element which we need to dequeue. So what happens in a dequeue operation is, let's say we have this particular queue with the first element as 10, then 20, then 30, and the last element 30 is pointing to the null. When we apply a dequeue operation, we'll need to return the element which is present at the front, that is element 10. So we need to return this 10. Along with that, we need to remove this 10 from our queue. So now consider a case, our head is pointing to this, our tail is pointing to this, and we have size as 3 currently. So what actually I want to do is, I will be returning heads data, right? And I'll be making this head to point to this 20 and then deleting this particular node temp. I'll make a temporary node and I'll store the data of the head, and I'll store the node head in the temporary data, and I'll make the head point to the next node. So in this way, I'll be able to remove this particular node from the queue. Along with that, we'll return the data of this node and we'll reduce the size by 1. The size will be 2. So let's try to code and see how we will be writing this particular part. So you can see that will be, firstly, we'll maintain an answer variable that will contain heads data. This is something that we are going to return at the end. So that's why I'm saving it in the priorly, because once we delete the node, we'll not have this data with us anymore. We'll write node t and we'll create a temporary variable in which will point to our current head. Then we'll make our head point to heads next. We'll delete the temporary node so that the data is free, the memory is free now, right? And we'll do size minus minus. At the end, what we need to return is, we need to return this answer. And I hope our dequeue operation is also done. Till then, let me just erase this, right? So now let's go on to the main part and try to see if our function, if our the code that we have written is running or not. What exactly I have to do is, I'll create my queue, let's say of integer variables. Let's name it as queue, and I'll perform certain enqueue operations. I'll do enqueue 10. So let's say I'm doing enqueue 20, enqueue 30, enqueue 40 and enqueue 50. And let's see different results. Like firstly, I want to have queue.front. Then I want to have queue.dequeue, cout queue.dequeue again, cout get size. So let's see what we are expecting in these results, and let me just go walk over through the code if everything is all right. Let me just change the header file. T node T data next. I think it is correct. We'll see if there is any compilation error or so. But like what exactly the output that we're expecting in this case is q.front will be giving us 10, then q.dequeue will be giving us 10 again, then q.dequeue will be giving us 20. Then we have already removed two elements from an array, the size will become 3. So the output that I'm expecting out of this is 10, 10, 20 and 3. Let's see and run if it's working all right. There is some more compilation error. It's basically the T. Okay, get size function. So the mistake that we were doing is like we were not able to we were not initializing these as pointers. Now we are initializing them as pointer, and we'll try to run. We'll see that we are getting the exact output that we were expecting, that is 10, 10, 20 and 3. I hope this code is clear to you, and do try to make sure that you write this code on your own, you try to dry run so that you can get a better understanding on how to implement a queue using a linked list. Next, we'll move on to how a queue STL works, that is standard template library. What all functions are there in standard template library, that we will not have to create all these functions again and again when we are performing different questions, different applications on queues. See you in another video. So now we've already seen how to implement a queue internally using an array as a linked list. So now I hope each and everything is clear to you and you have implemented it yourself as well. Now I'm going to talk about QSTL, that is a standard template library. Like it's basically a library for that stores all the functions that we have already made, so that we can use it as and when required without having the need to make all the functions again and again. So this standard template library contains a library of queue, that is we can include it using hash include queue. It has certain functions that are similar to what we have discussed using arrays. We have made using arrays, so we'll try to solve certain problems using QSTL going forward. So the functions that we have discussed earlier are like we have discussed enqueue operation. It was taking an element t. So in STL, corresponding to this enqueue function, we have push operation, that is void push t element. Then we have also discussed t front, that was giving us the front element of the queue. Similar to that, we have front element in QSTL. We have t dequeue in our previous methods, and in STL we have void pop. So it is basically used to pop an element from the queue. We have also discussed about int get size. So rather than int get size, here we have the function known as int size, and the last function is bool is empty, that we have discussed. Corresponding to this, here we have bool empty. So we'll try to see how all these functions are implemented using QSTL and how we can solve certain problems using QSTL. But let's just move on to the code part and then we'll discuss, right? So here, like first thing that we're going to do is we are going to add a queue class, a queue library, hash include queue. Now we'll simply, let's say, make a queue using STL, that is queue of integers queue, and we'll push the elements, that is, let's say I'm pushing 100. Similarly, along with 100, I'll push, let's say, 200, 300, 400, 500 and 600. So let's say I have pushed 6 elements in my queue, that is queue, and I am looking forward to output certain things, like that is queue dot front, that will give me the front element of the queue. I am doing then queue dot pop. This will remove the topmost element from the queue. I'm again doing queue dot front. That will again give the new front element of the queue after removing one. I want to get the size of the queue dot size, and I want to check if my queue is empty or not. So what output I'm expecting is, let's see, try to run and see if there's any error. So now you can see I have this particular output that is coming. I have 100, 200, 5 and 0. Let's see if this is true or not. So when I say it's 100, so initially the first element of our array is 100, so that's why we are getting the output corresponding to this as 100. Then we are making queue dot pop. So from our queue that was initially like this, I am popping the topmost element, frontmost element. Now 100 is removed. Now my head is pointing to this. Now I'm doing queue dot front. Again, the front element is 200. I'll be getting 200 corresponding to this. Then I'm doing queue dot size. What is the size? 1, 2, 3, 4 and 5. So the size comes out to be 5. Queue dot empty. Whether it's empty or not, I'll get 0 or 1. If it is 1, that means the queue is empty. If it is 0, that means the queue is not empty. So we are getting 0. That suggests that queue is not empty. So in this way QSTL works, and further discussion of queue we are going to do using different practice problems. So next we'll be discussing some important problems of queues that are very, very important from the point of view of interviews. So make sure you watch till then. So now, as we have discussed what a queue is, how to build a queue, what is QSTL, how to build it using arrays and linked list. Now moving upon to further practice problems, different problems that can be solved using queues. So picking up very basic question, very important question from the point of view of interviews, that is how you can implement a queue using stacks. So we are going to discuss this very important problem. We'll try to see how we can improve upon the efficiency of this program. We'll discuss one approach, then we'll discuss some more approaches. Let's say how we'll be solving this particular problem. Consider two stacks. Like, we'll try solving it using two stacks. We have stack S1 and we have stack S2. So this is our stack S1 and this is our stack S2. And consider that, like, you people are already familiar of what a queue is and what a stack is. Queue is basically, as I've already discussed in very detail, that queue is FIFO data structure and stack is a LIFO data structure. From LIFO I mean last in first out. For example, this is a stack. The element is entered from here and it leaves from here. The element which is entered at the last will be getting a priority to move out at the first. Whereas in queue what happens is, it's another way. We have front end, we have rear end. Elements are added from the rear end and elements are removed from the front end. So we have to implement this particular data structure using our stacks. Now let's say we have these two stacks S1 and S2. With the help of these two stacks S1 and S2, I'm going to implement my queue so that it has the same functionality of FIFO data structure. How we can convert this LIFO property into FIFO property using these stacks. Let's say I have these two stacks S1 and S2, and there is a certain algorithm or the steps that we are going to use for solving this particular problem. Let me just write down those steps once so that we can discuss upon them with an example, right? So the first step is moving elements from S1 to S2, then pushing element X to S1, then third step, moving elements again from S2 to S1. So these three steps can help us solve this particular problem, and they can help us convert our property of LIFO of stacks to our queue. So let's say we have I have to push, like, the first operation that I need to perform is I want to push 1. When I'm pushing 1, what is the first step that I should go through? Moving elements from S1 to S2. Now currently our S1 is empty, S2 is also empty, so there's no element in S1, so I'll have to move nothing to S2. Now pushing X to S1. So X is this element, like I'm pushing 1 to my first stack, so I'll simply add 1 to this stack. right? Done. First step is done, second step is done. Now moving elements from S2 to S1. Like, are there any elements present in S2? No, there are no elements present in S2, so I'll not move anything, and our push 1 is successful, right? Similarly, let me do a push 2. So when I'm doing a push 2, first step is moving elements from S1 to S2. So S1 I have 1, so I'll be moving this 1 from S1 to S2. That's done. Pushing X to S1, like now X is 2, I'll be pushing this 2 to my S1. That's done. Now moving elements from S2 to S1. Again, I'm moving the elements that are present in S2 to S1. So what I'll be doing is I'll be moving this 1 from S2 to S1, and we are done. These two operations we have performed. We have performed two push operations. Now all the functionalities that we have seen in a queue, are they being justified by this approach? Let me just let's just try upon one more push operation, and then we'll see how other functions are there. Like, I'm pushing 3. So the first step is moving elements from S1 to S2. So all the elements present in S1 will be moved to S2. Let me move them. So firstly 1 is moved. Now 1 is written here. Now after 1, 2 is moved. Now 2 is written here. Now pushing X to S1. This time X is 3. So I'll be pushing 3 in S1. Then again moving elements of S2 to S1. Moving elements of S2 again back to S1. So I'll be moving this 2 first. 2 is here. Now I'll be moving this 1. 1 is here. And we have successfully made this particular movement. And now let's see how it goes. So according to our queue property, if I'm pushing 1, 2, 3, so the elements in our queue should be something like this. Element 1, element 2, element 3. So the element which is pushed at the first, like, it is the front end, it is the rear end. Elements are added from here, moved from here. So this should be my actual queue. Let's see if this stack is actually solving my problem and it's helping me work out in a way that I want, right? So now different other properties of stack. Let's say if I want the top element of my queue. So to get the top element of my queue, that is the front element of the queue. So to get the front element of the queue, what I'll do is I'll simply do top. Like, this is top in stack. Let's say to get the front element of our queue, I'll simply need to do the top of S1. So if I do top of S1, I'll get 1. That's the front element, and that's done. If I want to perform a pop operation, so what I need to do is I'll simply need to pop from S1. If I'll pop from S1, 1 will be removed from this, and I'll get 1 as the output. Similarly, if I was to perform this on a queue, 1 will be removed from here and my head will move to 2. So front is also working, pop is also working, push we have seen, and all other functions will be performed in a similar manner. But now let's see what time complexity are we using while solving this particular approach. Let's say the time complexity is, because we have to, for each operation, we'll have to move the elements from one stack to another. So the time complexity that is taking it is O of n. Space complexity, what's the space complexity? We are using 2 stacks, let's say each of n elements. So the time complexity of both of them becomes n plus n, that is equal to O of 2n. Like, we can take it as O of n only. So in this case, the space complexity and the time complexity both are of the order of n. So this is something that we need to work upon, how we can improve upon this O of n approach to something efficient, like little more efficient than this. Let's see how we can do that. Like, this was the approach 1. Like, we'll move on to approach 2 and see how that approach can help us make our code more efficient. So when I say approach 2, again we have to perform 2 functions, that is push and pop, right? How we can improve upon the complexities of push and pop. The first thing is, again, what we'll be doing is we'll be taking 2 stacks again. This is stack S1. This is stack S2. So let's consider the push operation. I'll just need to push it simply in my stack. For example, I want to add push 1, push 2 and push 3. So for all the push operations, I'll simply push them in my stack 1, that is 1, 2 and 3. Now here in the case of pop, I need to do something else. Let's just write down what all steps that we are looking forward to perform, and then we'll see how we can explain it using different examples. So for pushing x, what I'll do is I'll simply add x to my s1. I'm simply adding my x to s1, like these are x's 1 2 3. And for pop, let's say I have a pop operation, I'll make a check if at all my s2 is not empty. If my s2 is not empty, what I'll do is I'll take a variable output. Let's say we are having a variable output. In this output, I'll simply put s2 dot top and I'll remove s2 if my s2 is not empty. Else, if my s2 is empty, what I need to do is I will move all the elements from s1 to s2 again and will get the top element of s2 as our output. So let's see how this is done. Like I've written a very non-familiar approach or non-familiar algorithm. So let's see how we can solve it using this. If you people are not able to see this, so else condition I'm writing here again. Else s1 elements of s1 will go to s2 and then will pop s2, and this element will be the popped one element, right? So now let's say push 1. If I'm pushing 1, pushing 2, pushing 3, simply pushes will be adding the elements to s1. When I'm popping, if let's say I call a pop operation after this, now what I see is if s2 is not empty, but in our case s2 is empty, so I'll not move into this if statement, I'll move into this else statement. So what this else statement says that all the elements from s1 should be moved to s2. Now I'm moving all the elements from s1 to s2. Let me just move all the elements from s1 to s2. It's 3, it's 2, and it's 1. So now I have 1 2 3 in my s2 stack, and I simply need to pop s2. So if I pop s2 from here, 1 will be removed, 1 will be removed, and the same would have happened if I have these 3 elements in my queue, that is 1 2 and 3. 1 would have been deleted on popping. I hope this much is clear. Great. Now second time again, let's say I am doing a pop. So if I'm again doing a pop operation, what do I mean to do by this? For pop operation, like I'm saying if s2 is not empty. Now this time s2 is not empty. What I'll do is I'll simply pop out the top element of s2, and by storing it in this variable output and returning this output, it can be anything. But now this time simply I'll return s2 stop, right? So this operation is performed in O of 1 time complexity. Push is also performed in O of 1 time complexity. This push is also performed in O of 1 time complexity. This is also performed in O of 1 time complexity. This push is performed, let's say, in O of n time complexity. Another push pop operation is performed in, like, 2 is also removed, 2 is also removed. Next is 3. Now again I'll see if s2 is empty or not. s2 is not empty. Again I'll simply pop out s2 stop. 3 will be removed, 3 will be removed, our stack becomes empty, and we have successfully made the functions push and pop for our queue using our stack. Again, for this pop also, the complexity will be O of 1. So like for most of the operations, let's say like for some operations in pop, there might be the complexity will be O of n, but for most of them, as s2 is not going to be empty in all the cases, it is O of 1. So we can say that amortized complexity in this case for push and pop operation is O of 1, big O of 1. So we have been able to successfully move from O of n complexity to O of 1 time complexity. Now let's see how we can solve this question, how we can solve this particular question using our code. So let's move on to the coding part. Now let's move on to the code part. Inside the code part, like we have a same question where we have to implement queue using 2 stacks. So what we are given is we are given to implement a queue using 2 stacks s1 and s2, and you have to push and pop. You have to create push and pop operations. As we have seen in our second approach, basically push is just we are pushing our element in stack S1. So I'll simply write S1 dot push and I'll mention the element that is X. But what we are doing in pop operation is, like I was checking, the first condition that we were checking is if S2 is not empty. If S2 is not empty, then what we were doing is we were simply let's say I take an input int output variable in which I'll be storing out my answer. I'll be putting out output is equal to S2 stop, right, and then S2 dot pop. So this I am doing, I am simply returning the element which is present at the top of the S2 if S2 is not empty. Now let's move on to else part. Let's say if our S2 is empty. So what we'll be doing in that case is we'll simply move all the elements from S1 to S2 while our S1 is not empty. While our S1 is not empty, what we'll do is we'll simply move all the elements from S1 to S2. So for moving all the elements from S1 to S2, I'll simply push on elements from S1 dot top, and side by side what I'll be doing is I'll be popping out elements from S1 dot pop, right? So all the elements from S1 will be moved to S2. Now I'll again make the same check. If at all our S2 is not empty, then I'll again do the same thing. Output will be equal to S2 stop and S2 dot pop. Else, if our S2 is empty, then what we'll do is we'll output -1 because there's no element that is left. So at the end what we'll do is we'll try to return output and see how it goes. So this is basically the approach that we have discussed. What we are doing in this approach is for push operation we are simply pushing in our element in stack S1. For pop operation we are checking in if our stack 2 is empty. If our stack 2 is not empty, then we are simply returning the top element of stack 2 and popping out that element. Else we are moving all the elements from S1 to S2 until and unless like stack 1 is empty, then we are simply returning the topmost element of stack S2. If there is no element in stack S2, we are outputting -1. This is the approach that I think should work. Let's just try to compile and run if there is any error. So yeah, we are getting the output for the given input. Let me try to submit and see if it goes well. Yes, we have successfully solved this particular problem, and yeah, that's done for this particular problem. Let's move on to our next problem. As now we have already discussed how to implement queue using stacks, so now there is another way around we'll be discussing in this problem. This is the second problem in which we'll be discussing about how to implement stacks using queue. So we'll see two variants, how we can implement stack using two queues and how we can implement stack using a single queue. So both the variants we are going to see, and these problems are basically made to be done so that you people are more familiar with the concepts of queues, so that you can implement them basic functionality of queues on your own. So when I say stack using two queues, let's take an example so that we can understand the approach, what exactly we are looking forward to. So stack using two queues. So let's say I have this q1 and I have this q2, and I want to push certain elements, so that what happens in a stack is, like, we have a stack of this particular form and we keep on adding elements from the rear end. Like, let's say I'm adding 1 2 3 4, and it's a lifo data structure. The element which is added at the last will be removed first. So 4 is added at the last and 4 will be removed first. So simply, let's say I want to push these 4 elements. Let's say push 4, push 3, push 2 and push 1 in my stack, right? Let's see how we can do this by using these two queues, Q1 and Q2. There are various steps that are involved in the process. Let's say I'm discussing about the steps. So the step 1 is insert the element in Q1. Next, what we'll do is we'll push the remaining elements of Q2 to Q1. And last step is we'll swap the elements of Q1 and Q2. So this is basically done for the push operation. Let's see how it works. Insert the element in Q1. The first step is insert the element. The first statement that I'm going to run is push 4. So 4 will be inserted here according to our algorithm. Now we'll push the remaining elements of Q2 to Q1. As Q2 is already empty, so we don't need to insert or move anything from one queue to another. We'll swap the elements of Q1 and Q2. Now third step is we'll be swapping the elements of Q1 and Q2. Q2 has no element, Q1 has one element. So after swapping, what it becomes is it goes something like this. 4 is here and Q1 is empty. R4 is done. The next element that we are going to do, we are going to push is 3. So what happens to 3 is insert the element in Q1. So I'll insert 3 here. Push the remaining elements of Q2 to Q1. So remaining elements of Q2 are 4 only. So I'll move this 4 to here and 4 will be removed from this queue. Next, swap the elements of Q1 and Q2. If I'll be swapping the elements of Q1 and Q2, both 3, 4 will be moving to Q2. So it will go something like this, right? Now I'm again doing push 2. What happens to 2? 2 goes here. I push the remaining elements of Q2 to Q1. I'll push 3 and 4 to Q1. Now what happens is I want to swap the elements of Q1 and Q2. Swapping the elements of Q1 and Q2, what will be there in Q2? It will be again 2, 3 and 4, and 2, 3, 4 will be removed from here respectively. Now see, our Q2 acts as our new stack. How Q2 acts as a new stack? Like let's say we are to push 4, 3, 2, 1 in our stack. So how will we be pushing them? We'll be pushing them in this form. 4 will be added here, 3 will be added here, 2 will be added here in this way. So the element which is added at the last, let's say we have added 2 at the last, it will be removed first. Now if we are to pop an element from the stack that we're implementing, so we'll simply do pop, and the pop function will remove the firstmost element or the frontmost element of the Q2, and it acts as our stack. So in this way we will be performing our stack operation using two queues, Q1 and Q2. Now if we are to perform the pop operation, we'll simply what we'll do is we'll check upon if our queue is empty or not. If it is empty, then we'll simply output let's say -1. If it is not empty, then we'll simply return the frontmost element of the Q2 to implement our stack. Now let's see this approach in the form of our code. So we are to implement stack using two queues. We have two functions, that is push and pop function respectively. So how will we writing the code for push and pop? It's the same thing that we have done. We have discussed the approach for push. The same thing that we are going to do. The three steps. The first step was we were to insert this element X into our queue Q1. So what I'll do is I'll push this element X in Q1. The next thing after this was to put all the remaining elements of Q2 to Q1. So to put all the remaining elements of Q2 to Q1, we'll run a loop until and unless Q2 is empty. What we are going to do is we are going to add the elements in Q1. What happens after that is we'll remove the elements from Q2.pop. The last thing was we were swapping the elements of Q1 and Q2, right? So I'll simply use a swap function, swap Q1 and Q2, and we are done. So this is how our pop function looks like. It's very, very simple. Now let's talk about the pop operation. Pop operation is also very simple. I'll just put a check if our queue is empty. We'll check upon if our Q2 is empty. Then we'll simply will not do anything. Let's maintain a variable int output. Like we'll put output is equal to -1 if our queue is empty. This is a check that we are putting. Else what we'll do is we'll in this particular output variable we'll put q2.front and then we'll do q2.pop. So in this way our output will be there. We'll return our output, and this is how our code for stack using 2 queues is written. Let's try to compile and run and see how it goes. Let me try to submit. So it's getting submitted. We have successfully solved the problem of making a stack using 2 queues, right? Now we have already seen that how we are implementing a stack using 2 queues, but what if we are asked to implement stack using just single queue? So what we'll do in this case is, let's just do second part, stack using one queue, and we are to implement our stack. Similarly, like we are implementing the function, let's say push 1, push 2, right? So what happens in this is, like let's say I'm pushing 1, the first element is added in our queue. Now the size of our queue becomes 1. What I'm supposed to do is I'm supposed to remove size minus 1 elements, remove, that is I'll pop these size minus 1 elements and push them again. So what will happen in this case is, like after this 1 is added, so size minus 1 is, like size is 1, so 1 minus 1 is 0, so no element is going to be removed, no 0 element is going to be removed and pushed again. Now I am pushing 2, so when I push 2, what I'm supposed to do is I will be removing size minus 1 element, that is now when I add 2 to my queue, the size becomes 2. Now size minus 1 elements, that is this one, is to be removed, is to be popped from this queue and is to be pushed again into this queue. That is, our queue will look something like this. 2 is here and 1 is added here, right? After this, let's say I am again pushing in my element 3. So when I'm pushing in my element 3, so what I'm supposed to do in this case is I'm supposed to push this element in my queue. I'm supposed to push 3 in my queue, and now the size becomes 3, so I'm supposed to move size minus 1, that is the previous 2 elements I'll remove, I'll pop and I'll push them again, so it becomes something like 2 and 1, right? So now what happens is, this queue, it looks exactly like how a stack will work. Stack was supposed to work like this. I am adding 1, then I am adding 2, then I am adding 3, so last in first out. 3 is added at the last, 3 will be removed at the first. Similarly, now the queue that we have got, the queue that we have implemented as a stack, if we perform a pop operation on this queue, what we'll get is, we'll get 3 as the output, right? If we perform top, that is the front element that we are getting, we will be getting the front element, that is the element which is at the topmost. So it acts similar to how a stack works, right? Let's just go through the code once on how we are going to implement this particular functionality in our code, right? So the same thing happens, like let me just open up my code editor. So what happens in this case is, like I'll not be using 2 queues but a single queue. Let's say I'm using q1. So what is the first step? I'll simply push the element x in my queue q1. Next thing is I'll calculate the size, int size, it's equal to q1 minus q1's size minus 1, right? After this, what we are going to check, until and unless this size is 0, all the size minus 1 is 0, what I'll do is I'll keep on pushing and keep on popping. So in the q1 only, I'll push q1 dot front, and side by side I am popping these elements. So this is the code that we are going to write for push. I think it is done. Pop operation will remain the same. Instead of q1 we are just using q2 we are just using q1, so q1 will be replaced everywhere, and I hope this should work. So we have seen that this is working. Stack using 2 queues have been successfully implemented. Now let's move on to our next problem.
Hi everyone, if you're liking this course, if you're liking the videos, if you're liking the type of questions that we are discussing, so
consider subscribing this channel, because we'll be bringing some more amazing content, some more amazing topics related to data structures, algorithms, related to system design, and more that can help you become a better software developer. So now we're going to talk about something known as a dequeue. Some people also call it as it's also named as dequue. Some people also call it as deq. It is implemented using a doubly ended linked list. You can say it is a generalized version of queue data structure that allows insertion and deletion at both ends. Like what was happening in general queue, like queue was something like this. We had this kind of structure, and we were able to add the elements from rear end, and elements were removed from the front end. But what is happening in a dequeue is everything remains the same. It's just that you can add the elements from the rear. You can also remove the elements from the rear. You can add the elements from front, and you can remove the elements from front. So there are different operations that we will be seeing in this dequeue operation, that is similar to what we have seen as pushback. This is used to push an element from the back. There is something known as push front, used to push the element at the front. Let's say 2, let's say 3. We are pushing 2 from the back and 3 from the front. Now let's say I am push back 1, so 1 will be added here. Now pop back and pop front. So pop back and pop back will remove this 1, pop front will remove this 3. We'll have only 2 left. So we'll see the implementation a little bit of how dequeue works actually, and different other functions. Like if you want to output some of the numbers which are elements which are there in this dequeue, we'll be using the functions known as front function. Similar to that, we'll be using back function. There's something known as add function, like the element which is present at second location. So the add suggests second location. So we'll see how it is actually implemented in the code. And yeah, so we are there on our ID. We'll include the header file hash include dequeue, and we'll create our own dequeue. Let's say integer variables and dequeue. I'll add dequeue dot pushback, let's say 3. Let me just copy paste this. Pushback 2, pushback 1. Let's also try dequeue dot pushback push front 5, dequeue dot push front 6. And now let's see if we are getting the correct output. Dequeue dot front. So what I'll be getting at the front, cout dequeue dot add 3, the number which is present at the third index. Cout dequeue dot back. Let's see how these actually work, then we'll see if we are doing the correct thing or not, right? Yeah, so we have got the output as 6, 2 and 1. Let's see how this output 6, 2 and 1 came. Like we were pushing, like the first element that we pushed was 3, 2, 1, 5 and 6, right? So we were getting something like 3, we did a pushback 2, 1, then we push front 5, then we push front 6. So this was the queue that was made. So now when we were accessing the front element, so we should get 6. When we are getting the back element, we should get 1. And when we want add 3, the element which is present at the third location. So let's see if we are getting the correct answer. So we are getting the answer as 6, 2 and 1. So you can see the number which is present at the front is 6, correct. Number which is present at third location, that this is 0, 1, 2, 3. So output is 2, that's correct. And the number which is present at the back, that is 1, it's also correct. So I hope you are clear with the basic functions of dequeue. Now we'll try to solve some problems that has an application of dequeue, and the problems can be solved in a much easier way. So we'll see the problems related to dequeue.
So let me read out a question for all of you. Now we know the concept of dequeue. So the question goes something like this. So basically I'll be reading out the question. I'll try to explain you what the question suggests. So you are given an array of integers, let's say nums, and there's a sliding window of size k, which is moving from very left to of the array to the very right. You can only see k numbers in the window each time the sliding window moves right by one position. Let's say, what is the question saying? The question's name goes like this. It is known as sliding window maximum. You'll find this question on lead code in the harder level. It's lead code hard question. So the question goes something like, let me explain the question with the help of an example. You have an array named as nums. Inside this array you have, let's say, numbers like 1, 3. I'm taking the same example as that given at lead code so as that you can understand it better. 7. So this is the value of nums, and you are given a value of k equals to 3. So you have to give me an output array that should be something like 3, 3, 5, 5, 6 and 7. So the question goes something like this. What exactly you have to do is, like, this is the array. Inside this array there is a value of k given. You have to check all the sub arrays starting from the first element of the array, and check for all the sub arrays of size k, which is the maximum element. Let's say you have this particular array 1, 3, minus 1, minus 3, 5, 3, 6 and 7. So the first sub array of size 3 is this. So which number comes out to be the maximum in this is, it's 3. So we get the answer as 3. Now the second subarray starts from here. So this is the second subarray. The maximum element among all of them is 3 again. So for this is the third subarray. Maximum element among them is 5. Next, this is the next subarray. It starts from this minus 3. The maximum element among them is 5 again. Now this is the new subarray. The maximum element among them is 6. Now again the maximum element among them is 7. So our output looks something like this, and this is exactly what we have to do in this particular question. So we'll start from 0th position of our array, and we'll go on till the 5th location of our array, like 0, 1, 2, 3, 4, 5, 5th location of our array, and we'll be done. So this is basically what we want to do in this particular question. So let's say this question comes up to you in an interview. So the first approach that you might think of in an interview is the normal brute force approach. So let's try and see how the brute force approach will work in this particular case. So what exactly you have to do is, you have to do nothing. You'll have to start from the 0th index. You'll have to go till this 5th index, and you have to run a for loop. You'll go from this, you'll go until 5th index. Then inside this you will be checking each subarray, like subarray starting from 0th to I plus k minus 1. So I plus k minus 1, that means the subarray of size k, and inside them you will have to find the maximum number. So the very simple code for this in brute force would be for loop that will be running from 0th location to 5th location for this particular case, and inside that you'll have to go from I to I plus k minus 1. So why I'm saying I plus k minus 1, what does that say? Let's say take the value of I equal to 0. For I equal to 0, it goes from 0 to 0 plus k is 3 minus 1. So it goes from 0 to 2. That is, our first subarray is from 0 to 2. Let's say second subarray, it starts from 1 to 1 plus 3 minus 1. So it goes on like 4 minus 1, it's equal to 3. So our second subarray goes from index 1 to index 3. So inside this we'll find out, we'll calculate our maximum of array of j, or the maximum. So whichsoever element inside that subarray is the maximum, will be getting as the output, and our code will be done. Let's analyze what would be the time complexity in this case. So the time complexity in this case would be like firstly we are running a loop from 0 to fifth location, that is all the elements. So it will be O of n into what is this, we are again running a loop for each of the subarray, that is for k elements of the subarray. So the overall complexity comes out to be O of n into k. That's something that we don't want. It kinds of look like quadratic, hence we need to think upon an efficient solution. So what helps us in this particular state is the data structure that we have discussed recently. Which data structure we have discussed? We have discussed about dequeues, right? So what exactly we'll do is we'll try maintaining a dequeue so that it can so that we can solve this particular question. Like, let's see the approach of a dequeue on how we'll be approaching this particular question. So again, I'll be writing upon the question exactly what the question says. We'll be having the same array, that is 1, 3, minus 1. It was minus 3, I guess. Yeah, minus 3, 5, 3, 6 and 7. So this was the array that was given to us. We'll try to run our approach of dequeue on this particular array, and we'll try to see how we can solve this question better, right? This is the array. These are the array indexes, and we are given the value of k equals to 3. So what exactly we have to do is we'll have to maintain a dequeue. Dequeue, as you people know now, like it's a new form of queue in which we can push at the front, pop from the front, push at the back, pop from the back. So all these 4 operations are possible. It's implemented using a doubly ended queue. I have also shown you how a dequeue works in an STL. So now we'll maintain a dequeue. Let's say I'm maintaining a dequeue. I have this kind of a dequeue, right? So the thing, like basic intuition behind this is like we'll have to maintain a decreasing order of elements. What I mean to say by decreasing order of elements is like you'll have to start calculating from the very first of the array. So we'll go and see for this particular array, like we have the first subarray starting from 0 and it ends at 2, right? So out of this particular array, let's go on to the first index. So first index is 0th index and we have the element as 1. Now as it's the first index, our dequeue is empty. What we'll do is we'll simply add the index of our first element in the dequeue, right? And we'll try if there is any element that is before this and are they maintaining a decreasing order. Like here we'll see if it is maintaining a decreasing order. So what I'll do is I'll check for 1. So there's no element, so I'll put 1 in this decreasing array and see how it goes, right? Subsequently, like that's done. Now we iterate. Well, we will move on to the next element of the array. The next element of the array is 3. The index on which 3 is present is 1. So we'll add 1 here, but before adding 1 here, I'll see what is the value of the element present at 1. So the value of element present at 1 is 3. So if I add 3 in my array, will it be in decreasing order? No, it will not be in decreasing order. If I'll add this, so 3 is anyways bigger than 1, so this doesn't go in the correct way. Hence it will not matter whether this 1 is there in my decreasing decreasing array or not. So I can remove this 1, I can remove this 0, because anyways, like if this is my sub array, so if I have an element which is bigger than 1, so no matter how much I can do, this 1 is not going to matter at all. Matlab, is array mein we'll have, once we have 3, so this 1 has no importance at all when we consider the maximum element that is present in the array. So we'll remove this 0, right, and we'll add this 1 in our array. So now 1 is the element. Now we have removed this 1. We have 3 as the first element of our decreasing sequence, right? That's fine, perfectly fine. Now we move on to the next element. The next element is -1. We'll check in our decreasing sequence whether -1 goes in the decreasing sequence or not. Yes, -1 perfectly goes in the decreasing sequence. -1 is lesser than 3, hence if we put -1 here, our decreasing sequence is maintained. Now we'll check upon, now we can, like if decreasing sequence is maintained, we'll put on the index of this in our dequeue, and it goes something like this. Now a very important point to note at this point is, now our first subarray is over. Like as soon as we reach the second index, our first subarray is over. Now we need to have an output array. Like this is the array that will be storing our output, and how we'll be calculating that output, we'll see throughout the process. Right now, as soon as we reach the first subarray, like the first subarray is over, now what we'll do is we'll check upon what is the element at the front of this particular dequeue. The element which is present, the index which is present at the front of this dequeue, and the element corresponding to that particular index, will put it in our output array. So here the index that is present at the front of our dequeue is 1 and the corresponding element is 3. So we'll put 3 in our output array, and that's done. Right now we'll go on and go on and check for our next array element. So for next array element, we see when we move from -1 to -3, we'll see if -3 goes with this decreasing sequence. Yes, -3 goes on with this decreasing sequence. If we'll put -3 here, again a decreasing sequence is maintained. If a decreasing sequence is maintained, we'll put the index of -3 in our queue without doing anything, and we are done. Now as soon as we reach 3, right, as soon as we reach the third index, we have one more subarray completed. Earlier we traversed upon first subarray. This is the first subarray. Now second subarray is also done, and if a subarray is completed, what we'll have to do is we'll look again towards the front of our dequeue and see if there is what element is present, or what index is present. We'll write the element corresponding to that particular index in our output. So now again 1 is present at the front of the dequeue. Which element is there at the first index? 3 is present at the first index. We'll put 3 in our output array. Clear till here? I hope this much is clear to all. Next thing that we are going to do is we'll move on to the further array elements. When we move on to the further array elements, like we have 2 subarrays completed. After 3, we'll move on to 5. Now tell me one thing. Once we move on to the third subarray, that is this particular subarray. So the first thing that is very important thing is, now we have crossed this, this element is not going to come in any subarray. We have crossed this element. Now after the second subarray is over, we have crossed this element also. Now this subarray element is not going to come in any further subarray. So if this happens, like this is basically the element which is going out of bounds as soon as we move to our new subarray. So now this is of no value, no significance to us, so we can simply remove this element from our decreasing sequence also, and from our dequeue also. Now we have moved upon to this, and we have removed that element from our decreasing sequence. Right now we have an element 5. Now if we put 5 here, do you think our decreasing sequence is maintained? No, the decreasing sequence is not maintained, so we'll not put 5 here. Instead what we'll do is I'll not put 5 here. I will now I'll check upon in my dequeue whether putting 5 is alright. No, 5 will not help us maintain this decreasing sequence. Rather than that, we'll check upon, now in this particular array, like -3 will be of no significance once 5 comes up. So we'll compare this -3 with 5, as they are not able to maintain that decreasing order. So we'll remove this -3 and we'll remove this third index from our array. Again we'll check with -1. -1 is also smaller than 5. We'll remove the index also, right? So, and we'll put this index in our array, that is 4. Now 5 comes here. We'll start from the again, we'll start our decreasing sequence once again. 5 is the single element that is present in our decreasing sequence, and 4 is the corresponding index to 5. Now what happens is, now our third subarray is completed. We'll again look forward to what is the index present in our dequeue, and we'll put the corresponding element in our output array. The corresponding element in our output array goes like 5. So we'll have 5 in this output array, and we'll move forward. Right now the next subarray that we are going to see is this subarray. Right now we'll see if how it goes, like whether like the new array element that we have is at fifth index and the element is 3. Now if we put 3, are they maintaining a decreasing sequence? Yes, they're maintaining a decreasing sequence. If they're maintaining a decreasing sequence, what we do is we put that array index into our dequeue. So 5 goes here, and now we have one more subarray completed. What we do once the subarray is completed, we'll look forward to the front of our dequeue. The index corresponding to the front of dequeue is 4, so we'll put the element corresponding to 4 in our output, and that's done. Right now what happens is we'll check upon for another subarray. This subarray this time has sixth element. Now once again, is 6 will 6 help us maintain a decreasing sequence? No. Because why? Because 6 is, first of all, 6 is greater than 5 also, greater than 3 also. We'll compare 6 with 3. As 6 is greater than 3, we'll remove 3 from our queue. We'll remove this 5 from our queue also, because 3 was the element that is present at the 5th index. We'll compare 5 and 6. Again we'll remove 5. We'll remove the 4th index corresponding to this also, and we'll put 6 in our queue, dequeue, and we'll again start this decreasing sequence from 6. Right now again our new subarray is completed. We'll look forward to the front of the dequeue. The index present is 6, the element corresponding to 6 is 6, and we have 6 as the output. Now the last subarray for this particular example is this. What happens is, like, we'll see 6 is there. There's the new array element we have is 7. We'll check if 6 and 7 maintain a decreasing sequence. No, they don't maintain a decreasing sequence. We'll remove 6 from here, we'll remove 6 from here, and we'll add 7, and 7th index is added here. Now we'll again, our new subarray is completed. We'll again check from the front of the dequeue whether this goes with the whether this our subarray is completed or not. Now we'll look forward to, from the front of the dequeue, we have this index 7, and the element corresponding to index 7 is 7, so we have 7 at this particular output. So now we are done with this particular question, we are done with this particular example, and we have the output array that is giving us the correct output. So now think on what would be the time complexity in this case. So the time complexity in this case would be O of n plus O of n. We can say that it's close to O of n. Why it is O of n? Because like we are doing two things. As soon as we move to the new subarray, we are removing an element which is out of bound. So it goes on for O of n time complexity, and we are comparing that element with the previous element, and we are correspondingly adding that element to the queue or not. So it also causes O of n time complexity. So overall, if we see, the time complexity comes out to be O of n, which is far better than what we have seen in our brute force approach, right? So this was all about the approach that helped us solve this problem using dequeue. Now let's move on to the coding part and see if we can submit this problem on LeetCode.
So now you can see the same question we have on LeetCode. The question is by the name of sliding window maximum. It's in the hard level. So what we are given is, we are given a vector nums, that's the input array, and we are given a value of k, that is the length of our sliding window, like that's the length of our window. Now what we did in this particular question was, our efficient approach was, we made a dequeue. So of type integer, let's name it as let's say deq. This is the name of our dequeue. We'll also maintain a vector that will contain our output. Let's say we'll name it as vector output, right? So what we have done in this case is, we'll iterate from for int I equals to 0 to I less than nums dot size, and I plus plus will iterate. After that, what we are going to do is, we are going to put a check upon the out of bound index. Once we are moving from one subarray to the another subarray, we were checking if that particular element is there in a new subarray or not, like whether the index that is present in the dequeue is there or not. If that is of no significance, we'll simply remove that element from our dequeue. So what happens is, we'll check if at all our dequeue is not empty, because like if it is empty, so we can't remove any element from the dequeue. That's obvious check. it will give a segmentation error if we'll not put this particular condition. And we'll check if dequeue's front is equal to I minus k. Why am I writing this I minus k is because let's say you have this particular like this is the array that we have, and like let's say I'm suppose at this particular condition position I, before this there are certain k elements, and this element would be I minus kth element. So we'll check if this is the element which is present at the front. If it is so, we'll remove this, right? So this, if this is I, this will be I minus k. So that's why we are checking if this goes like this. What we'll do is we'll simply do a dequeue dot pop front, and that's done. So this is the condition basically that is used to check if our sub array is going out of bounds, right? Now again there is a second condition that we are checking to compare our elements whether they are maintaining a decreasing order or not. So we'll again check while our dequeue is empty, until and unless our dequeue is empty, and nums of dequeue dot back, the last element will check if at all it is less than or equal to nums of I. So what we are going to do is we are going to dequeue dot pop back, that is we are going to remove the element from the back of our dequeue, right? That's done. This is the second condition that we have written. This is basically we are checking that comparing the elements, right, if they are maintaining a decreasing order or not. The next thing that we are going to do is dequeue dot push back I, we'll push back the index if both the conditions are not met. Push back I, right? And at the end we will check if at all, like this is the case, like finally we are putting that element which is present at the front of our dequeue once our sub array is complete. So if I is greater than equal to k minus 1, that is our sub array is complete. So what I'm going to do is in our output vector we'll push back, what will push back, will push back nums of the front element that is present, will simply push back the element present at the index dequeue dot front. ठीक है जी, तो I hope this is should be clear, and what will return will simply return output. I hope this should be okay. Let me just see if there is any error. There might be. I'll try to include this class hash include dequeue. If there is anything else, let's check it once again. I think we are good to go. Let's try to run this, and we are getting the correct answer. Our output is this, expected is this. Let's submit. On submitting, we are getting that this question has been submitted successfully, and that's done. So finally our question is accepted, and now let's move on to another such problem that can be solved using a dequeue.
So let's discuss another question. Another question that we're going to discuss is basically about interleaving the first half of the queue with the second half. So the question goes something like, although the question seems to be really simple, but there are some operations. Majorly, you'll have to be very good at push and pop operations so as to be able to solve this particular problem. So you will be given a queue of integers. So this is the input. Queue of integers you will be given of even length. Let me read out the question. And you have to rearrange the elements by interleaving the first half of the queue with the second half. You have to rearrange by interleaving first half and second half. Also, there is one condition given, that is use only one auxiliary stack. This is the condition that is given. This is very, very important. So what do I mean to say by this question is, let's take an input. Like this is the input. You have an input 1, 2, 3, and 4. So the output that you will be requiring from this particular question is 1, 3,
2, 4. So how you'll get this output from this particular input is it goes something like, let's say we have this particular, like this is the queue you will be given as input 1, 2, 3, and 4. You divide this queue into two different parts and then take one element from the first queue and take second element from the second queue. So it goes like first element from the first queue is 1, first element from the second queue is 3, first element from the second element from the first queue is 2, next is 4. So you get an output similar to this, right? But there's no possibility that we can divide the queue into two different parts and then take the front portion or the front of both the parts of the queues. So and also we can't use two queues. If we were given a chance to use two queues, what we would have done is we would have created Q1, we would have created Q2. I would have pushed the first two elements here, next two elements here, and I would have done it like one first element like popped from the first queue, then first element popped from the second queue, then second element popped from the first queue, then second element popped from the second queue, and I would have got the answer. But we are not allowed to do this. We are allowed only one auxiliary stack. So what we need to do is we need to go something like this. Let's discuss with that particular example only, then we'll generalize the steps that we have taken while solving this particular problem, right? So we have this particular queue, we are given this queue. Inside this queue we have 1, 2, 3, and 4. So and you can take one stack as per your choice. This is the stack I have taken, right? So initially what you need to do is you need to push the first half of the elements of the queue to stack. So pushing first half of the element of the queue to stack, that means uh, I will be removing this from here, and it will go into the stack like this. Let's say I have the stack named as S. What happens next is you have to enqueue back the stack elements. So that these elements are to be enqueued back. So the queue becomes something like this. In this next step, it becomes 3, 4. If I pop this 2 from the stack and add it to the queue, it will go something like this. And then I'll add 1, right? Now my stack again becomes empty. Next step is I will be dequeuing the first half elements of the queue and enqueue them back. So these two elements, first half of the elements, I'll dequeue and I'll enqueue them back. So my queue becomes again something like this. So if I'll dequeue this 3, it will move back, it will be added here. 4, it will move back, it will be added here, and I'll get something of this sort, right? Now again, what I'm supposed to do is I'm supposed to uh, pop back first two elements of the queue and push them into the stack. Now my stack becomes 2, 1, and my queue becomes 3 and 4. Now you can see it's very easy for us to interleave. Now once we are into this condition, we can interleave both of them. What I mean to say by interleave is I'll take one element from the stack and I'll take one element from the queue and I'll simply print. So inside my queue, what I'll do is I will take one element from the stack, one element from the queue, one element from the stack, one element from the queue, and we are done. We get this as our output. So if you have to generalize the steps that we have taken, we can generalize the steps as like we have taken these particular steps. The first thing that we did was we have pushed the first half of the elements of the queue to stack. Second thing is we have enqueued back the stack elements. Next is we have dequeued the first half elements of the queue and enqueued them back. Next is again we push the first half elements to stack, and the last step is we interleave, right? So this was the approach that we followed. Now let's move on to the code and see how the code functions. So now you can see we have written the code for that particular question. What exactly was given is like I have made my own queue by the name of queue int queue. I have pushed four numbers 1, 2, 3, and 4. Like I'm taking the same example that was given that we have discussed initially. Now calculating the size of this particular queue by queue dot size, then calculating half size, that is n by 2. You can just do n by 2 in the question itself. That doesn't make any difference. I have initialized one stack, that is the auxiliary stack that we're going to use. The first step. So the first step basically was to push the first half of the elements of the queue into stack. So first half of the element, like I'm running a loop till half of the size of the queue. Then we are pushing those half elements in the stack, and simultaneously those elements are popped from the queue. Next step was enqueue back the stack elements. Now those until the stack is empty, I'm enqueuing back those stack elements to the same queue. Third step was dequeue the first half elements of the queue and enqueue them back. So I am dequeuing the first half of the elements, like queue front is removed and queue and it's popped. It's added back, pushed back to the queue, and it's popped back. And the next step is pushing the first half elements to the stack. Now again, those first half elements were pushed to the stack. Finally, this step is basically an interleaving step in which I am taking one element from the queue and pushing it of taking one element from the stack and pushing it into the queue, then popping that element from the stack, also pushing one element, take at the same time taking one element out of the queue from the front and pushing it from the back, and again popping that element until and unless this stack is empty. After that, this loop is just to print the queue elements that we have at the end. So let's see what goes with this particular code. Like if I'll run this code, I'm getting the output as 1, 3, 2, and 4. Let's try with some more examples. Let's say I have till 10. If we have this code running till 10, let's see how the output changes, right? So I'm trying to run this. So you can see we have again 1, then 1 to 5 will be separated and 6 to 10 will be separated. 1, then 6, then 2, then 7, then 3, then 8. So we're getting the correct output once again. So this code, I hope this is clear to you. And now let's move on to the next question. Hi everyone, so now we're going to discuss a very interesting problem. So the problem says that the title of this problem is distance of a nearest cell having 1 in binary matrix. So when we say binary matrix, so binary matrix is a matrix that is containing only 0 or 1 as its elements. So the question statement is something like, let me read out the question for you. So it says that given a binary grid means you are given a matrix, find the distance of the nearest one in the grid for each cell. So for each cell, you'll have to find the distance of the nearest one. The distance is calculated as I1 minus I2, or the index of that particular point, difference of the index of that particular point from the position at which 1 is present, where I and J are the row numbers and column numbers of the current cell, and I2 and J2 are the row and column number of the nearest cell having the value. So what I mean to say by this particular statement is, let's say you are given an input. Your input is something like, you have an input like 0, 1, 1 and 0. Again, you have 1, 1, 0, 0, 0, 0, 1 and 1. And you're supposed to get an output of this particular form. So the output goes something like 1, 0, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0. So this is the expected output out of us, and this is the given input. So how we reach from this to this is, let's say we take this element which is present at 0, 0 location. So from this 0, 0 location, what we can see is the nearest cell which is having 1. So the nearest one to this is at what particular distance? So it is at a distance of 1. So we'll replace this by 1, right? So now from this one, what is the nearest one? So this one is already at its own position. So the distance from this one to one is 0 only. So we'll update this to 0. Again, this is 1. So we'll update it to 0. From this 0, if we'll go to this direction, we'll find the nearest one is at a distance of 1. So we'll update it as 1. We'll check for this. 1 is already at its position, we'll mark 0. 1 is already at its position, we'll mark 0. For this particular 0, we can either go to this side or go to this side or go to this side, and we'll get 1 as the output. For this 0, we'll see the distance of this one, we'll get 1 as the output. For this 0, we'll see the distance of this one, we'll get 1 as the output. For this 0 also, we'll see this one, we'll get 1 as the output. For this 1, it's already there, so we'll mark it as 0. 1 is already at its position, so we'll mark it at 0. So this is how this particular question is there. Let me take one more example so that it becomes a little more clearer to you. Let's say you have this particular grid 101, 110, and 100. So now if I want to have an output matrix, so how will that look like? So for this one is at its own location, so we'll have 0 as the output. For this 0, like this one is at first one distance, this one is at one distance, this one is at one distance. So output will be 1. For this one, it will again be 0. For this one, it will again be 0. For this one, it will again be 0. For this 0, it will be 1. Like 1 is at the nearest distance. If you update as 1, for this one, it will be again 0. For this 0, either it can be this one or it can be this one. Both are at the distance of 1. So we'll update it as 1. For this 0, either it can be this one, it is taking 2 steps. So the distance is 2 in this case. Or it can be this 0 and this one. Again, it is 2. So the minimum distance nearest cell that is having 1 is at a distance 2. So we'll update this with 2. So basically, this is something that the question says, and how we are going to solve this using Q is really something very, very interesting, right? So what we'll do is, rather than just thinking upon from a point of view that we'll start from zeros, let me pick up all the ones that are given in that particular question. Let's take one more example. So let's say in this example, you are given a grid of this form: 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0. So for this particular grid, let's say we'll take all the ones that are present in the grid and we'll calculate the minimum distance which is present for a particular 0. Let's say for this particular one, if I want to reach this 0, so I can reach it in 2 steps. Also from this one, if I'm reaching out to all the zeros, I can reach it by 4 steps. So from 2 and 4, the number which is coming out to be minimum, I'll put it at this place. So this place will contain 2, right? So this is something like, this is the intuition that we are going to use behind solving this particular problem. So you can think of on a similar basis, on a similar approach on how we'll solve this particular problem. Let me just take one more example and see how we are making the use of our queues, right? So the question says something like, you are given this example, let's say 101, we have 110 and 100. So the first thing is, you will have to maintain a queue. So this queue will be holding the indexes of all ones initially, right? So it will be holding the indexes of all the ones initially. So this one, like let's say this is a queue and it is having the first, like this index is 0 comma 0, this is 0 comma 1, this is 0 comma 2, this is 1 comma 0, 1 comma 1, 1 comma 2, this is 2 comma 0, 2 comma 1, and this is 2 comma 2. So all the one indexes, like I'll put 0 comma 0 into my queue, I'll put 0 comma 2 into my queue, I'll put 1 comma 0 into my queue, again I'll put 1 comma 1 into my queue, we'll put 2 comma 0 into my queue, and I am done. So now for each of these ones, what I'll do is I'll make them 0 already. Like I'll make one answer grid. This is my answer grid, and inside this answer grid, all these positions where 1 is present, so they will be marked as 0. So we'll have 0 here, 0 here, 0 here, 0 here, 0 here, right? And rest other places I'll mark them as by int max. So rest other places will be marked by int max. This will also be marked by int max. This will also be marked by int max. This will also be marked by int max. So now what I'm supposed to do is I'll go for each of the location that is present in the queue. That is the initial position of all the ones. So for this particular position, in the queue, I will see, like I'll go on to 0 comma 0 position, like this is the first position that I'm looking forward to, and I will see, I'll try to explore then all the nearest possible position. So from this 0, if I will be moving to this position, like that is not 0, any non-zero position that I'm moving into, so I will check and see that it is at a distance, like we'll add one distance of one if we move from this to this. So we'll see if this int max, like the number that is present at this particular location, is this smaller or is this greater than this new distance. So we'll compare this one with int max. So as I can see, this int max is greater than this one. So as it is minimum, so we'll replace this int max by 1, right? As soon as this is done, what I will do is I'll remove this 0 comma 0 from my queue and I'll put the index of the new updated element in the queue. So this new index is 0 comma 1. I'll put it in the queue, right? Now we'll move on to the second index from the queue. It is 0 comma 2. Like this is 0 comma 2. From this 0 comma 2, like this is the position. I can move to this location also. I can move to this location also. Moving here, I will add the distance of 1. So I'll compare this one with already present one. Now 1, is it greater less than 1? No, this condition is false. We'll not do anything for this particular case. We'll check for this thing. Again, it is adding 1. So 1 is lesser than int max. So what I'll do is, again, I'll replace this int max with 1 and I'll add the index of this to my queue. So the index is 1 comma 2. I'll add 1 comma 2 to my queue and I'll remove 0 comma 2. Now I'll check for 1 comma 0. When I'm checking for 1 comma 0, like this is the position, I'll go to the nearest non-zero positions. So the nearest non-zero position is like this is also 0, this is also 0, this is also 0. So I'll not do anything, I'll simply remove it from the queue. Now I'll again check for 1 comma 1. For this particular position, I can go to this non-zero location, I can go to this non-zero location. For going to this non-zero location, I'm adding 1. So if I'm adding 1, I'll compare with the already present one. Since 1 is less than 1, this statement is not true. I'll not do anything for this case. For this particular case, what I'll do is I'll check if, like again I'm adding a distance of 1. I'll check if 1 is less than int max. Yes, 1 is less than int max, so I'll update this with 1. I'll remove this index and I'll add this particular index in my queue. This is 2 comma 1. Right, I hope the things are getting pretty clearer by what I'm trying to say. Then next index is 2 comma 0, so this is 2 comma 0. I'll go and check upwards. No, I'll go and check sideways. I'm again adding 1, but 1 is already present, so we'll compare 1 and 1. It is not lesser than 1, so we'll not do anything. We'll simply remove 2 comma 0. Then comes 1 comma 0 comma 1. So we'll go on to 0 comma 1, like this is the location we'll go on to, and we'll see if like what is the nearest non-zero number. Like if I move from this one to nearest non-zero, like this is also 0, this is also 0, this is also 0, so I'll not do anything. I'll simply remove this from my index. Now I'm going to 1 comma 2. So from this 1 comma 2, I'll see which is the nearest non-zero number. The nearest non-zero number is like this is the nearest non-zero number, and going from this to this number, I'll add 1. So 1 plus 1, I will see 2. So 2 I'll compare with this int max. So 2 is definitely less than this int max. So I'm supposed to replace this int max by 2 and add the index 2 comma 2 in this queue and remove 1 comma 2 from here. Then 2 comma 1, I'll compare this 2 comma 1 from here also. If I'll compare this 1 and add 1, so it will again be 2. 2 less than 2, which is false. So I don't need to do anything. I'll simply remove 2 comma 1 from my queue. Now 2 comma 2, I'm already present at 2 comma 2, and which is the nearest non-zero number, like 1 and 1. So going there, like from 2, if I go to there, there will be the number 3, but 3 is greater than 1, so I'll not replace them. I'll replace it with I'll not do anything. Again, I'll remove 2 comma 2, and in this way we will be getting the answer of the form 0 1 0 0 0 1 0 1 2, and that is something that we require as the output. This might look a little trickier. The question is a little tricky, but you need to understand what exactly we are going to do. I'll just try to reiterate through what all things we have done. This is basically the classic example of BFS. This is known as breadth first search, and this can be implemented using arrays, oh sorry, queues. So we have implement, we'll try to see how the code works, but before that, just I'll take you through the code on how the code part works. So input, we are given something like this, and we are expected to have an output of this. So how this output is calculated, we'll go and check for each of the non one digits. Like we'll go for all the zeros in this binary matrix, and we'll see which is the nearest one, and we'll calculate the distance of that nearest one and put it at that place. For this particular 0, the nearest one is present at first location, so I'll put the distance as 1. For this particular, like for all the ones, they're already at their own position, so the nearest distance from 1 to 1 is 0. For all the ones, we'll have 0 as the output. For this particular one, again it is 0. For this 0, this is the nearest one, so I'll get the output as 1. For this 0, uh, I'll again, like, this is done. For this one it's again 0, for this one it's again 0, for this 0 I can take it from this also, for this also, from this also, any one, answer is going to be 1. For this 0 I will take from this, it is 1. I'll take for this 0, answer is coming out to be 1. From this, like, 1 is the minimum distance between them. For this 0, again 1 is the minimum distance. For this one, it is 0. For this one it is 0, and we'll get the answer. So this is the approach, this is the question that we had. So what we are trying to do is, the approach goes something like this. We'll maintain a queue and we'll put the indexes of all the ones in that queue for the first time, right? Then all the zeros that are present. So we'll put int max in place of those zeros. And what we are supposed to do after that is, we'll go and check for each one. From this particular one, I'll traverse all the non-zero locations and see what is the minimum distance that this one can be from all the different locations. So this one can go to this place, this place, this place, this place. It can go to north, it can go to south, it can go to east, it can go to east, it can go to west. So for all the 4 directions, I'll be calculating the distances and I'll update the distance with, on comparing whether it is minimum or not. So I'm comparing like from this 0 position. If I want to move to this, I can add a distance of 1 and I'll compare it with the int max. It is 1 is always less than int max, so I'll update this with 1. Similarly, I'll go from each and every location and we'll have the final output metric something similar to this, right? I hope this approach is clear. Just try and dry run this once on your own, so you will get a better idea on what I'm trying to say. Now we'll move up on to the code part and you will have a little more clarity on what we have discussed in now. So this was the question that we were discussing. It tells us about the distance of the nearest cell having 1. We are given a binary grid, like we took the same example of 0, 1, 1, 0, 1, 1, 0, 0 and 0, 0, 1, 1. The output comes out to be 1, 0, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0. I've explained you the entire process, how we did, and now let's have a little bit of consideration of how this code is going to work. Let me just show you the code part. So what we are given in this particular question is, we are given a vector of vector. We have to return a vector of vector and we are given the entire grid. So that grid is basically the input grid that is given. Next, I'll create two variables n and m, through which we'll be able to iterate over the entire, we'll find out the size of the number of rows and number of columns of that particular grid. Next, I'll create my own answer vector and I'll initialize initially with all the places with int max, as I've already told you. Then I'll create a queue of the type pair int because it is going to store the index value of that particular grid. All the indexes we are going to store in this particular queue. So that's why it is going to be of the type pair of int and int. Next, this is the for loop that we are running basically to, like, we'll go and iterate over the entire grid and check at which particular position we have one. For the positions for which we have one, we'll update them to 0 because we've already seen, and we'll push those indexes into our queue. So now we have all the indexes with which were initially 1 in our queue, and we have made them to 0. That's one thing. Now we are running a while loop until and unless this queue that we have made of indexes is empty. We'll find out and we'll check for each and every position. For each and every position, we'll check out the nearest distance from a non-zero position. So we'll see, we'll take two numbers I and j. I stores the front element, the first element of the queue's front, and the second, basically the index first value. Let's say we have 0 comma 0 or 0 comma 1. So 0 comma 1, in 0 comma 1, 0 will be stored in I and 1 will be stored in j. Next, we'll check for a particular position in that matrix and we'll see if that position is greater than equal to 0. That this is basically to check if it is not out of bounds. It should not be out of bounds, so we are checking this. It should be greater than equal to 0 or it should be less than equal to n, or lesser than equal to n, so just number of rows and number of columns. And we'll check for each and every location, like we'll check for the top position, the bottom position, the left position and the right position, basically that I've talked about as north, south, east and west. We'll see if we'll compare both of them and we'll see if it is less than the initial present value. If it is less than the initial present value, so we'll simply update that position with that number and we'll put the index of that in our queue. So we'll check for each and everything. We'll check for south, east, north, and west for all these cases, like different cases I have made, like for all the iterations I minus 1 comma j, I and j minus 1, I plus 1 and j, and I and j plus 1. For all of them, we'll make this, we'll push the indexes, corresponding indexes, and after that we'll pop, like if the entire operation is done, we'll pop the index that we have operated upon. At the end, we are going to return this answer. This answer is of the form vector of factor int, and we are done. So I hope this code should be clear. You should be able to write it on your own. There might be a little difficulty while going through it for the very first time, but trust me, once you dry run it on your paper and pen, you'll definitely be able to solve this particular problem. Now let's move on to another problem, and this is something like, this is a very important interview problem with respect to queues. So make sure you don't miss on this problem, and let's move on to another problem. So moving on to the next problem. The next problem states, the name of the next problem is rotting oranges. It's one of the very famous problem and it's one of the favorites in an Amazon interview. Like, I've heard a lot of interview experiences in which this problem has been asked. So listen to this interview problem carefully and see how this goes. So what you are given in this is, you are again given an m cross n grid where each cell can have one of the three values. There can be three values in the grid. It can be 0, 1, or 2. So 0 represents that the cell is empty. We don't have anything in that cell. 1 represents that there is a fresh orange present at that particular place in that grid. And 2 represents that there is a rotten orange that is present at a particular location in a grid. So what happens is, every minute, any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. Matlab, what they are trying to say is, at every minute, like any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. Let's say this is a rotten orange and this is a fresh orange. Like, this is a grid. So if such is the case, so in 1 minute, this rotten orange will again rot this fresh orange. So it will also become rotten. So 1 minute will be passed. This is what they're trying to say. Return, what we need to return is, return the minimum number of minutes that must be elapsed until no cell has a fresh orange. If this is impossible, return -1. So we'll have to tell in what minimum time can all the oranges be rotten. Also, if this is not possible, like in any case, if there is any orange left that we can't rot, so we'll have to tell them ki we'll have to return -1, and this, that means this situation is not possible. So what exactly they're trying to say is, like, let's look at the first example that they have given already. So in this particular example, they are saying that we have a location, we have at minute 0. This means that the orange is rotten. That means 2 is placed here. And these are fresh oranges and these are empty cells. So after 1 minute, so this orange, this rotten orange can rot the oranges in 4 directions: upwards, downwards, leftwards, and rightwards. So upward there is nothing, so it can't rot anything. This is gone. From leftwards also there's no element that can be rotten, so it is gone. So downwards and sidewards. So for downwards, like in the first minute, when it will go in the first minute, this orange will be rotten by the uh, first rotten orange, and this orange which is present at the side will be rotten in the first minute. After 1 minute is done, so we'll move on to the another minute. Now this orange has the capability to rot all the oranges present in the 4 directions. So upward there is nothing, rightward it's already rotten, so it can rot the one which is present at the right and the one which is present at the down location. So in the second minute, this will rot this particular orange and this particular orange. Also, there's a possibility that this rotten orange can move in all the 4 directions. Let's see what will happen. Upward, it's already rotten, nothing to go. Leftwards, there's no place, it is out of bounds, nothing to do. Rightward, it can be rotten by either this or this. If it is rotten by this, then there's no use of this. Downwards, there is no orange, so it can't be used. So we will move on to the next. So in the second minute, we have 5 oranges that have been rotten. Now in the next minute, what will happen is, this orange has the capability to rot this particular orange, this orange has the capability to rot all the oranges in the four directions. This has also the capability to rot the oranges in the four directions. From here, there's no possibility, no possibility. This is already rotten and there's no possibility. Now from this orange, it can rot this orange, that this orange can be rotten in the next step. There is no possibility, it's already rotten, already rotten. So in the next minute, in the third minute, this orange becomes rotten and we move ahead. Now in the fourth minute, only one orange is left. This can be rotten by this particular orange in the fourth minute. This is rotten in the fourth minute. And you can see at minute 4, we have all the oranges that are rotten. So we can say the minimum number of minutes that must be elapsed until no cell has a fresh orange. Like in this case, there's no cell that is having a fresh orange. So we can say that the answer of this case would be 4, right? So this is what the question is going to say, and we are trying to, like, we will be given an input grid of the similar kind and we need to solve this particular problem. Let's look at the second test case that they have given. So the second test case is something like they want to uh, have something like 2 1 1 0 1 1 and 1 0 1. So here 2 suggests that it is a rotten orange, 1 suggests that it is a fresh orange, and 0 suggests that the place is empty. So in the first minute, what will happen is this 2 will rot the orange present at this particular location. Upward there is no possibility, sideward there is no possibility, downward there is no possibility. So this will become 2 in the first minute, matlab 1 minute passed. So it will be 2, 2, 1, 1, 1, 0, 1, 0, 1. So again, in the second minute, this 2 has the capability to rot this orange and this orange. It will become 2, 2, 2, 2, 0, 1, 1, 0, 1 in the second minute. Now for third minute, now this orange has the capability to rot this orange, and this has the capability to rot this, and this. But there's no need, uh, again no need, and this can be either be rotten by this or this. Till the third minute, we'll have something like 2, 2, 2, 0, 2, 2, 0, 1, 1. Now in the fourth minute, what can happen is this can become something like 2, 2, 2, 0, 2, 2. Now this orange can rot this orange. It will become 2. It is 0 and it is 1. So now there's no possibility that this fresh orange can be rotten. Like no, like even if let's say 10 minutes are passed, 15 minutes, 20 minutes are passed, this orange can't be rotten. At 4 minutes, like even after passing 4 minutes, this orange still remains the same. So there's no possibility that we can have this condition. So we'll simply return the output as -1. This is the second condition that they have given, right? So I hope the question is clear. Now let's move on to our uh, board so that we can understand it a little more better, right? On how we'll be solving this particular problem. So let's say, so now you have understood the question, right? So let me take a grid, a very simple grid, so that the things become easier for you. So we have this particular grid, right? Let's say initially this is the, like, oranges are present at this, and this location, right? We can number them as 0, 1, 2, 3, 0, 1, 2, and 3. So initially we are given this orange and this orange is rotten. So the orange which is present at location 0, 0 and which is present at location 0, 3 are rotten. So how we'll be solving this particular problem? We'll be using the concept of BFS once again. So in the concept of BFS, we use queue as a data structure. So here comes the application of queue once again, and it's a very, very important problem. You definitely need to check upon how we are solving this particular problem. But before starting with the problem, let's try and maintain a variable count. This count variable will have all the non-empty cells, the total number of non-empty cells in my grid. So total number of non-empty cells is 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 number of non-empty cells in my grid. So in every question of BFS, I need to maintain a queue. So I'll be maintaining this particular queue, right? So this queue will, like, firstly will start this queue, like, during BFS it starts with something, like queue should have something. So what we'll put is we'll put the locations, we'll put the indexes of the oranges which are rotten. So here 0, 0 is rotten and 0, 3 is rotten. So we'll put 0, 0 and we'll put 0 comma 3 in our queue, which is already there. So now we'll closely look at 0 comma 0 and 0 comma 3. So 0 comma 0 is here, 0 comma 3 is here. What can happen is, like, after the passing of 1 minute, this rotten orange can rot the oranges which are present in all of its four directions. That is, it can rot the orange present at the top, it can rot the orange present at the right, orange present at the bottom, orange present at the side. This 0 comma 3 can also rot the orange present at the top, present at the side, present at the bottom, and present at the left, right? So for this 0 comma 0 location, like top, there's no element, so there's no possibility, it's cancelled. From left side, there's no possibility, it's again cancelled. From right side, there's no orange that can be rotten, again there's no possibility. Downwards, now downwards, there is at that is the orange at location 1 comma 0, it can be rotten by 0 comma 0 in the first minute. Simultaneously, at the same time, for 0 comma 3, top there's nothing, left right there is nothing, left there is no orange, and downward position, that is 1 comma 3, it can be rotten. So after the passing of first minute, this is rotten and this is rotten, right? So what I'll do is, I'll remove the indexes already present from the queue and I'll add the indexes which are rotten. So indexes which are rotten are 1 comma 0 and 1 comma 3. Now after this, what I'll do is, uh, and like these indexes can be maintained by using the iterators I comma j. So, this can be the uh, number of rows, this can be the number of columns once we are iterating. This can be the number of rows, this can be the number of columns, right? So now after this, we'll pick up 1 comma 0 and 1 comma 3. When I say 1 comma 0, let me just erase this. Now if I have 1 comma 0 and I have 1 comma 3. So from 1 comma 0, that is this 1 comma 0, I can go to top, right, left, and bottom. Top, that's already rotten, so I don't need to do anything. Right, there's no orange. Left, it's out of bounds, and down it can be rotten. So the answer, we can rot the orange that is present at 2 comma 0 location. From 1 comma 3, similarly 1 comma 3, top there's no possibility, it's already rotten. Right, there's out of bounds. Left, there's no orange. Down, we can do. Down is 2 comma 3. So I have 2 comma 0 and 2 comma 3. So what I'll do is, I'll remove these indexes and I'll add 2 comma 0 and I'll add 2 comma 3. Right, now this is rotten, this is rotten. Now both of these are there. Now let me erase this once again. Now I have the elements 2 comma 0 in my queue and 2 comma 3 in my queue. So now if I have 2 comma 0 and 2 comma 3, again there is a possibility that this 2 comma 0 and 2 comma 3 can uh, rot the elements in all the four directions. This 2 comma 0, in the top direction, there's no possibility. In the right direction, yes, it can rot the orange present at 2 comma 1. In the down direction, there's no possibility because orange is not there. In the left direction, it is out of one. So only 2 comma 1 is there. For 2 comma 3, that is this particular orange. So this particular orange can also go in the four directions: top, down, right, and left. So when I say top, so it's already rotten, there's no need. Left, this is out of bound, there's no need. Right, left, there's no orange. And down, yes, it can be rotten, it is 3 comma 3. So now after this, we'll remove these and we'll add 2 comma 1 and 3 comma 3. So as soon as we are doing all this, like after each step, we'll see if at all the queue is empty or not. So for everything, like initially, let me take a new variable, that is minutes. It is 0. As soon as this has passed, like we remove these two elements from the queue and we add these two elements in the queue, we'll update the value of minutes to +1. Again, second case, we'll remove them. We'll again add the elements in the queue. Queue is not empty, so we'll again increase the value of minutes to 2. Again, we'll add these numbers. We'll remove them. We'll see the queue is not empty. We'll increase the number of minutes to 3. Now we are on a position that we have two more numbers in the queue. We have 3 comma 3 and we have 2 comma 1. So now 3 comma 3, this is 3 comma 3, it is rotten already. So it can rot the top, right, left, and bottom. Top, it's already rotten, no need. Right, out of bound. Down, out of bound. And left, it is empty. So this cannot rot any element, then it's done. Now 2 comma 1, 2 comma 1, it can also rot in the four directions. In the top, there's no orange. In the right, there's no orange. In the down, there's no orange. In the left, there is already rotten. So again, it can also not rot anything. So like we'll remove these elements and we are done. So what next we are going to see is we'll calculate the total number of elements that we have added in the queue. So 2 we have added here, 2 we have added here, 2 we have added here, 2 we have added here. So total number of elements that we have added in our queue is 8. So what we'll see is this minutes that will tell us the minimum time to rot all the oranges if and only if, like we'll return this minutes as answer if and only if this value of count becomes equal to this total number. Like we'll take a new variable total. So once this count becomes equal to total, that is 8 is equal to 8. Like in this particular case we have all the oranges which are rotten. There's no case in which any orange is left fresh. So what we'll do is we'll return this value of minutes. If this would not have been the case, like if count would not have been equal to the total minutes, then what we would have done, we would have returned -1 simply, right? So I hope this question is clear. This approach is clear. You should go through it once again. Might seem a little typical to you, but once you try it on your own on a piece of paper, it will be a little more clear, right? So let's move on to the code part and see how we'll be coding this particular question, right? So we are given oranges rotting. We are given a vector of vector int grid, like that is we are given a matrix. So first thing that we're going to check in this grid is whether this grid is empty or not. If at all this grid is empty, so we'll simply return 0. That is there's no time. That is there are 0 minutes that will be taking to rot all the oranges. Next we'll maintain two variables m and n. Along with that, we'll maintain the variables minutes. This will tell us how many minutes are elapsed for each of the rotting stage. We'll maintain a variable total that will help us to know how many total number of indexes or total number of oranges we are rotting, and we are adding it into the queue. This is the value of count that initially tells us total number of non-empty cells in our queue that we're adding. So I'll create a queue of the type pair int. Why pair int? Because it is showing the indexes, that is the value of I and j uh, for all the indexes of our grid. And we'll name this queue as output queue. We'll run two loops for from I to m, from j to n, like from the entire grid. We'll traverse this entire grid. We'll check for if at all the value of grid at any point is non-zero. That means we are checking the total number of elements, that is the total number of elements which are present in the queue, that is non-empty elements which are present in our grid. So we'll increase the value of total. So in our example we have already calculated the total number of non-zero, like non-empty cells in the grid, so it comes out to be 8. So we'll check for the same, and if at any point we'll check if the value of grid is equal to 2. That means in the first stage what we did is we initially made all the rotten oranges to be in the queue. So we'll check if the grid value is equal to 2. We'll push I comma j in the grid and in the queue, so that we have these two elements from where we can start our BFS. Next is this is dx and dy. These are the four directions. What do these four directions suggest? I'll try to explain it with the help of this chart. So like let's say this is in a coordinate system also, if we want to move in this particular direction, so we have 0 comma 1. Any point in this particular line will be of the form 0 comma 1. Any point of the form 1 comma 0 will be of in on this particular line. Any point of the form 0 comma -1 would be of the form this, and we'll have -1 comma 0, right? So we'll see, like this will help us to move in all the four directions, that is north, south, west, east and west, whenever we are writing our code. So we'll see, like you will understand it a little later when we'll put them in our code. So what we'll do is we'll check upon until and unless our queue is empty. We'll make a condition for our queue until and unless our queue is empty. The first thing that we're going to see is we are getting the value of k, that is the size of the queue. Why we are maintaining the size of the queue? Because at the end we'll have to check whether our count is equal to total or not. If this doesn't happen, we'll have to return -1. So this count variable tells the total number of elements that are added in the queue, the total number of oranges we have rotten. So it maintains this particular count. So until and unless the size of queue becomes 0, what we'll do is we'll create a variable x, we'll create a variable y. X will store the outputs front first. Outputs like queues like I and jth index, basically x and y are I and jth index of the elements, and for each I and jth index, what will remove that particular element from the queue, and for each value of I and j, what we'll do is we'll add dx of I and dy of y. That means what we are going to do is like we have seen here. Yes, so we have seen here. So for each value of element that we have added in our queue 0 comma 0, we are going to check in all the four directions. So for checking in this particular direction, what I need to do is I need to add in the positive right, I need to subtract in the negative down, I need to subtract in the negative left, I need to add in the positive y. So this is something that we're going to do, and this has been implemented using uh, dx and dy, because these are the values. Like we'll add one at, we'll say x plus dx of I, that is dx of 0, the x, and we'll check upon x and y minus y plus 1. So for x and y plus 1, what will be the case? So similar to that, like we'll check for nx, ny, nx, like will these are basically the boundary conditions that the value of nx should not go out of the bounds, and we'll check if at all our grid is not empty. So if it is not empty, then we'll simply continue. If it is well, if it is non-empty, if it is not a fresh orange, then we'll continue. If it, or else we'll make it equal to 2. That means we'll rot that particular orange, and once we have rotten that particular orange, we'll put it into our queue. Finally, we'll push the indexes of them in our queue, and at the end we'll check if at all our queue is not empty. We'll increase the value of minutes, that is for every element, for every rotten like after checking if our queue is not empty, we'll increase the value of minutes like we were increasing in the r uh, in our explanation. So the value of minutes will give us the total number of minimum number of time that is required to rot all the oranges. If at like at the last we'll make a check. If our total equals to count, then we'll return minutes. Else what we'll do is we'll return -1. So this is basically the code. I hope this will be a little more clearer to you. I have given you an idea. Now it's your turn to just go through the code, just go through the question once again and try solving it on your own in any of the preferred language, be it C++ or Java, so that you can solve this problem during your interviews, right? I hope this solution is clear to you, and make sure you dry run it once on your own so that you can get it in a better way. Thank you so much. Let's move on to the next question. So we're going to see yet another question, and it's also a very, very important question. People do miss upon this question. It will be an easy question, but still you need to see upon how we'll be using queues to solve this particular problem. So the question goes something like this. You are given a stream of numbers, you can say you are given non-repeating characters. You have to find the first non-repeating character in a stream using queues. So this is the question that is given to you. So what does this question actually means is, like, you are given a stream of numbers. When I say stream of numbers, stream of characters, that means characters are coming one by one. Like initially in my string, I have A. Let's say A is the first character that is coming up. So the answer corresponding to this A will be A only. Like A is the only element in my string and A is non-repeating, so the answer will be A only. Now I have B added to my stream. Like B is the second element which is coming in the stream. But still, which will be the first non-repeating character in my stream? A, again, A is not repeating till now, and A is the first element. So the output corresponding to this will also be A only. Now let's say I have the third character, that is A again. Now, as soon as we add another A, we'll see that A is repeated. So now A goes from the picture. Now, which is the first non-repeating character in the stream? So the first non-repeating character in the stream this time will be B. Now, in the next iteration, I'll have A, B, A, C. Let's say I have this particular thing. So again, for this particular case, which is the first non-repeating character? Still B remains the first non-repeating character in the string. So I'll have B as the output again. Let's say I have another C as the output. So the answer corresponding to this will again be B. Let's say I have one more C coming up. The answer corresponding to this is also going to be B. So this is something that I'm looking forward to as an output. So my output should look something like A, B, 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 B. So this, like, let's take one more example. Let's say you have A, B, B, A, B, C, C. So this is the string that you are given. Let's say all the characters are coming one by one. Initially, A was the first element that came. So answer corresponding to A will be A. Next, at this particular point, also the first non-repeating character remains A. So the answer will be A. At this particular point, uh, again the answer still remains A because A is not repeated. At this particular point, now at this particular point, you see, do we have any character which is repeating, which is non-repeating? Now we have two characters A and B and both are repeating. So at this particular point we will mark hash, right? Now again B, at this particular point also I have no element which is non-repeating, so I'll mark hash again. At this particular point C, which is the first non-repeating character, C is the first non-repeating character. At this particular point all the characters have been repeated once or twice, so I'll again mark hash. So the answer corresponding to this is this. So where we are going to mark this hash, where we don't have any non-repeating character prior to that in the string. So this is something that the question says, like, and how will we trying to solve this particular problem is, let's see how we'll be solving this particular problem. Yeah. So for this, let's say I have, we'll take the example of this string only, A, B, A, C, C, C. And for this, I'll maintain a frequency array. This frequency array will mark the frequencies of the characters from A, B, C, D till Z. Small letters, small alphabets, small English alphabets. And I'll maintain a queue, right? And I will have one output string that will contain the output answer that I want. So we'll be having three things. So as soon as a character is coming up in the array, in the string, so let's say firstly A comes up. So what I'll do is I'll go in my frequency array and I'll increase the frequency of A to 1. Now I'll put this, like my queue is empty. I don't have anything. I don't need to compare or do anything. So I'll put this A in my queue. And also the first non-repeating character at this particular point of time is also A. Now the second number comes up. It is B. Now I'll increase the frequency of B here. I'll add B to my queue. And in the output array, what I will do is I will pick up the front element of the queue, right? The element which is present at the front index of the queue, that will be going to the output every time because that has not been repeated yet, right? Now the third case, now A comes up. Now again, as soon as A comes up, what happens? The frequency of A here becomes 2 now. As soon as the frequency of A becomes 2, so what I'll do is if that element is present in my queue, I'll remove that element from the queue, right? Now the element correspond, like, which is the front element in my queue that is present, the front element in the queue that is present is B, so I'll output B, right? Now again I have C, so corresponding to C, I'll mark the frequency of C as 1. I'll put this C in my queue. Corresponding to C again, what I'll see the front element of the queue. The front element of the queue is still B. I'll move B. Again, I'll check out C. C is again coming. We'll increase the frequency of C here. As soon as the frequency of C is increased here, I'll remove C from my queue. Again in the output, what I'll see the front of the queue. It is again B. I'll put B. For the next C, I'll again see the frequency here becomes 3. Like, it is not 1. So again, this C is not there in my queue. I'll not do anything. Corresponding to this, I'll check my queue, which is the element which is present at the front of the queue. It is B, and I'm done. So this particular output is what I want. And see, our problem has been solved very quickly by this particular methodology using a queue, because we can push we can push from the rear end and pop from the front end. Here in this question, the requirement was that we need to pop from the front. So basically, we can solve this problem using this particular methodology. Now, let's see how the code of this particular question will work. So for the code of this particular function, for the code of this particular question, I will need to create a queue. I'll create a queue. I'll create a frequency array, and I'll create an output string. So what I will be doing is, as soon as a number comes up, as soon as a character comes up in a string, I will add that to my queue. I'll increase its frequency and I'll see the front of the queue. What will be the front of the queue, and corresponding to that front, I'll add it in my queue. Whether it is to be added in my queue or not, I'll take a decision based upon that. Right? Also, one thing I'll check is until and unless this queue size is empty. Like if there is nothing in my queue at that particular point of time, what I will do is I'll see like there's no element which is non-repeating, first non-repeating element. So we'll correspondingly put a hash in the output, right? For that particular case, let's see, it will be more clear once you see the code part. So let's move on to the code part and see how it goes. So let's quickly see this code part. Basically, we have this particular question. We are given a first non-repeating character in a stream, and corresponding to that, we'll have to perform the things that we have discussed already. So the first thing that I've told you that we'll be doing in this particular question is we'll be making a queue of the type character, because we are adding characters there. Let me name it as queue. I'll maintain a frequency array, frequency of 26, because there are 26 alphabets in English, 26 letters in English alphabet. So initially this frequency array is 0. I'll maintain a string answer that will initially be empty. Now I'll run a loop. We are given a string a, and corresponding to this, what I'll do is I'll push that element in my queue as soon as it comes. So a of I, I'll push it in my queue. Next thing is I'll increase the frequency of that particular element corresponding to that. So the frequency goes something like a of I minus 97. Why 97? Because the sky value of a is, well, the first alphabet is 97, so we'll increase it. Now I'll run a while loop and check until and unless the size of my queue is not equal to 0, and also the frequency of queue dot front. The element which is present at the front of my queue, if its frequency is not equal to 1, it is greater than 1, equal to 1. So what I'll do is I'll pop that element from the queue. That was something that we were doing. And after that, we will check if the size of the queue is not equal to 0, there is something in my queue, then we'll in answer is the string that we'll be getting as the output. In the answer string, we'll push back the front of the queue, right? I hope these steps would be very clear to you, because you have already seen what the solution is like. Else what we'll be doing is, else we will simply push back hash, right? When our queue becomes empty, we'll simply push back hash. And let's just try to return this, return answer string, and I hope this should work. Okay, let me just compile and run. So it's a medium level question that is marked upon geeks for geeks. Is it something that we are going wrong with? Q character Q, we are initializing a frequency array, string type of length I plus. We are pushing it in the queue, frequency of wave 5 minus 97 plus proceeding, while my queue size is not equal to 0, and my frequency of front, this should be frequency of front minus 97, because again we are checking the sky value is not equal to 1, then q dot pop, q dot size equal to, okay. So I think it should work now. Let me just try it once again. So this, like, we didn't do the subtraction of 97 because we are comparing the sky values, we are storing it in the frequency array. Now we have this particular output corresponding to this. Yes, our output should be this, because corresponding to A, the output should be A. Now A is, once again, now I don't have any element which is non-repeating, so I'll put hash B, so I'll put the B as the answer, and C, we have B, which will be present at the front of a queue. Let me try to submit and see if it goes well. So yes, we have successfully solved this problem, and I hope the solution is clear to you. It's also a trivial problem, but yet it is considered in the medium level, and it is asked by various companies and has been solved using queues. Now let's move on to another question.
Hi everyone, discussing another problem. The another problem that we are going to discuss is finding the count of unvisited indices in an infinite array. The question goes something like finding the count of unvisited indices in an infinite array. So question goes something like, given an array of infinite length, you are given an array whose length is infinite and two integers m and n which are co-prime. You need to find the number of positions that cannot be visited starting from the first position when in a single move from ARR of I you can go to ARR of I plus m and ARR of I plus n. Also, you are given a note that the result is finite. So now you have seen the question. So what it exactly says is, it says that you are given two integers m and n and an infinite array, right? Infinite array. What you are given, the properties of m and n is that m and n both are co-prime. When a number is said to be co-prime, a number is said to be co-prime if it doesn't have any other factor than 1. So they both have 1 as a common factor. Let's say we have 5 and 7. So for 5 and 7 the common factor is 1. So 5 and 7 are co-prime. Let's say 3 and 5. So for 3 and 5 also there's no other common factor than 1. So 3 and 5 are co-prime. So m and n are co-prime numbers, and you are given that you need to find out the number of positions that can't be visited starting from the first position when in a single move you can move. So this is an infinite array that you are given, and you have to tell me the number of positions that cannot be visited using these indexes. Matlab, if I move from array of like from the 0th position I can move m steps, or I can move n steps, or I can move m plus n steps. So which all indexes will be there in an infinite array which will not be visited? But like, see, if it is an infinite array, so then you might be thinking ki this will to go on in an infinite loop, like we'll be having infinite numbers which will not be visited, or we'll need to run through the entire loop. But no, there is a property, special mathematical property, like if you are good at maths, not good at math, this is something that you need to know for solving this particular problem. Let's say I have a given input. Let me just explain you with the input and output. Let's say m is 2 and n is 5. The output you will get in this case is 2. Why 2? So like from the index 0, the indices that can be visited are, like it can be 0 plus 2, that is 2. It can be 0 plus 2 plus 2. It can be 4. It can be 0 plus 5. Can be 5. 0 plus 2 plus 2 plus 2. We can visit 6 also. Can we visit 7? Yes, we can visit 7. 2 plus 5 is equal to 7. Can we visit 8? Yes, 0 plus 2 plus 2 plus 2 is equal to 8. Can we visit 9? Yes, we can visit 9. 0 plus 2 plus 2 plus 5 is equal to 9. 0 plus 5 plus 5 is equal to 10. So we have done it till here, and we have seen that 1 was not there and 3 was not there. Like apart from that, like you are given this 1 and 3 are not visited, hence the answer comes out to be 2. But from an infinite series, we have just chosen these 10. Why? On what basis? So there comes a property of Frobenius number. So what does this property of Frobenius number tells us? So you need to know this Frobenius property. Let me just read out the exact statement of Frobenius number. So Frobenius number, it will tell you the largest index that can't be obtained using any combination of m or n. It gives the largest number that can't be visited using any combination of m or n, where m and n are co-prime. So there is a formula. I will not go into the depth of formula. So it will give us the largest number in this form. So you can go and search for Frobenius number if you want a detailed explanation proof for this particular property. So you just need to have this result in your mind for solving this particular problem. So Frobenius number, it gives us the largest number that can't be visited using any combination of m or n. Right, so x is equal to m star n, m multiplied by n minus m minus n will give us the largest number which cannot be visiting using the combination. So this makes the problem a finite one, right? So we don't have to traverse over the infinite loop, but we have to look forward till this particular number. After this, we don't need to check anything, right? So for our case, like if m is 2, n is 5, so the value of x will be 2 into 5 minus 2 minus 5. It will become 10 minus 2 minus 5. It will be 3. Right, so the largest number that can't be visited using any combination of m or n is 3. So have you got this point? The 3 is the largest number. Also we have seen now 1 and 3 were the only numbers, so 3 is the largest number that can't be visited using any combination of m or n. So using this similar approach, we are going to solve this particular problem. We'll need queues, as we are discussing queues at some point of time. We'll need queues to solve this particular problem. We'll see how we'll solve this. Now you know you have the largest number. What we can do is, if we know that there's a largest number x which can't be visited, so x minus m will also not be visited and x minus n will also not be visited. So we'll push these numbers in our queue and we'll maintain a count, and at the end we'll return this particular value of count so that we can get to our answer. Let me just go through the question once again so that you can understand it in a better way. So what we are given in this question is, we are given two numbers m and n, both of them are co-prime. Using these two numbers m and n, we need to start traversing our array from traversing our infinite array from 0th index. We can increase by m steps or we can increase by n steps, and we need to find out the places that we cannot visit, the total number of places that cannot be visited in that infinite array. So what we have come up with the solution, we have something known as Frobenius number. So Frobenius number tells us the largest number that can't be visited using any combination of m or n. So using Frobenius number, let me calculate the value of x that will give us the largest number that can't be visited using any combination of m or n. So once we have that largest number, we need to see, like we already know that after that there's no number that we are going to check. We need to check only till the number x. So now we have the value, we know this number. So from this x, we'll have an intuition that x minus m, if x is not visited, there's an obvious way x minus m also want to be visited. If x minus m would have been visited, so then x would have definitely been visited by that number. So x minus m is also not visited, x minus n is also not visited. At the end, what we'll do is we'll maintain a count for all the numbers that have not been visited and we'll return this count. So let's move on to the code part and see how we'll code this particular question. So now we'll be seeing the code for this particular problem. We have the function name as count unvisited, and we are given the value of m and n. The first thing that we were doing is we were calculating the Frobenius number. Let me just name that Frobenius number as x. The value of Frobenius number is majorly m into n minus m minus n. You can look forward to the explanation of this particular formula online at by searching for what Frobenius number is. Next, what I'll do is I'll maintain a queue of integers and I'll name it as queue. The first thing that I'll do is, in this queue I'll push this value of x. Once I push this value of x in the queue, and I'll maintain a count variable, count is equal to 0. Now I'll run a while loop while my queue is not empty. Until and unless my queue is not empty, what all things I am going to do, I'll check for the current that is present in the queue. So the current element that is present in the queue, I'll mark it as, like, we can get the element from the current, and then we'll remove this particular element, queue.pop. Once I remove this particular element, then I will increase the count. Like, this is the number that can't be visited, so I have the count value as 1 now. Also, what else I have seen is, if at all my current minus m is greater than 0, if at all they are greater than 0, then what I'll do is I'll again push them, queue.push current minus m.
if my current minus n is greater than 0, I'll queue dot push current minus n, right? So this is something that we are going to do, and at the end we'll return the value of count. It will give us the exact value of count that will help us to solve this particular problem. Return the count. So let's see what we have done. We have written this function with variables m and n. We have calculated the value of x, that is the Frobenius number. It gives us the largest index that can't be visited by using m and n. We maintained a queue of integers. We push this x in the queue, and after that we have the value of count initially equal to 0. As soon as we popped out the current element from the queue, we increase the value of count. Then we know that if the current element can't be visited, so current minus m also won't be visited, and current minus n also won't be visited, and after both these cases we'll return the value of count. We'll try to run and see how it goes. So the answer that we're getting is 2. So this is running for the test case 2 and 5. Let me just run it for one more test case, let's say 3 and 7. So for 3 and 7, what will be the answer? So for 3 and 7, the largest number that can't be visited is 7 itself. So yeah, I hope this problem is clear to you. Now let's move on to another problem. Hi everyone, so we are going to discuss one more problem in the series of problems. This one is going to be a little easier problem, as after a lot of problems we are going up with this problem. This problem says a geek prepared n questions for developers hiring challenge of Geeks for Geeks, but the hiring manager wants only one question in the contest. He asked the geek to give the best problem out of n problems. Geek thinks that all the problems are the best and he's confused to choose a single problem. So what he does is, he places all the problems side by side from 1 to n. He takes out the first problem and inserts it at the end, removes the next first problem from the set. He repeats the same process until a single problem remains. The task is to find the single last problem. So this question seems to be very easy. So the approach, the thing that they want in this particular question is that you should be able to remove a number from the front and add it at the back, and also you should be able to remove a number from the front. So these two properties are very well being sufficed by our queue data structure, right? So we'll see how the question statement and input output statements are given. So seeing that, I can see you have something given as, like, you will be giving the number of test cases t. After that, for each number of test cases, you will need to tell which is the last number that will remain, right? So let's just try writing the code for the same and see how it goes. So the first thing is, we need to input the number of test cases, int t, c and t. So t stands for number of test cases. So we'll run these until all the test cases are passed. We'll insert a number n, c and n, and after that we'll make our queue of integers. Let me name it as q. Now I'll run a for loop and I'll insert the numbers from 1 to n, right? So they haven't specified that exact number that you have to, they just told you are specifying numbers from 1 to n, like 1 2 3 4 5. Like if n's value is 5, so I'll have the numbers 1 2 3 4 5 in my queue. So let me make a queue and insert the numbers from 1 to 5. I is equal to 1, say n equal to n I plus plus. After that, what I'm going to do is, I'm going to do q dot push and I. As soon as this is done, what I'll do, I'll create a while loop for queue's size greater than 1. We'll only do if the queue size is greater than 1, because we need the queue at the size 1, right? So what I'm going to do is, I'm going to q dot push. I'm going to push the front element in the queue from the back. So what I'll be pushing, queue's front, and at the same time I'll have to remove that front element. Also, after, like, what happens, what I'm doing is, this is the element, right? So I'm removing this element, I'm adding it at the back,
right? This is, I'm pushing the element at the front element is pushed at the back, and then it is removed. The next step is I have to remove the second element. To remove the second element, I'll again have to write q dot pop, so that it is done. Let me just erase this, right? So again, once I'll write q dot pop, and what we'll do, we'll see out for each test case. What will see out? The front element that is left in the queue, right? So I hope this code goes well and you have understood the problem carefully. It was a very trivial problem. Basically, you should be able to understand the properties of queue. That's more than sufficient. Let me compile and run. Yes, we are getting a certain output. Let's try to submit. So yes, we have successfully submitted the problem, and this is also done. So now let's move on to another problem.
Hi everyone. So now we are going to see application of queue in trees. How in tree data structure we can use our queues for BFS. BFS means breadth first search. This is a very important application of queues, and like it would be very difficult to solve this problem of trees without using queues. That is without using breadth first search. So what actually happens in breadth first search is like let's say we have a particular tree. For some of you, you might, if you haven't been introduced to the topic of trees yet, I would advise you to go and check out some of the videos on trees first, then come to this problem on queues. For rest of you who are clear with the basics of tree, how to form a tree, they can have like they can understand it right now, right? Let's say we have this tree data structure and we want to print this tree in a level order fashion. So when I say level order fashion, so what I mean to say is I want to print it like first I want to print 1, then I want to print 2, 3, then I want to print 4, 5, 6, 7. So the output that I want is of this format. It should be 1, 2, 3, 4, 5, 6, 7. So this is the output that I'm looking forward from this particular question, and how queues are going to help. That's our actual main topic. We'll discuss about that, right? So we can think of ways on how we will be solving this particular problem, right? Let's say I want to print this particular question. If I was to go by initial method, so for the identification of a tree, the node that is given to us is root node. Okay. So from root node, we can access either its left subtree or we can access its right subtree. But if we go to one of the subtrees, let's say if I'm going from root, if I start accessing roots left, okay, then it would be difficult for me to access roots right after that. After I access 1, then let's say I print 2, then after that I can't go back to root. I need to print either 4 or either print 5. That would be very cumbersome if I go by this particular method. So what helps us in this is our queue data structure. So what I will be doing actually is I will be maintaining a queue, right? This is a queue. So what happens in a queue is we add the elements from the rear end and we remove the elements from the front end. So let's say the first element that comes into the picture is the root element. So I add the root into my queue, right? So 1 is added into the queue, right? And I am also maintaining an output array or output factor, you can say, that will store my final answer. So what I will do is I'll first add the root to my queue. I'll push queue 1 to my queue. Then as soon as I'll remove this queue from this one from my queue and I'll add it to the output. Like I'll add this node's data into my output, right? As soon as I remove this from the queue, I'll add both its children in the queue. I'll push them from the back. But I'll before that I'll make a check like whether it's left or right exists or not. So I'll add 2 and 3 simultaneously, right? After this, what I'll do is I'll check for 2. I'll remove 2 from the queue and I'll add it in my output. I'll add the data of this particular node into my output. And as soon as I remove 2, I'll add both of its children in the queue. So 2's children are 4 and 5. I'll add 4 and I will add 5 in my queue. As soon as this is done, what is the next step? I'll remove 3 from my queue. I'll add the data in my output. And as soon as I remove 3, I'll add the children of 3 in my queue. I'll add 6 and 7. Right? Now, next step is I'll remove 4 from my queue. I'll add it in my output and I will check for the left and right node of 4. There's no left and right node of 4, so we'll not do anything. Like we need to make this check whether the left or the right node of that particular node exists or not. Right? So now it is also null. It is also null. So we'll not do anything. We'll simply remove this and add it to the output array. Next is I'll similarly check it for 5. Again, for 5 also it doesn't exist. I'll put it directly into the output, its data. Then I'll check for 6. It also doesn't exist. I'll add it into the output. Then for 7, it also doesn't exist. I'll add it into the output and we are done. So in this way, basically the tree data structure, that is queues for BFS, uh, helps us in solving this particular problem that is known as a level order traversal. And it doesn't only helps us in trees but graphs also. There is a method to traverse a graph known as BFS, that is breadth first search. In that method also we are definitely going to see the application of queues. Now let us move upon to the code of this particular problem and see how we perform BFS using our queues. So what we're given in this particular question is, this is the question that is present on Geeks for Geeks for level order traversal. They have given us a binary tree. They want us to find its level order traversal. Level order traversal is a breadth first search traversal of a tree. Like 1, 3, 2 is there. So first we'll input of output 1, then 3, then 2. For this also it would be 10, 20, 30, 40, and 60. 10, 20, 30, 40, and 60. So this is what they are expecting out of this particular problem. What they have given is they have given us a function signature of this particular format. So function signature looks something like this. If you can see, so we need to code upon this. So the output that they want us is a form of a vector. So we'll take our output array or the output like I told you an array, but we can take a vector. So it will be, let's say, let's name it as vector int answer. This is something that I'll maintain. Also, I'll check if my node exists or not. Like if the node is only null, then I'll simply return this answer. Like this is an empty vector, right? Next, I'll maintain a queue of integers. Let me name it as queue. And the first thing that I will push in my queue is I'll push this node. Like this is the root. The first thing that I push in my node is push in my queue is the root. After that, I'll check for until and unless my queue is empty. While my queue is not empty, I'll make certain things. I'll take out the front. Let's say node star t is equal to queue's front. Now I've removed that topmost element or the element that I've added in the queue. Then I'll do queue.pop, that element I have removed from the queue. The next thing that I'm going to do is in this answer vector that I'm going to actually return, I'm going to push back the data of this t. Right now we are done with this. After this, I need to push the left and the right of this t into my queue. So for that, I'll make a check whether the left of the t exists or not, or the right of the t exists or not. Firstly, what I'll do is if t's left exists, like this statement says that if there is a possibility that t's left exists, like t's left is not equal to null, then what I'm going to do is I'm going to push t's left in my queue. Else if P's right exists, then what I'm going to do? I'm going to do queue dot push P's right. Okay. Now after everything is done, what next thing I'm going to do is I'm going to do queue dot pop. Like we can do it here also, we can do it here also. Let's do it after doing all this. Doesn't make a difference, but let's go with the flow. After this, let me return the answer vector that we have made. I hope this code should work, and let me just try to compile and run this code and see how it goes. So it's ready for evaluation. Okay, so here we have to make, rather than integer, we are adding the uh, elements in the queue which are of the type node star. So rather than making this queue of integer type, I'll have to make it of node star type. Now I hope it should be fine. So yeah, so for the first input we are getting the output as 132. Let me see and submit if this goes all well. So the code for our level reversal is passed and we are done with the problem. Now let's move to another problem. Hi everyone, so there's a question by the name of IPL 2021. So this question basically we'll read the statement and then we'll find out how exactly we'll be able to use Q in this particular question. So they are saying due to the rise of COVID-19 cases in India, this year BCCI decided to organize knockout matches in IPL rather than a league. So today's the match day 2 and it's between the most loved team, Chennai Super Kings, and the most underrated team, Punjab Kings. Stephen Fleming, the head coach of CSK, analyzing the battling stats of Punjab. He has stats of runs scored by all N players in the previous season and he wants to find the maximum score for each and every contiguous sub list of size K to strategize for the game. So what exactly they want us to do is uh, just think upon this problem. We have already done this problem before, which like it's a variation of like it's the same problem that we have already done. So we just need to understand this particular statement and see what they're asking. So in this particular problem, they are given us n, that is the size of this particular the scores that we are getting, and the value of k is 3, and they have given us an array. So what exactly they want us to do is they want us to find maximum subarray maximum subarray, the element which is the we have to find the maximum element in a given subarray. So out of this particular subarray of size k, size 3, in this case the answer is 3. For next subarray the answer is 3 again. For next subarray the answer is 4. For next subarray the answer is 5, and in this way it will go on. So I hope you people know this question now. We have solved it using queues. So try submitting this problem on Geeks for Weeks. I hope you will be able to solve this particular problem.
Hi everyone, so the next question that we are going to discuss is basically the question states that you need to reverse the first k elements of a queue. So what exactly you will be given in this particular question is the input will be value of k, n, and a queue of numbers, right? So let's say the value of k is 3, the value of n is 5, and the numbers in the queue are 1, 2, 3, 4, and 5. So now for these 5 numbers, what I need to do exactly is I need to reverse the first k element. Like out of the 5 elements, the first k element, that is the first 3 elements I need to reverse. So if this is the given input, I'm looking forward to an output of this form: 3, 2, 1, 4, and 5. My output should look something like this, right? So how we can do that? and we can solve this in a time complexity of O of n and a space complexity of O of n. That is, we can use an extra space. This is given to us in the question. So the first thing that comes into my mind is like, I'll create a stack. Let's say I create a stack S of integers and I put in the first three elements of my queue. I'll dequeue the first three elements of my queue. I'll pop the first three elements of my queue and I'll push them into my stack. So 1 will go here, 2 will go here, and 3 will go here. 1 was earlier here, so 1 will be removed, 2 will be removed, 3 will be removed, right? Now my queue will look something like this. Well, if we are planning out a circular queue, so internally, if you have understood queue, so you know now 4 and 5 are at the top positions. Now what you need to do is you need to pull out an element from stack. That is, you need to pop an element from stack and push them back to your queue, all three elements, until and unless this stack is empty. So after this step, my queue will become something like this: 4, 5, 3, 2, 1, isn't it? Now last one step that I need to do is I need to pop these n minus k elements. These are n minus k elements. I need to pop them and push them in the same queue. So now if I pop 4 and 5 and I push them back, what I will get? I'll get the output as 3, 2, 1, 4 and 5. So this is exactly what we are looking forward to. This will be our output, right? So what we did initially, like we were given the question to reverse first k elements of a queue. The input that was given to us is a value of k, the value of n, that is the size of the queue, and a queue of numbers. Let's say I'm taking an example of 3, value of k is 3, value of n is 5, and I am taking a queue. So for this queue, I need to reverse first three elements. After reversing first three elements, the output that I'm expecting is something like 3, 2, 1, 4 and 5. Now next thing that I need to do is I need to create a stack. I'll pull out, that is, I'll pop three elements, that is first k elements from my queue, and I'll push them in my stack. Next thing that I'm going to do is I'll pop these elements from the stack one by one and I will push them back into my queue. So my queue becomes something like 4, 5, 3, 2, 1. And the last step that I want to do is I'll be pulling out, that is, I'll be popping out n minus k elements from my queue and pushing them back once again. So my output becomes something like this. I hope you have understood the approach. Now let's see how to code this particular problem. So you can see the question. The question says you need to reverse the first k elements of the queue. You are given an integer k and a queue of integers. You need to reverse the order of the first k elements of the queue, leaving the other elements in the same relative order. Only you need to follow the standard operations that are allowed on queue in this particular question. That is, you can only use enqueue, dequeue, size and front for this particular question, right? They have also given the example 5 elements, 3 is the value of k, so you need to reverse 1 to 3 as 3 to 1 and so on. So now let's see what we did in our approach. The first thing that I did in my approach was I created a stack. So let me create a stack here, stack of integers, and let me name it as S. Inside the stack I'll iterate and I will push the top k elements of my queue, right? I is less than k and I plus plus s dot push queue ka front, right? And at the same time I'll pop that element from my queue. Now we have done the first step. We have made a stack and we have popped out the top k elements of the queue and pushed them into our stack. The next thing that I'm going to do is, while my stack is empty, until and unless my stack is empty, what I'm going to do is I'm going to push the k elements back into my queue. So that will be s dot top. Then I'll be popping those elements from my stack. Now the second step is done. So what is the third step? After that, I need to remove the first n minus k elements from my queue and push them back. I'll pop the first n minus k elements and I'll push them back. So let me just see what is the size of the queue. Let's name it as n. N is equal to queue dot size. We'll use the inbuilt function of size and we'll run a for loop for int I is equal to 1 to I less than n minus k and I plus plus, right? I'll have int x is equal to queue's front and queue will pop and will push this element x into our queue again, right? After everything is done, we need to return back the value of queue, and I think we are done with the question. Now let's try to compile and run and see how it goes. Okay, so there is a semicolon for this particular question of the output 5 and 3. What I was supposed to get? I was supposed to get the answer as 32145, but there is something wrong with our approach, I guess. Not with our approach. Let me just see. Stack S, we have pushed out elements, queues pop while stack is not empty, queue dot push s dot top, then s dot pop, int n is equal to queue size, I is equal to it should be starting from 0. Rest everything is fine, I guess. Yeah, so we are getting the correct answer. Let me submit. Yeah, so we have successfully submitted this problem and I hope you have understood the code as well as the problem. Now let's move upon to another problem. So let's discuss another problem. It's a comparatively easier problem, but still you might not strike, the logic might not strike in your mind. So what we need to check in this particular problem is, you need to check if the queue elements are pairwise consecutive. To check if the queue elements are pairwise consecutive. What I mean to say by this is, let's say you are given an example input. You have numbers like 1, 2, 5, 6, 9, 10. So pairwise, like we'll be making their pairs and we'll checking the difference between them. Both of them, the difference is absolute difference between them is 1. Absolute difference between them is 1. Absolute difference between them is 1. So for this particular question, I want to return the value true as my output, right? Let's say you have another input. Let's say 7, 8, 6, 7 and 5, 8. So for this particular question, here 1 holds, but here it is 3. So for this particular case, I need to return a false as the output. So how we'll be solving this particular problem is, like we'll be creating 2 stacks. We need to create 2 stacks. Let's say stack A1 and stack A2. Okay. So first thing is, you need to transfer all the queue elements to stack A1. Secondly, transfer all the stack A1 elements to A2. Now, as you remove, or you can say pop, elements from A2 side by side, check what's the difference between consecutive pairs. Right? If it is 1, like absolute difference is 1, if it is not 1, so then we'll simply return false, else will return true. Now this is one use case. And fourth thing is, like after popping, you need to push the elements in the original queue so that it remains the same. Right, so these are the steps, and let's see how we'll be performing these steps with the help of an example. Right, so we have, let's say, this as the input, 1 2 5 6 9 10. Right, I am creating a stack A1, I'm creating another stack A2, and the first thing that I told you was to pop all the elements from my queue and push them into the stack A1. So it will contain 1 2 5 6 9 and 10. Right, now all the elements of A1 to be moved to A2, it will be 10 9 6 5 2 and 1. Now I'll be popping out two elements at a time, let's say 1 and 2, and I'll be checking out the difference between them. 1 minus 2, it will be absolute of 1 minus 2 is equal to 1. So yes, if it is yes, I'll push them into my queue. Now my queue is empty, right? All the elements have been removed. So let's say this is empty. Now I want to insert 1 and 2. I'll insert 1 and 2. Now I'll go and pop out 5 and 6. I'll find out the difference, it is 1. I'll insert them in my queue. Now I'll go and check out 9 and 10. The difference is again 1. I'll add them into my queue, and we are done. As soon as these three are 1, we are not getting any false, so the answer is going to be true, else the answer is going to be false. Right, so I hope you have understood the problem. What we actually need to do, we need to check if the queue elements are pairwise consecutive or not. Pairwise consecutive ka matlab, like for the pair of 2 2, it should have a minimum difference, it should have a difference of 1. Matlab consecutive ka matlab both the numbers are together, like 1 2 5 6 9 10. So input that you are given is 1 2 5 6 9 10. So the difference between them is 1 1 1. So answer you need to return is true. Right, what you need to do in this case is you need to create two stacks, stack A1 and stack A2. Firstly, push all the elements from queue to stack A1. Now push all the elements from A1 to A2. Now as you are removing the elements from A2, check two elements at a time. If the difference between them is 1, if the absolute difference between them is 1, keep on pushing and putting them in the queue again. And as soon as the stack is empty, as soon as the queue is full and you haven't got any fallacy matlab if you haven't got any difference greater than 1 or less than 1, it is not 1, so you should return true, else you should return false if you have got the fallacy. Right, I hope this approach is clear, and now let's see how the code of this particular question looks like. So here's the function signature, that is pairwise consecutive we need to calculate, and we are given an input queue. So how we have made this particular queue is, let's say I've initialized the queue of integers and I've pushed the elements 4 5 minus 2 minus 3 11 10 and 5 and 6, and I'll be checking for pairwise consecutive of queue. If it is yes, then if the answer comes out to be true, because the return type is boolean, so if the answer comes out to be true, I'll print yes. If the answer comes out to be false, I'll print no, and I'll print all the elements of the queue side by side. So let's see what we did in our particular approach that we discussed. The first thing was that I was creating two different stacks, stack A1 and stack A2. So let me create my first stack of integers A1, and I'll be pushing in until my queue is empty. I'll be pushing in A1 dot push q dot front and then q dot pop. Right now I'll create my stack of integers to, let's say, A2, and while A1 is not empty, I need to empty the entire A1 and put the elements in A2. A2 dot push A1 dot top, A1 dot pop. Okay. After this, what we were doing is, like, now we'll be removing the elements from A2 and we'll be checking if the consecutive difference is 2. So I'll make a bool result. Initial value, let me give it as true. I'll be going inside a while loop until and unless A2 ka size is greater than 1. A2 dot size is greater than 1. Then I'll simply pop out two elements at a time. Let me say integer x is A2 dot pop, A2 dot top, right, and I'll be popping out A2. Along with that, integer y is equal to A2 dot pop again and A2 dot pop. Right now I'll be checking the difference between A2 x and y. So if at all the absolute difference between x and y is not equal to 1, then I'll put the value of result equals to false. Okay, and I'll be pushing back the elements in my queue. Push x कर दिया, q dot push y, and I think this should suffice. Is there anything else that we are missing? We have created one stack A1 while my queue is not empty. I've popped out elements from my queue and pushed them into my stack A1. Then I've created stack A2. A1 ke elements are in A2 now. I'll be popping out two elements at a time from A2 and be checking the absolute difference between them. If it is not equal to 1, I'll make the value of result equal to false, else it is true. Also, side by side, I'll be pushing out x and y into my queue. At the end, what I need to return is return the value of result. I hope this should be fine. Let's try and see if we get the correct answer. There is some expected before pop. This is something that we missed. Yes, so we're getting the answer as yes. That means our queue is pairwise consecutive. The difference between 4 and 5 is 1. Absolute difference between 4 and 5 is 1. Minus 2 and minus 3 is also 1. 11 and 10 is 1. 5 and 6 is 1. So we have successfully solved this problem. Let's try with some other example. Let's say for this case, let me do minus 2 and minus 4. What is the answer coming? So the answer is coming out to be no. Why no? Because now the absolute difference between minus 2 and minus 4 comes out to be 2, which is not equal to 1. Hence the result variable here becomes false and it is automatically returned as false. I hope this question is clear to you, and let's meet in another video and see another question. Let's also touch upon the time complexities of queues. Let's say when I say time complexities of queue, like we have different operations. These operations include accessibility, that is if I want to get any particular element of the queue. Next thing is search, if I want to search any element in my queue. Next thing is insert, if I want to insert any element in the queue. And next is delete, if I want to delete any element of the queue. So there can be different cases. Let's say we generally deal it in the form of best case or the worst case. So we'll see what will be the accessibility of a queue in best case. Like this is my queue. Let's say this is my queue. For example, I have certain elements like 1, 2, 3, 4 and 5. If I want to access any element out of this queue, so I'll have to either pop out other elements then move to that particular element. So the in the best case you can say that my element which I want to access is present at the first position only, so it will become O of 1, but will not take best case. Let me just name it as average case. In average, on average, we'll make it as O of n only. Let's say my element is here or somewhere else. In the worst case, let's say your element is at the last, again you'll have to traverse over the entire array or the entire queue. Then again your accessibility will be O of n time complexity. When I say search, if you want to search at any particular element in the queue, again you'll have to pop each and every element and see if that element is equal to the required element. For this also the time complexity becomes O of n. In the worst case also it becomes O of n, right? If the element is present at the last, let's say the element that we are searching is present at the last, again we'll have to traverse from the starting till end and we'll have to traverse over n elements. Insert, if I want to insert an element in my queue, let's say I have this particular queue, there's one, like the queue size is 6. If I want to insert an element, I'll simply insert it at the back, at the rear end, and it will take the time complexity of O of 1. In average case also, in worst case also, in best case also, there's no doubt on insertion. So what will be the complexity of deletion? When I say deletion, basically the pop operation I'm doing. So pop operation in the terms of queues is also done in O of 1 only. Like if I want to remove this one, so it is the element which is present at the front end. I know that I can only remove the elements from the front end in a queue. So the complexity in this case would also be O of 1. Here also it will be O of 1, and probably we'll be able to understand how the time complexity in a queue goes on. For space complexity, let's say what will be the space complexity of queue. So when I say space complexity of the queue, so we are creating a queue, so we can create it using an array, or we have also seen we can create it using a linked list. So it will be O of n space. We need to create this particular array of size n or linked list of size n. So we can generalize it by saying that the space complexity of, in general, like in worst case also you can say it will be O of n in general, right? I hope these complexities part is clear and you have practiced a lot of questions related to queues so that your entire topic can be covered. It's a very important topic from the point of view of interviews. Majorly a lot of questions related to dequeue. Dequeue is a very important topic. Like we have discussed so many problems related to dequeue, so make sure you are well versed with some more problems related to dequeue. Generally that involves sliding window, right? So you might have seen that we have done a problem in which we were finding subarray maximum. So it's a very important problem with respect to interviews. Then there was a problem by the name of rotten oranges. So rotten oranges problem is also a very famous interview problem, right? Then one question in which we were calculating the distance from the binary, in a binary matrix, from the ones and zeros. So that question is also very important. So make sure this topic is revised well. Apart from that, questions relating to BFS of a graph and tree. We have discussed the BFS of a tree in this video, but for graph also you need to use it. and if you have a sound understanding of queue, you can easily solve the problems related to BFS in trees. Like a lot of questions in tree will be based upon BFS. In graphs also, major problems are based upon BFS. So BFS is a very important topic, that is breadth first search, right? So make sure you practice these well. Apart from that, we have discussed about the time complexities. So time complexities you need to keep in mind while solving certain problems. Also, there can be some trivial problems that we have discussed, in which we were popping out elements into stack, pushing out elements in queue from the rear end, from the front end. So those questions need to be given a thought. You need to understand like what exactly is the demand of the question, and you need to supply the solution accordingly. So this is also very important thing that you should take into consideration while solving questions related to queues. Apart from that, like most of the things we have covered, so make sure you revise this video once again if you feel any problem, and try making short notes, so that once you are done with the preparation, you can just easily go through the type of questions that we have done, so that the topics are revised in a much easier and efficient way, right? So this was all for this particular video. I hope you people enjoyed learning this extensive course on queue data structure. See you in some other video. Till then, stay tuned.
Hope you all like this amazing video. For more such amazing content, consider liking and subscribing this channel. We'll be bringing some more concepts related to data structures, some more topics like cloud, some more topics like the system design, and much more on this particular channel. So please do subscribe this channel, share this video, and like this video. Along with that, if you people have any doubts, any queries related to anything, don't forget to comment in the comment box, and we'll be more than happy to take all your comments from the comment section. Thank you so much. Hi everyone, this is Recursion. Welcome back to Scalar. In this video, we are going to have a 4 to 5 hours extensive course on linked list. We'll talk from the very starting, what is the linked list, what is the need of the linked list. Also, we have discussed various aspects of operations on linked list, like insertion, deletion. Along with that, we have solved a lot of problems. We have discussed doubly linked list, we have discussed linked list STL. We've also discussed circular linked list at some point. Along with that, we have solved a lot of problems ranging from lead code to interview bit, and the topics have been very extensive. So if you're looking forward to prepare for linked list well, make sure you watch this entire tutorial from the beginning till the end. Also, do let me know if you have any queries, any problems throughout this particular lecture. You can comment them down in the comment section. I'll be more than happy to take from there. I hope you people enjoyed watching this amazing video. Also, don't forget to press the subscribe button and like this video. We have a lot of videos coming up on Scalar's channel, be it from system design to data structure algorithms to cloud technologies, and a lot more. Make sure you stay tuned and subscribe this channel. All the best. Good luck. In this video, we are going to discuss about linked list, introduction of linked list, insertion in a linked list, deletion in a linked list, different operations that we can perform on linked list. We'll also try to see some important algorithms, some important concepts behind linked list, how we can solve different questions on linked list on different platforms. This is going to be an extensive 4 to 5 hours long course on linked list, and will take you from scratch to advanced level in linked lists, right? So we'll start from the very basic definition of things like storing, right? How we store data in programming, right? If let's say I want to store a variable, so we generally store a variable in this particular format, like int a is equal to 5. So this is the format in which we store a variable in our programming, like while we are coding. Right, now let's say if I want to store a group of numbers together, let's say I want to store the roll numbers of top 10 students of your class. So for storing them, either I'll need to create 10 variables. So that will be a little tedious task. So instead of creating these 10 variables, what I will do is we already know a data structure for this, that is an array. So what is an array? Array is a basic data structure. It goes something like this. Let's say this is array. How we initialize an array? Like this int specifies that the data that we'll be putting up in our array is of integer format. Right, so this is the initialization of an array, basic initialization of an array, int arr, and in the brackets we are putting 5. So 5 suggests the size of this array, let's say. So let's say this is the array that we have. we are putting in numbers like 1 2 3 4 5 6 7 8 and 9, right? So let me index this array. 0 1 2 3 4 5 6 7 and 8. So indexing of array starts from 0, right? So this is how we store elements in a contiguous fashion. So in array gives us a privilege of storing elements in a contiguous fashion, right? So what if I say now I want to add 2 more elements in my array? So is there a possibility? And how arrays, like let's say this, how we store this particular array? We generally store the address of the first element. Let's say this address is 100, right? And an integer takes 4 bytes. So this is 100, this will be 104, this will be 108, this will be 1112, this will be 116, this will be 120, this will be 124, 128, this will be 128, this will be 132 and 136. So the next number if I want to add should be at 136th place. But I'm not sure whether this 136th place is available for me or not. Right? If I want to add another number after 9 in this particular array, so I am not able to add that number, right? So so this is a big problem. How we can solve this particular problem? So here comes the concept of what we are discussing is linked list. So how is linked list different from an array, and what actually is there in a linked list is, let's say, so now instead of saving elements in a contiguous fashion as we have seen above, what I'm going to do in this case is I'm going to, let's say I want to store 4 numbers 1 2 3 and 4, right? So I make a block and I take a particular memory block and I put 1 in that. I take another memory block and I put 2 in that. I take another memory block and I put 3 in that. I take another memory block, I put 4 in that. So I have 4 different memory blocks in my array, each having its own address. Let's say it is address 1, this is address 2, this is address 3, this is address 4, right? So there are multiple addresses that we can see in our linked list. So this is address 1, address 2, address 3 and address 4. So now if I want to add a new element, I can simply create a new element, let's say 5, add address 5. So for this kind of a structure, for this kind of a data structure, what I actually need, I need to store these addresses somewhere, right? So maybe I can maintain something in which I will be storing all their addresses, right? This is possible, right? But this will again be very tedious, right? Carrying, maintaining and storing addresses of elements somewhere. So this is again a tedious task. So I want to make it a little more simple. How can we do that? So is there a possibility in which I don't need to store all these addresses? So instead, there is a possibility. How we can do that is basically by connecting these elements. How we can connect these elements? Let's say I have 1 here, it is present at 100th location. I have 2 here, it is present at 200th location. I have 3 here, it is present at 330 location. I have 4 here, present at 450 location, right? So I want these should be interconnected. I don't want that I should store their addresses somewhere. It will take me more memory, it will take me more operations. So that is something that is not very required, right? So is there a way in which I can avoid that? So for avoiding that, basically I'll be creating something in which I'll connect this element or this block with another block, this block with another block, this block with another block, right? And I will save the address of this block. This only saving the address of this block will serve the purpose. So what can be done in this case is I want to connect all of these together. So for connecting all of these together, there is a way out, right? How that will work? Let's say this is 1, this is 2. So we'll create a structure in such a way that this memory block is divided into 2 partitions. This first partition will contain my data of the node that I have, data
that I want to store, right? And the second part will store the address of the next number that I want to store. So the address of next number is 200, so I'll store 200 here. Here it's 100. So the next node here is 330. I'll store the address of 330 here. Next node is 3. I'll store the address of next node, that is 450 here. This is 4. And now there's no node, so I'll store null here. Right? So in this way, what we are actually doing is we are connecting this 200. Now this 200 address is written here. That means I have the location of the next node. So both of these are connected now. This is also connected now. This is also connected now. Now I just need to store this address. Now if I have this address, this is the address 100. With this address, I can access any of the elements of this linked list, right? I don't need to separately store these addresses anymore, right? I don't need to separately store these addresses anymore. I can just store the address of the first element, and that's it, right? So how will be like if like now you have seen this is a new kind of a structure, right? So when I say a new kind of a structure, it's something of this particular sort in which I am storing data in this part, and I am storing the address of next node here, right? Data here and address of next node here. So is there any data type, like we already know data types like integer or character or float or double. So is there any data type that can store any of this type of a structure in which I want to have an integer number here and I want to have a pointer number here, because address is generally stored in pointers? No, so there's no inbuilt data type of such sort. So instead of that, I will be creating my own data type. So creating my own data type means I will be creating my own class. So this whole structure, this structure that contains data as well as address of the next node, next we call this as node. This is known as a node. So we'll create this class node, and inside this class node we will have two data members. This is like first thing that we want to store is data, second thing that we want to store is address. So the data here is integer data, and secondly is what we are going to do is we are going to store the next address. So if we are storing address of something, so what we generally use in storing address, we use the pointer, right? But what will come here of pointer is of what type? Let's say if you have something known as integer a is equal to 5. How we store the address of this integer? We generally store it by %a. Let's say I'm doing int star ptr, right? This is the way in which we store the address of a, right? So this is the variable, like of what type? Like I am storing the address of integer type, so I have this integer in the front. So here I am storing the address of what? I'm storing the address of the next node. So this complete node, right? So what will be the data type here? It will be node star next. So this is the basic structure of class that we will be using ahead. This is how my first linked list will be, one node of the linked list will be made. Basic structure, basic understanding, right? Now if someone says you to create a node, like this is the class that we have made, right? And once we are making a class, we need to initialize these as well. So to initialize these as well, what we do is there is something known as a constructor. As you people already might be aware, you all have studied object oriented programming, right? So constructor is required. So what will constructor do? Class node, inside this we have int data and node star next. What else we need to do is we need to create a constructor. So constructor will be something like this. It will have an argument int data, and inside this what we'll do is we'll initialize this data and this next. So how will initialize this? We can use this this data is equal to data. What is this keyword? This keyword is the keyword that stores the address of my current object. Stores the address of current object, right? This के data में I am putting this data that is I am receiving in the argument. So this data is initialized. What I'll put in the next, I'll put null initially. So this is basically how a node is created. Initially, if a node is created, let's say I'm creating a node n1. So I need to pass on the data, let's say 1. So once I write this statement in my main function, what will actually happen? A node will be created. It will have two parts. The data part 1 I am passing, 1 will be passed here, and the next variable will be initialized to null. So writing node n1 will create a new node with data 1 and next pointer as null. Right? I hope this is true. Right? So now let's just try to code in what we have written till now so that you can have a better understanding. Right? So we are here on the interview bit IDE. So the first thing that we were doing is we were creating a class node. Inside this class node, what happens is like we generally have access specifiers, be it private, public, and protected. So let's create a public data members. Int data. Second thing is node star next. Now you very well know why we are using this node star next. Next thing that we want is we want to create a constructor node int data, and I will be initializing this now. So how we are initializing this data, I was putting as data, right? And next is initialized to null. So this is what we have created, this node class. How we'll create our nodes? Let's say I want to create my first node. So how will create my first node? Node n1, and in the bracket I'll put 1. So what does this statement means? This statement here, node n1 bracket 1, means that I have created a new node with data 1 and next pointer is initialized to null. Right? Let me create a node n2 with the data 2. Right? I have created two nodes, node n1 with data 1 and node n2 with data 2. Right? Now I want to connect these two nodes. How I will be able to connect two nodes? Let's just try and see. Right? So what happened like this is we have written node n1 1 and node n2 2. So these are the two statements that we have written, right? So this statement refers that I have created a new node with the data 1 and next pointer as null. This statement means I have created a new node with the data 2 and next pointer as null. Right? Now I want to connect these two nodes. Right? I want to have a structure of this particular format in which 1 is connected to 2. How I can do that? I can do that by connecting, like this will have a certain address, right? Let's say this address is 100, the address of this is 200. So if I put 200 instead of null here, so now my first node is storing the address of the second node and second node is storing null. That means my linked list is connected now, right? So what we need to do is we need to put n1 dot next is equal to ampersand of n2. Ampersand of n2 suggests address of node 2, and we are putting the address of node 2 in my node 1's next. Right? I hope this is clear. So I just want to do this, and let's just try to print after that how it goes. Right? So I have node 1 and node 2. What I did there was n1 dot next is equal to ampersand n2. Right? And now let's just print cout n1 dot data, n2 dot data. Right? So this is what we have done till now. Class ends with a semicolon, and now try to run this. So yeah, we have successfully executed the code. We have two nodes coming ahead, that is 1 and 2. Right? I hope this is clear to you. Great. So now we'll try to see something else, like we'll try to create more number of nodes, and so that you can have a better clarity. So now that we have talked about, we have seen how we can output, we can print n1 dot data and n2 dot data, right? So now I want a thing in such a way that I don't need to know both the nodes of this linked list. I just have one pointer through which I can access the entire linked list. So now currently my linked list looks something like this. It's n1, it's n2, here it's data, here it's address of n2, here data of n2, here it is null, right? So in this way, this is the format of how a linked list would look like, right? So now what if I store the address of this particular node in a variable known as head? So this variable, this starting node of my linked list is known as a head variable, and I'll use this head to access the entire linked list. So this head can be like head. What will this heads next represents? Heads next represents the second node. What will be heads next? So what will be this? This will be the third node, and so on. In this way, we can access the entire linked list using the head. Let me just show you in the IDE that how we'll be doing this. Right. So now we have created node n1. Let me create something as node star head that is equal to address of n1. Now I'll be printing the data using this only, right? How we'll do that? We'll do heads data and head के next का data. Let me just try and print if it is working all right. Yeah, so we are getting 1 and 2 again just by the first node of the linked list, right? So now we have discussed this. Let me take you to some point where we create multiple nodes and we try to print all these nodes in a linked list. So how will we be doing that? So let me just I just want to let you know what I am actually trying to say, right? Let's say there are multiple nodes, that there is n1, there is n2, there is n3, n4, n5, and I want to print all these nodes. How I'll be printing? And I have just this head of the linked list, right? This, let's say we have this particular linked list and this is null. Address of 1 is 100 and 100 is stored in my head pointer, right? So now using this head, I want to print this entire linked list. So what will be the steps that we can follow? There can be multiple steps, there can be multiple ways. So if I want to print this particular linked list, so the first thing that I will be printing is 1. So how we can print 1? We can do cout heads data, right? Cout heads data. After we have done cout heads data, the next thing after this is what we'll do, we'll move head equals to heads next. So what we are doing in this particular line is, like, initially the value of head is 100, right? Now we have moved the value of head to heads next, right? So the value of 100 changes to 200. That is the address of 2. Let's say it is 300, it is 400, it is 500. Now we have done this, we have used this particular line. Now we are at second node, right? Now again, if we print heads data, here the output was 1. Now again, if we print heads data, the output will be 2 in this case, right? Again, what I'll do, head is equal to heads next, right? So this 200 will change to 300. Again, if I'll print heads data, it will give me 3. So in this way, we can print the entire linked list, right? So let me create these 5 nodes, connect them together, and we'll try to print it using a print linked list function, right? You will understand it a little more better when we'll code it on screen, right? So what I'm trying to say is, like, we have already created node n1, we have created node n2. Let's create node n3 as well. Node n3 with data 3, let's say,
node n4 with data 4, node n5 with data 5. Right now what I want to do is I want to connect these nodes together. So connecting these nodes together means n1 के next में what I'll put address of n2, right? This is something that we written again. Similarly, we'll do it for other nodes as well. Sorry. Right? So here it will be n2's next will have address of n3, n3's next will have address of n4, n4's next will have address of n5, and we are done. Now we have head variable, head pointer, that is storing the address of my first node. So I'll simply call upon a print linked list function that, and I'll pass head in that function. Right? Now I need to create this print linked list function. Let me just remove these two lines of code as well. So yeah, let us create this void print linked list, and I'll be passing node star root. Let's say this is the head that we are passing on, right? Let me just call it as head only. Right? So after this, what I'm going to do is, the first thing going here, what we'll do is I'll put a while loop. I'll say while my head is not equal to null. So the first thing I'll do is I'll see out heads data, right? And I will do head is equal to head arrow next. So what does this line represent? See out heads data. So firstly we have passed head, that is we have passed this first node. So it will check if head is equal to null. No, it is not equal to null. It will move inside, it will print heads data, that is 1 will be printed. It will change head is equal to head arrow next. This is what we have seen here. Head is equal to head arrow next every time we are doing, and the address of the next is stored in the head. Now again, second time 2 will be printed, then again head is equal to head arrow next, 3 will be printed, 4 will be printed, and 5 will be printed, and we'll finally have the printed linked list. Let me just try and see if we can print the linked list using this. So yeah, you can see that we have successfully printed 1, 2, 3, 4 and 5. So this is that the function is working, right? Let me just do one thing. Let me just copy this function and paste it here. So what do you think will happen? Just pause the video and think. Yeah, I hope you have thought on what will happen. So now as we are changing head every time, we are changing head, we are printing the data of the head, and we are changing head is equal to head arrow next. So once we are out of this loop, our head is pointing to null. So now if head is pointing to null, this will not go inside this loop and will not see any difference in the output. So our linked list will not be printed twice but once. Why? Because our head will be null at this point. So but this is really wrong, right? We need to use this head. We might need to use this head multiple times throughout our function. So instead of using our head directly here, let me just pull it down. So instead of using our head directly here, what I'll do is I'll create a temporary node temp is equal to head, and I'll perform all operations on this temp. While temp is not equal to null, see out temp's data, and temp is equal to temp arrow next. So this is what we need to do, and I hope this will also be printed. So in this way we have successfully printed our linked list, and I hope you are clear with the basics of linked list. Now we'll move on to some other concepts of linked list, right?
So now we have seen how we use linked list, how we print a particular linked list. Now let's move on to some operations that involve linked list, right? So if we are to do some operations, let's say insertion to begin with, if we are to insert something, let me just, yeah. So for insertion in a linked list, so what is going to happen? Let's say you might know the case of an array, right? If we are given an array of such a form
in which there are certain numbers like 1, 2, 3, 4, 5, 6, and so on, right? And like these are the indexes 0, 1, 2, 3, 4, 5. If let's say I want that you should insert a certain number 70 at index 2. So what you will do in case of an array? So we very well know that in case of an array, I'll have to make this space vacant so that I can add 70 here. So for that case, we need to move all these elements that are after second index. We need to move them one place back. So that involves transferring this to this, this to this, this to this, this to this, and this space becomes empty. We'll add 70 here, and we have inserted an element. This is something that is considered to be a negative point in case of arrays. So if we are talking about linked lists, right? So we have seen what are the advantages of linked list. So how will this process of insertion go like in a linked list? So linked list is something like 1, 2, 3, 4, 5, and null. So let's say we have this linked list and I want to insert same thing, want to insert 70 at index 2. So let's just name the indexes. This is 0, 1, 2, 3, 4, and so on. So this is the second index. We want 70 to be inserted here. So for that matter, and what like generally for a linked list, what we are given this head that points to the address of this first location, and we want to insert 70 at the second index of the linked list, right? So this is to be done. So what we can do in this case is, let's say we will be shifting the pointer, the next of this first node, like the node that is just before this index, to the address of my new node, and the next pointer of the new node to the next pointer of my previous node. So this is the very general overview. We will go in depth of how this everything is happening. Let me just take you to a new page, right? So yeah, so we want to insert, now we want to insert a new node in linked list. Let's say we are given an example. Let's write it very neatly. 1, 2, 3, 4, 5, and null. What we are given is head. Let's say the head initially is like the address of this is, let's say it's 100. So let's say the head value is 100. What we are given is, we are given a certain data that we want to add. Let's say we want to add 70. We are given a position that is ith position, that is the second position. We want to add 70 at the second position, that is if we index them. Let's say if I index it as 0, 1, 2, 3, 4, right? So I want to insert data 70 at second index. That is, my linked list after insertion should look something like this. It should look like 1, 2, 70, 3, 4, 5, and null. This is what I want. This is my final output. So how can this happen? Okay, so we have already discussed like what happens in a linked list. Basically a linked list node is of this form, right? A node has something known as data and something known as next pointer that stores the address of the next index. Now this node, let's say 1 will be having the address of 2, 2 will be having the address of 3, 3 will be having the address of 4, 4 will be having the address of 5. Let's consider these two nodes, right? Let's consider node 2. Let's consider node 3, right? If this address is 100, let's say we consider its address as 200, it says 300, 400, and 500. So 1 will be having the address of 2, that is 200. 2 will be having the address of 3, that is 300, will be lying here. 3 will be having the address of 4, that is 400, will be lying here. Now what I have been told is, I have been told to add a node 70 here. So to add a node 70 here, first thing is, from this head I need to move to this place, a place one less than my index value, right? So I need to reach this place. First of all, the first task is to reach this place. This is one thing. What will I do after reaching this place? I have been given this data. I have to create a new node with this data, right? So if I was to create a new node with this data, so how the new node looks like? New node is something like, this is my new node, data is 70 and address we don't know, so it is null. So I've created my new node and I want to insert this new node in between both of these nodes, right? So till now, what things we know? We know one thing, that is we need to create a new node with data, right? Second thing is we want to travel till the one index less than my given position. Travel till one index less than the given position. So how we'll start writing the code, right? Let me just take you to the IDE so that you can get some better insights. Okay, so this is our IDE. What we have done till now is we have created a node, we have printed that node, printed a linked list, and we have a certain linked list. Like this linked list is currently having these nodes 1, 2, 3, 4 and 5. So this is the current linked list that we have right now, right? So what I need to do is I need to create a new function so that I can insert a new node. Let me just create a new function by the name of insert node. So what this insert node function will be having? So the first thing that so as to perform anything on any linked list, we need to have the head pointer of that linked list. So one head will be passed. Second thing that is passed is int data. What is the new, what is the data that we are going to add as a new node? Third thing is int I. So I stands for at which position I want to add the data. Let's say I want to add 70 at the second position. So if I want to add 70 at the second position, my data value will be 70, I value will be 2. This is what we have passed as our arguments, right? Okay, so let's see how we'll start with the things. We just know some part of the thing that we are going to do, right? So first thing that we are going to do is we are going to create a new node. So how to create a new node? Let me just name it as node star new node, and what are the parameters? That new node, and inside this node I'll put in my data. So this line creates a new node. This line creates a new node of this particular format. Data is here and this is null. So this is what we have done by writing this particular line, right? Next thing is we know we don't prefer writing head. Instead we use temporary function, temporary node that will work as our head. So let me just start with the node temp is equal to head. Rather than doing anything, any operation with our original head, we try to maintain a temporary variable, temporary node that points to my head and will do all the operations on this head, right? So now first, after creating this, I need to reach to a point. I have this linked list 1, 2, 3, 4, 5 and null. So I want to reach to this point if I want to insert my number at the second index. So yeah, for this reaching, what we'll do? So we'll use a while loop. While let me just maintain a variable count, which value is initially 0, while the value of count is less than I minus 1. I minus 1 suggests that a position that is less than the actual index, right? Because we want to go to one node previous to that index, right? So what we'll do inside this loop is we'll do temp is equal to temp arrow next. That is, we are going to the next node every time, and we are increasing the value of count, that is count plus plus. So what this function is doing, right? So let's just take this example as only. Okay, so what we have done till now,
So we have been passed a linked list, like this is the head of the linked list. This point, the head points to this. Its address is 100, its address is 200, 300, 400, 500. The value of initial head is 100. What we do, we create a new node by the name of data. I have created a new node. Let's say its address is 800. Data that we have passed is, let's say, 70, and this is initially null. This line is done. Now we have created a new node that is temp that points to my head. So instead of this, I have created a new node temp. Its value is also equal to 100. I have made a new variable count. Its value is equal to 0 initially. I am checking this condition, and the value of I that we have passed is 2 here. If count is less than 2 minus 1, is count less than 2 minus 1? Yes, it is 0. It is less than 2 minus 1. We'll go inside and we'll make temp is equal to temp arrow next. Temp is equal to temp arrow next. So 100 will be changed to 200 and value of count will increase to 1. Now again we'll move into the while loop. 1 is 1 less than 2 minus 1? Is 1 less than 2 minus 1? So what is there anything that we are doing wrong? Let's just see, right? So now we have temp is equal to head, while count is equal, the initial value of count is 0. Now we have increased value of count to 1. Now if we move on to this while loop again, so what will happen? The value of count is now 1. I minus 1. So what is the value of I? I was 2. 2 minus 1, that is 1. So we'll not go inside this loop. We are simply here only. So do we need to add this on this location? Are we planning to add our new node at this position? No, right? We want to add at this particular position. So we will be using count is less than or equal to I minus 1. Let me just type in here. There is something that we are missing, right? So while count is less than or equal to I minus 1, we are doing the same things, and we have reached till here. Like if the value of count is less than or equal to I minus 1, so now count value is 1. Again 1 is less than or equal to 2 minus 1, that is 1. So we'll move inside the loop. We'll increase the value of temp to 300, but increasing the value of temp to 300 will make it here, right? And that we don't want. We just need its value till here, 200 only. Why? Because if we have the value of temp 200, then we can simply put in the new node at this position and this node at this position. So we don't need to go inside the loop. We just need to have 200 in its place. So will not do this equal to sign, right? This is actually wrong. So it will be count less than I minus 1. Let me just explain it to you once again in that page so that you can get a better clarity what we have done, right? Let's just yeah. So yeah, this is what we were doing. We've had this linked list 1, 2, 3, 4, 5 and null. We have head that is pointing to 100. This is 100. This is 200, 300, 400, 500. We want to add a new node with the data 70 with the value of I that is at second position we want to add. This is currently what we have, right? So what is the first step that we did? We created a new node. I created a new node. New node is of this form. It has the data 70 and the next as null. Let's consider its address as 800. Now this is what I have. Now I created a new variable that is temp. The value of temp is initially equal to head, so it is 100. So what I am doing is I am maintaining this loop while count is less than I minus 1. I am doing temp is equal to temp arrow next and count plus plus, right? ठीक है जी? तो initially the value of count is 0
So I'll check for if count is less than I minus 1. If count is less than I minus 1, that suggests that 0 is less than 2 minus 1, that is 1. That's true. We'll go inside the loop. We'll make temp is equal to temp arrow next. Temp key value changes to 200. Right now temp value is 200, that is I am here. Right, and the value of count increases to 1. As soon as the value of count increases to 1, we'll again check for this while loop. Now 1 is not less than 1. We'll not go inside the loop and our thing is done. We just want to be here. Now we are here. We have reached till this point, or the one index less than the actual position, and this is 0 1 2 3 4, right? We want to insert between 2 and 3. So we have reached till here. We have a new node 70 and we want to insert it here. So what can be the possibility? We can simply put can we do this like temp के next में we can put this new node, right? Can we do this? Like if it is, let me just create it once again so that you can get some more clarity with addresses. Right? If you have something of this sort, ठीक है, यहाँ its address is 100, its address is 200, it's 300, it's 400, it's 500. 200 is stored here, that is the next address. 300 is stored here, that is the next address. 400 is stored here. We want to insert a new node that we have created. Its address is initially 800, its value is 70, and this is pointing to null. We have reached till here. Now temp points to 200. Temp is currently pointing to 200. And now we want to insert. So the one thing that we can do is we can remove this 300 and we can add 800 here. That makes this connection, right? But as soon as we do this, we lose this 300. We don't have the rest of the linked list available, so we'll not do this. What we'll do this before making this connection, I'll do one thing more. I'll store this 300 somewhere, right? I'll create a new pointer that is node star A, and I'll store this 300. Node star A will contain my temps next. So now this value is safe. This 300 is safe in this node star A. Now what I will do is, now I can do temp ka next is equal to new node. This line makes this 300 to 800, and now this new 100, this new node's next should point to this. So this address is stored in A. So what I can do is I can do new nodes k next is equal to A. So these three statements we need to perform in order to insert this node. Also one thing more, like instead of saving the address here, what we can do is we can do this in two statements also. So doing this in two statements is of this particular form. Like rather than first making this connection, if we make this connection first, right? So what I will do in this case is new nodes next should contain temp ka next, right? This will be of this will be like let me just take you through it once again. This is 300, this is 300, and what we are doing is this is null. So I'll not make this connection first, I'll make this connection first. So I'll put new node ke next mein 300, new node ke next mein temp ka next. 300 is stored in temps next, temp is here, temp ke next, right? And once this is done, what we'll do is we'll do temp ke next mein new node. That is, this 300 will be cut to 800 and this connection will be made. So we can also do it in 2 steps. We can also do it in 3 steps, right? Let me just take you to the code part and then you will understand it better, right? So we are here. What I want to do is I want to write 3 statements. Node star A is equal to temp arrow next. That means it is storing, it is saving that thing. Next is new node
सॉरी temp के next में is equal to new node is equal to new node and new node's next will be having a.
So these three statements will solve the purpose or serve the purpose, right? Let's just try and see if this is working and how it goes, right? So we initially created a linked list that is having 5 nodes, 1 2 3 4 5. They all are connected to each other. We are printing linked list using the head, right? Let me just try and run if to see if it is working. So yeah, this is working fine. We have got 1 2 3 4 5 as our output. Now what I want to call this function insert node. So insert node and 3 arguments, right? We are passing on head. We'll pass on this head. We'll pass on the data. Let's say I'm adding 70 and I, that is the second position. So these 3 things I have passed. I'm again printing my linked list. Print linked list, and I'm again passing the head. So we'll check if this insert function is working correctly or not. Before that, let me just call cout endl. So yeah, we have 2 linked lists, 1 2 3 4 5. 70 is inserted at the ith position and we are done. So we have successfully inserted a new node in our linked list, right? Now let me just try out something else. So instead of 2, let's say I make 7, make it as 7. So now you can see we are getting a runtime error. Why we are getting a runtime error? Because 7th index does not exist. We have a linked list with only 5 nodes. So how this operation will be performed, right? Let's just see this. So what we are doing in this case is we have this linked list 1, 2, 3, 4, 5 and null. I am passing on the head. It's going to temp. Its value is, let's say, 100, 200, 300, 400, 500 and initial value of temp is 100. New node I have created. The value of new node is 70 and it is null, right? This is something that we have in our hand currently. Now I'll check for the value of count is 0. I'll check if while count is less than I minus 1. Now the value of I is 7, right? 7 minus 1, that is 6. Yes, count is less than 6. I'll go and make temp is equal to temp arrow next. It will become 200 and we'll do the value of count. It was initially 0. We'll make it 1. Again, I'll check for the value of count. Is it less than 1? Yes, it is less than 1. I'll make it as 2. I'll increase the value of temp to temp arrow next. That is, it becomes 300. The value of count becomes 2. Again, this happens. We'll check if 2 is less than 6. Yes, 2 is less than 6. What I'll do, I'll make the value of temp is equal to temp arrow next. It will become 400. 2 becomes 3. Again, we'll check. It again goes. We'll make it 500. Again, it will become 4. Yes, 4 is less than 6 again. We'll make 500 as 600. Will we make 500 as 600? No. We'll make it as null because 5 ke next mein it's null. So the next time we have the value of temp as null and we are accessing null is the next. So null's next is not defined. It will give us a segmentation error. So to solve this purpose, what we'll do is we'll make a check. We'll make a check until and unless temp is not equal to null, then only we'll perform this thing. So what we are going to do in this case is we are going to make a check and temp is not equal to null. So if this condition is there, then probably we'll get to our answer. Here also we'll make the same check. If temp is not equal to null, right? So we have finally checked this edge case also. Okay, if at any point we pass on a number which is out of the size of the linked list, so what will happen? So now we'll try to run. So yeah, you can see we have the same linked list, 7th position we don't know only, so how we'll add anything there, right? So this is something that we have solved right now. One thing more that I would like to stress upon, if I pass on my position as 0, right? Let's see. So your expected output should be, according to you, it should be 1, 2, 3, 4, 5. This is the current linked list. So if I have 0th position, so it should be like 70, 1, 2, 3, 4 and 5. Null, right? Let me just try and run to see what happens in this case. So now in this case, you can see 70 is being added at the first position. So why this is happening? Right, let's just try and see why this is happening. Now if I am passing head 70 and 0, so head data is 70, I is 0. So first thing what we are doing is we are creating a new node. We have created a new node already, 70, and this is null, right? Now we are creating time count value is 0. We'll check if count is less than I minus 1. So what is I? I value is 0. So we are checking if we are checking for the first condition, that is count is less than I minus 0. So this is wrong, right? 0 is less than minus 1. This is wrong. So we'll not go inside this loop. We'll directly go inside this loop. So what happens here is we'll create a new node, that is node star A is equal to temp ka next. So temp's next is, that is 1 ka next, that is 2. So A will be having A's next, that is 200. A will be having 200. Now temp's next is equal to new node. Temp's next, that is 1 ka next, will be equal corresponding to this new node. So 1's next will correspond to 70, and we'll do new node's next is equal to A. So new node's next will point to this. So my linked list according to our code will look something like 1, 70, 2, 3, 4 and 5. But this is wrong. So we need to make a separate check. If at all the value of I is equal to 0, what I need to do is I need to simply put new nodes next is equal to head. If I simply put this new node ka next is equal to head, matlab 70 is next, I point it to this and I make this new node as head, then it will serve the purpose. So let's try and see in the code how it looks like. So we'll make this check first of all. If I is equal to 0, what I will do is I'll simply put new node k next equals to head. Then head should point to the new node, right? This is what we need to do. But in this case, we have changed the head itself. That means in our original linked list, the head was something different, but we have changed the head here. So rather than using this, we'll try to return our head, return our new head. So if we are returning something, so this will also change. It will change to node star, right? And also for this particular function, nothing is going to be changed. We just need to return head. Everything else is remains same. Here we need to change our head, and I think we are done. Right now we are again passing 70, 0 and head. So now 70 should come at the first position as per our code. So yeah, 70 is coming here and we have successfully solved this problem. So this was basically how we are inserting a number at ith position in our linked list, right? Now we'll see some more operations on linked list. So now we have seen one operation, that is insertion. Now let's just talk about deletion. Right, if you are given a linked list, let's say of this particular format, 1, 2, 3, 4, 5 and null, and somebody asks you to delete a node from this linked list, right? They give you the position of the node to be deleted, similar to what we were doing in insertion. So position में जैसे तुमको दे दिया है उन्होंने let's say 2, right? So you want to delete the node at the second position. So to delete the node at the second position, that is, this is the first 0th node, first node, second node, third node, fourth node. That means you need to delete this node, that is third node. So what we simply will do in this particular case is, let me just make it like this. We have something like 1, right? We have something like 2, 3, 4, 5 and null. Right? So let's say the head is 100, it is 200, 200 will be stored here, 300 will be stored here, 400 will be stored here, 500 will be stored here, and null will be stored here. We want to remove this node. So what we simply will do is, rather than making the second node, that is 0, first, second, third, fourth, the first node to point to 3, we'll make it point to this, and we'll explicitly delete this. This is what we are going to do, right? So what the first step in this case would also be, we'll traverse till the I-1th node. Second thing is, what we'll do, we'll first of all, we'll make a new node, let's say node star A, and inside this node star A, what I'll store temps next. That is this address. I'll store 300. I'll create another node, that is node star B, and inside B I'll store A's next. So A's next is, that is 300's next, that is 400. So in B we have 400 now, in A we have 300 now, and what we want is, we want to put 400 here. So what we'll do is, we'll do temps next is equal to B, and these three steps will finally delete this node. This will start pointing to this, and this will be explicitly removed. If we have made the nodes as static, then we don't need to do anything. If we have made the nodes as dynamic, then we need to use a delete keyword and delete them explicitly, right? Also, one thing more, like how we'll handle the case of if we give the node position as 7. Same, we'll check for if temp is not equal to null. This is the condition that we checked in insertion also. One thing more, if the node position is 0. So what we simply will do in this case is, head is equal to head ka next. This is what we'll do in this case when the position given is 0. Right, let me just take you to the code and see how it works. So yeah, so this is the code for insert node. I'll see if we can just make some modifications in this code only, and we'll get to our answer. Right, I'll copy and paste this entire node once, this code once again. Instead of insert node, let's just name this function as delete node. Now I'll not be having this data part, I'll just have the position of the node, right? I don't need to create any new node because I'm deleting a node. I'll make this temp variable, point this temp to head, count variable will also be made. For this 0th position, for if a node is at the 0th position, what we were doing, right? If this is the case, this is the linked list, and we want to delete the node at the 0th location. So this is initially pointing to head. So we'll simply do head is equal to head arrow next, right? And we'll return. So we'll rather than doing this, what we'll do is, we'll remove these two lines. I'll do head is equal to head arrow next, and I'll return head. Right, this will remain the same because we are moving on to the I-1th loop. Once temp is equal to I-1th loop, these three steps are what I am going to change. So node star A will be equal to temp cut next, right? Node star B will be equal to A ka next, and in temps next I am putting B. That's it. Right, so what I'm doing in these steps is, in these three steps, what we are doing is, like we have this case 1, 2, 3, 4, 5, 6, and null. This is 0th, 1st, 2nd, 3rd, 4th, 5th position. I want to remove this, delete the 2nd node, right? So now temp is pointing to currently this, and the value of temp is 200 now. Its address is 300, its address is 400. I am doing node star A is equal to temps next. So temps next is now storing 300. So A will store 300. B will store A's next. So A is 300. 300's next is 400. So B will store 400. And temps next will point to B. That is this 200. This 2's next will start pointing to this 400, that is B. So simply this will be removed, and I hope this should work, right? Let's just try and run this code. This is delete node. Let's just create one more function, that is delete node. Let me insert head, and let's say we'll remove this 70, right, the 0th location one, and then we'll do the same printing, right? Let me just run this code. So yeah, the 70 is removed. That is the node that was at 0th position, that is now removed. Something more we can try, rather than 0, we are removing the node at the 2nd position now. So now the node at the 2nd position, that is 2 is removed, 0th, 1st and 2nd, the 2 is removed. Let me just make it as 7. 7th is the index that does not exist. So we'll check if that condition, that case is handled. Yeah, that case is also handled, because 7th is not the position in this linked list, and that we can't delete anything. So I hope this was also easy, and you have got a pretty good idea of how to insert a node in a linked list, how to delete a node from a linked list. Let's see some more things in linked list going forward. So now we have seen insertion as well as deletion in a linked list. Now that was without using recursion. Now recursion is a very important concept, and going forward we'll be using recursion to solve problems related to linked list in many ways, right? So I want you people to understand how we can insert or delete a node using linked list, a node in a linked list using recursion. So this is something that I want you to understand now, right? So what happens in recursion? We will basically be looking forward to 3 things in a recursion question, that is a base case, a small calculation that we perform, and a recursive call, right? So let's just take one example, the same example that we were taking for so long. 1, 2, 3, 4, 5 and null. So this is the linked list that is given to us initially. Now I have 2 things, that is I have data. Let's say I want to add a node with data 70, and I, that is position is 2. I want to add a node at position 2 with data 70. This is 0th index, 1st index, 2nd index, 3rd index, 4th index, right? So I want to add the node 70 here. That is my node should my linked list should look like 1, 2, 70, 3, 4, 5 and null. This is what I'm looking forward to, right? This should be my output, right? So how we'll go forward doing this particular question is, so what happens in a recursion question? So whenever we are given a recursion question, we first think of the base case, right? This is the linked list that we initially have. So what will be the base case? Let's say if the head is only given to us as null, if at any point head is equal to null, so we can simply return null. What we'll add in a null linked list, right? We don't have any position to add in that linked list, so we'll simply return null. So this will be my base case. Also, what happens in any recursion problem is we try to break the problem. We try to break it in such a way that we have a smaller part and there's a large part. So let's just try breaking it in this way, so that we perform on this smaller part and recursion gives us the answer by automatically doing the things for the rest of the part, right? So now if this is the linked list, right, this is the part that we are concerned about, that we will have to perform a small calculation on, and this is the part that recursion will help us to, like if there is something to be added in this part, then recursion will give us the answer, right? So what we'll focus on while solving this particular problem is that, for one, right, so we want to, if we want to add any node at the first position, so what will happen, right? So if the value of I is equal to 0, that is I want to add the node at the 0th location. So what will be my steps? So first step is, if I want to create a new node with data 70, I'll create a new node. So first step is creating a new node, right? After that, what would be the step? I will add the new node at 0th position, right? So my first thing is I'll create a new node, that is node star new node. I'll do new node with data 70. Now I have this new node. So at ith position, what will happen? We'll simply do no new node का next will point to head, right? We'll make a new node and we'll make it point to head. Second thing in this, what we'll be doing is we'll be updating our head. Now our head will be equal to new node, right? My head points to this and will return head. So if we are to add any new node at the 0th position, so these are the 3 steps that we'll perform, right? Yeah. So after this, we need to call on recursion, right? But like this is what we will do if we are to perform at the 0th position. Now we are to perform at the 2nd position. So we'll want recursion to do that. We'll make a recursive call, that is delete recursive. Insert recursive, and we'll pass on 3 parameters. So which parameters? Firstly, instead of head, now what we'll pass on? We'll pass on head ka next, because we are passing the entire linked list except the head. So we'll pass on head ka next. We are breaking our problem basically, right? Data will pass as such that we want to add, and now the position, right? If let's say I have 2nd position, so this is 0th, 1st, 2nd, 3rd, 4th. So this would be my 2nd position in that case, right? But now this part is already done by us. Now I'm passing this particular node. So for this particular node, what will be? So these will be the indexes 0, 1, 2, 3. So in actual, we want to add at the 2nd position, but in our new node, it is the 1st location, that is I minus 1, 1 less than 2. So that is, we'll pass on I minus 1 here. And after this, we'll store it in a new variable, that is node star x. So this x will give me updated linked list with addition of 70 here. So this x will have now 2, 70, 3, 4, 5. Now x is having this. Now the last thing that we need to do is we need to connect our head with this x. That is heads next should point to x. Now we have our complete linked list with head as the operated head, and we'll simply return this head. Let me just explain it to you once again in a little more simpler way so that you can get an idea. So what we're actually doing in this particular question, we are to add a node in a linked list using recursion, right? We are given this linked list. We are given head is here initially. We are given the data as 70, I as 2. That is, we need to add a number at the 2nd position, 0, 1, 2, 3, 4, right? Now first is base case. So we have seen that base case would be if head at any point becomes equal to null, so we'll simply return null. Small calculation is like, I'll do the small work. We'll break the problem into 2 parts. This part will be handled by recursion. This part will be handled by me. That is, if at all the position is 0, then what I'll do is I'll create a new node. Right? This new node will be created. What I'll do for this particular case is I'll do new nodes next is equal to head, right? And I'll update my head equal to new node, and I'll return this head, right? These 3 things I will do. What after this? So we have done this, we have performed the base case, we have done the small calculation. Now it's the time for recursive call. So what happens in a recursive call is, so now it's the time for recursive call. Insert recursive. So here are the 3 arguments. Initially we were passing head, data and I. Now what will pass? I have 1, 2, 3, 4, 5 and null. So now this is our breaking point. We have performed the operation on the first, that is the head. Now we need to pass this into our recursive function. So this will be, instead of head, will pass on head ka next. Data will be same. Now carefully observe what will happen here. Now initially it was, indexes were 0, 1, 2, 3, 4, right? So we were to add at the second position, but now we are passing this as our linked list. So its indexes will be 0, 1, 2, 3. Instead of this 2, now we have 1 that is to be passed. That is one position prior to my actual position. So we'll pass I minus 1 instead of I. I'll get this in a new node, that is node star x. I believe this x will contain my 273, 4, 5. This is something that recursion has done for me, right? It's stored in x. Now the only thing that is left is I need to connect my head with this x. Head ke next mein I want x. So I'll add on 1, 2, 73, 4, 5, and this will be stored in head. I'll simply return my head. This is how it looks like when we are performing insertion using recursion, right? Let me just take you through the code part. So yeah, let's just create a new a function, that is node insert recursive. Here we'll have node star head, we'll have int data, we'll have int I, that is the position. So the first thing that we do is we'll create a new node is equal to new node with this data, right? I've created a new node. After this, what we are going to do, if we are to perform this in a recursive manner, is the first thing that we'll do if you have to perform this in the recursive manner is we'll check the base case. If at all my head is equal to null, then what I'll do is I'll simply return my head, that is null, right? After that, so we are to perform the small calculation for a case if I is equal to 0. If the value of I is equal to 0, then what we are going to do is we are going to attach this new node in the front of my linked list. So new node ka next is equal to head. We'll update this head also. Head is equal to new node, and I will return head. These are the things that we are doing for our case. Next is the recursive call. I'll get the answer of this recursive call. What are the parameters that I'll pass on? I'll pass on heads ka next. I'll pass on the same data, and this is very important, I minus 1, right? Now we have x, we have head, so I simply need to connect head ka next is equal to x, and I will return my head. I hope this should be fine with you. So let's check if this is fine. What we are actually doing is we are creating a new node. This is like, this node is being created 70 and null by this particular line. We are checking for if the head is equal to null. This is the base case. We are doing the small calculation for this part of my linked list. For this part, I am doing this work. If I have to add a node at the front location, then I'm passing on the entire linked list in a recursive call. Instead of head, we are passing head ka next. We are passing the same data. We are passing I minus 1. I minus 1 means the position that is prior to the actual position, because we are passing head ka next, right? So now this x will hold on by adding the number at this particular position. I'll simply connect this head ka next equal to x and will return this updated head. So this is how we perform insertion using recursion. Let me just see if this runs well, right? Insert recursive is what we need to call upon. So instead of node, insert node, what I'll do is I'll call upon insert recursive. So let's see if it adds upon, instead of 70, let's say I give 69 this time. So yeah, you can see 69 is added at the 4th position. Let me just change this index to 0. 69 is added at the 0th position. So recursion is able to help us in inserting a node in our linked list, and the code looks a little more simpler, right? So let's just see how we can perform deletion operation using recursion, right? We have already seen deletion using our normal method. Now we'll try to see deletion using recursion, right? Yeah. So now what we have is, it's very similar to what we have seen in the case of insertion. We have this linked list and somebody tells me to delete the node at the ith position, that is 2nd position. So this 0, 1, 2, 3, 4. So somebody tells me to delete this node. My linked list should be, the output should be something like 1, 2, 4, 5 and null. This is the output that I want. Right now currently I have this. So how using recursion we can do this? So again, we'll have three things in recursion. So which all 3 things we are concerned about? First is base case. Base case is, we'll check for if my head is equal to null. If it is, we'll simply return null. Second thing is small calculation. So what will be the small calculation? That is if the value of I is equal to 0. That is if I want to remove this head. What I will do is, I'll simply do head is equal to head connects. That is, my head will start pointing to here and I'll return my head. This will be my small calculation. What will be my recursive call? So recursive call will be, I'll take a variable, I'll take a node x, node star x, and inside this node star I'll call recursive, that is delete recursive. I'll pass on 2 parameters, that is, I'll pass on this part of my linked list, that is head connects. Instead of I, again we are passing I minus 1. I hope now this is clear why we are passing I minus 1, not I in this case. Right now we have X also, we have head also. We need to connect both of these. What we'll do is head connects equals to X and return head. This is what we are looking forward to do in this particular question. Let me just take you through on how we will be performing the deletion operation. Right, let's just try and see if we can copy paste this only and make some changes to get the answer. It will save your time as well as my time. So instead of insert recursive, I'll use delete recursive. We should pass head. We don't need data this time. We don't need to create any new node this time. We'll simply check for the base condition will remain the same. For value I equal to 0, we'll remove all this. What we simply need to do, head is equal to head connects. We have simply removed the first node. I'll return head again. Right now we'll call upon the X, that is delete recursive. Here it will become delete recursive. I'll pass on head connects. I'll remove this data as a parameter. I'll pass on I minus 1. Head connects me, I'll put X and I'll return my head. This will be the perfect function for delete recursive as well. Let's just try and see if we can how it goes here. So instead of insert recursive, what I'll do here is delete recursive. Head is same, 69 is what I need to remove. I want to remove the number that is present at the 0th location. So let's see how it goes. Yeah, so we have successfully removed 69, that is the number at the 0th position. Let me just change the index to 4, 3. So we have removed the number that is present at the 3rd index, that is 0th, 1st, 2nd, 3rd. 3rd index is 3. So we've successfully removed the number that is present at the 3rd index, and these both are working super fine. So we have been able to successfully insert as well as delete elements from a linked list using the normal operation as well as using recursion. Going forward, we'll be solving a lot of questions using recursion. So make sure you do these questions on your own. Make sure you use a copy and pen and try to dry run these approaches so that you can get a better clarity on how you can get inside this very interesting topic of linked list, right? So the next thing that we're going to understand is basically calculating the length of the linked list, right? We are going to see how we calculate the length of linked list.
So let's say we have this particular linked list 1, 2, 3, 4. And we'll try to see the recursive solution for the same. Right? So what happens is, in a recursive solution, we need to check for the base case first. Right? So base case would be if the length is equal to 0. If the value of head is equal to null, that is linked list does not exist, we'll simply put length is equal to 0, else we'll break it here, and this is something that will pass on in the recursive function. That means our recursive function will return the length of this part, and we'll have to do this small calculation, like what for this part we'll have to calculate. So for this part, what is the answer? Like it is of length 1, so we'll add 1 in this. So overall it would look something like length function, and we have node star head. So what we'll do is we'll check for base case. If head is equal to null, we'll return 0, and we'll simply return 1 plus, we'll call the recursive function and we'll pass head connects. That's it. This will give us the length of linked list. Right? Now there's one more thing, like I'll try to code this also, but before going forward, let's just discuss one more concept, that is how to calculate the middle of our linked list. Right? Calculating the middle of linked list. So it is very simple. Like we have already discussed how to calculate the length of the linked list. So calculating the middle is no big thing, right? Let's say you have this kind of a linked list. Right? So you have to calculate the middle of the linked list. So using the above function, you know what is the length of the linked list. So the length of the linked list is 5. Length comes out to be 5. So what you can do is you can simply find out the mid. Mid will be equal to length by 2. Right? Length by 2. That means 5 by 2. 2. So it will be 0, 1, 2, 3, 4. Right? So this is the index that will be our middle index. So we'll simply return the data that is present at the middle index. Let's say our linked list is even linked list, like the length is even. So how we'll find out the same? Let's say we have 6. Now 6 by 2 is 3 again. So we can find out by 0, 1, 2, 3, 4, 5. So the third index, that is the second middle. Now for an even linked list, we have two cases, right? It can be either the first one or the second one. So for calculating the second one, we can simply use 6 by 2 and we can return. But this is again a little bit more complex. Let's just try to simplify this. Right? So simplifying this is a very important technique that is basically known as hare and tortoise method. So what is there in hare and tortoise method is how we calculate the length of the middle of the linked list. We are given a head of the linked list. We initialize 2 pointers, that is node star slow and node star fast. We initialize them to head. Let's take this example. Now this is my head initially. I created a slow pointer, I created a fast pointer. Both point to this head initially, right? Now what I will do is I'll move the slow pointer one step at a time. Slow is equal to slow's next. And I'll move the fast pointer as fast is equal to
fasts, next, right? So in the first step, slow will come here and fast will come here. The next step, slow will come here, fast will come here, right? So for whenever fast reaches null or a number before null, that is whenever this thing becomes null or only fast becomes null, so then we can't access this thing at all, so we will not go. So we'll put up the condition. So whenever this fast will point to either null or one less than the null, then the number that is there at the slowest node is my middle. I'll simplify it when you will do the code. That will make the things a little more clear to you, right? So what actually we are going to do is we are going to put down the condition here, and I'm going to move slow by a single time and fast by 2 times. Right, and I'll return the slow pointer. So what should be this condition? So there can't be a time when fast ka next is equal to null, right? Fast is not equal to null and fast's next is not equal to null. As soon as fast's next becomes null, so we can't access this. Hence, this will give a segmentation fault otherwise. So we can simply return the slow pointer, right? So this is something that is an approach that you should keep in mind. You can categorize it for even and odd linked list as well. Now let's just move on to the code and see how we'll code this particular question. So now let's see the code part of this. We have a linked list. Let's first find out the length. For this, the return type will be integer only, and we'll be passing on the head, right? So first thing is, if head is equal to null, so we'll simply return the length as 0, right? Else what will return? 1 plus length of heads next. Okay, this is what we discussed. So probably this should give us the correct length. Let me just find out length is equal to length of my head, and I'll see out endl first and then length, right? Let me see if we can get the correct length. Yes, we are getting the correct length, that is 6. So this linked list is containing 6 elements. Now let us just find out the middle also. So its return type will be node. Let me just name it as middle only, node star head. We are passing on the head. And how will we calculate the middle? The first thing is, let me just take a temporary node. Let's just not mess around with the head. We'll take a slow pointer that is initially equal to head. We'll take a fast pointer that is also equal to head. We'll run a loop while head is not equal to null. Sorry, let's just write this condition later on. First thing is, slow is equal to slow's next is what we are going to do. Fast is equal to fast's next, right? And we'll return this slow pointer. So here the condition should be, firstly, fast should not be equal to null and fast's next should not be equal to null, right? These are the two conditions that we have. Let's just find out the middle as well. So let me just have this as node star mid is equal to middle. I'll pass on the head again. I'll see out mid, and that's it, right? Let's see what does the answer. Mid's data, right? This is a node, so we'll be finding out mids data. So yeah, so the middle number out of this list is, we are getting the second middle, that is 3 as the answer. We can also get the first middle if, let's say, you are given the same question and you need to find out the first middle, right? In this particular linked list, you need to find out the first middle. So this is the question for you to try, think upon it, do a dry run and try solving how to get the first middle if the length of the linked list is even. Let's also try for an odd length linked list, right? Let me just remove this insert recursive. Now let's see what is the answer that we get. So yeah, so this is the linked list that we have. The length of the linked list is 5, the middle that we're getting is 3, and I think we are all set to go with the next questions. I hope you have understood finding the length of the linked list, middle of the linked list, insertion, deletion recursively as well as with a normal method. So this creates the base for you to move ahead with other questions. So we'll talk about other questions now. So now we have very well discussed what is a singly linked list. So now I want to just focus upon what is a doubly linked list and how can we operate on a doubly linked list, right? So when I say a singly linked list or a linked list in general is what we say. Singly linked list. It looks something like this. 1, 2, 3, 4, 5 and null, right? This is what a singly linked list looks like. It just has the forward arrows, right? But what happens in a doubly linked list is the structure is something similar to this. Two, 4 and 5. So it is something like this. Right? So in this case, we had the node structure as, our node was something like, we had int data, and node star next. So this was basically the components of a singly linked list or the data members of a singly linked list. But in doubly linked list, what happens is, along with this next pointer, we have something known as previous pointer. So what is the benefit of this is, like, at any point we don't need to we can access the previous element to that also and the next element to that also using any particular element. So the node in this case would look something like int data, node star left, and node star right, or you can say them as next or previous. Right? Node star next, node star previous. So this pointer points to the next node, this pointer points to the previous node, right? So now let's say you are given a case in which you need to remove this particular node, right? You are given a node, let's say A, and this points to this fourth node, and you need to remove this particular node from the linked list. How can you do it without traversing the linked list at any cost? Right? What we need to do, we simply need to put this here and we need to put this here, right? And this we need to explicitly delete, right? Now let's say this is the node that is given to us. The node is node star A, right? This is the node that is given to us. Now what we'll do is, we'll do A's previous. So what is A's previous? A's previous, it's 3, right? And 3's next, right? 3's next, that is A's previous next. So A's previous is 3 and 3's next is this. So what we want to put in this is, we want to put 5. So what is 5 with respect to A? So this is A, so this is A's next, right? So we can say that A's previous ka next is equal to A's next, right? This is the first line of code. Now after this, like this connection has been made. We have successfully made this connection, right? Now this connection we want to make it again. So how we'll do that? So now again, so what is this node? So this is A's next. A's next is this. Now iska previous, A's next previous is equal to A's previous. Right? What is A's next? A's next is 5. So 5 ke previous mein what we are putting? A's previous. Right? So these 4 lines of code are something that will help us in this particular case. So this is how a doubly linked list works. Apart from that, let us just go through what STL and lists look like, right? So how, like for every time when we are solving particular questions, we don't explicitly create linked list. So we know something known as linked list STL. So STL, you all know that it is standard template library. So what happens in linked list STL is, linked list STL, it is categorized into 2 parts. One is forward list and one is only list. And we need to specify the data, like the type of elements that we want in this list, whether it's integer or whether it's something else, right? So this is known as doubly linked list. This list corresponds to doubly linked list. And this forward list corresponds to singly linked list, right? So let us just have a more closer look at forward list and list through our website. Like there's a website known as c++.com through which you can get entire information about all the STLs. So you can see forward list, they have mentioned it very, very clearly what forward list is. Forward list are sequence of containers that allow constant time insert and erase options anywhere within the sequence. So there are a lot of pre-built functions, pre-built member type functions that are already defined so that you can use them directly. So these are the operations, right? You can use insert after, you can use erase after, you can use remove, unique, merge, sort, reverse. Different functions are there that you can use with forward list. Similar to forward list, there is an STL known as list STL. So list STL also, it has some of the functions like begin, end, and some others. So make sure you check out c++.com for more information about STL on linked list, right? You will get entire information about all different kinds of standard template libraries that are available in C++, right? So now let's see how we can use them in our questions ahead. So the next very famous question that you all might know about or might not know about is reversing a linked list. So you all might have heard of an ad. Do you know how to reverse a linked list? So I hope you all know this, right? So reversing a linked list, what happens when we have to reverse a linked list? We are given such nodes like 1. We are given this linked list, right? 5 and null. And you need to reverse this linked list. Like let's say its addresses are 100, 200, 300, 400 and 500. When you will reverse this linked list, it will, like, it should not become something like this. Let me just write it down and show it to you. It's not that you are just taking out 5 and putting 5 here, or taking out 4 and putting 4 here at the same address. No, this is not to be done. Instead, what you need to do is you need to change the connections. How you will change the connections? That is, if 4 is pointing to 5, now 5 should point to 4. If 3 is pointing to 4 here, now 4 should point to 3. If 2 is pointing to 3 here, now 3 should point to 2. If 1 is pointing to 2 here, now 2 should point to 1. 1 is pointing to nothing, then 1 should point to null here. And you need to return this head. This null will be removed.
So this is what is our aim. This is what is the output that we are expecting, right? So this is what we are looking forward to in this particular question. So how we'll do this? There are two particular methods that we'll see to implement this particular question. One is iterative method and the other one is recursive method. So we'll see both methods. Let's start by iterative method so that you can understand the in-depth analysis of how we are reversing a linked list, right? So what happens in this case is, in an iterative case, let's say we have this linked list 1, 2, 3, 4, 5 and null. We have this linked list, right? Let's consider its address as 100, 200, 300, 400 and 500. So now let us say what we want to actually do. We want to reverse this pointer. That is, if this is the head node, right? So heads next, now this is currently pointing to 2, right? Now we want to make this 2 to point back to 1. This is what we want, right? So let's consider 3 pointers. We can solve it using by taking 3 different pointers, right? So let me just mark them as, so this is my current pointer. My current pointer will be here. I'll take a previous pointer. My previous pointer will be here, and next pointer, that is my next pointer, will be here. So this is my current number. This is my next number in the linked list. This is my previous number. So for the first case, the previous should be equal to null because there is no number before 1, right? Now what we are actually trying to do is, in this case, is what will be C's next. So we want to connect this 1, instead of 2 we want to connect it to null, right? We want to put C's next as null, right? We want to put C's next as null. So instead of null, like now we have previous, but every time when we'll, let's say this is the current situation, let's say P, C and N are here, right? So now what you want to put in 4's next? 4's next we want to point to 3. So C's next we want to point to previous, right? So this is one thing that we'll do. So we'll point C's next to previous, right? After that, what we'll do? We'll move on, right? We'll move on this entire thing to the next part. Now current will come here, previous will come here, and next will come here, and we'll repeat the same cycle, right? Now what we have done in this case is, after C's next is equal to P, we have made P is equal to C. Previous becomes current and C is equal to N. Current becomes my next, right? And what happens to the next? Next has changed to from here to here. That is, next is equal to N ka next, right? And like we will be putting a check in front of the N, because as soon as we move ahead in our linked list, at some point of time N will become null when current will be at this particular position. So we can't access null ka next. This will give segmentation error. So I'll put a check if N is not equal to null, then only we'll do. So these are the 3 conditions that will help us reverse the linked list, right? And what we'll simply do, once we reach till here, we'll simply return P at the end, right? So these are the steps that will follow. Now let's move on to the code. I hope you will better understand it using the code. So this is a question that is there in front of us. It is basically reversing a linked list. We are given the head of the linked list, and we will be performing. So first thing is, will check if our head is equal to null. If our head is equal to null, we don't need to do anything. We simply return null, right? After that, what we took 3 pointers, list node star P, that is previous pointer. It was initially pointing to null. We also took list node star C, that is currently pointing to head. We took list node star N, that is currently pointing to heads next,
right? These are the three things only we have. Now we were repeating the steps again and again until and unless C becomes equal to null. C is not equal to null. So which all three steps were we are performing? C's next becomes previous, then previous becomes my current, and current becomes my next. These are the three steps, and the last step was if n is not equal to null, we will be moving n is equal to n's next. So these are the steps that we were doing actually, and what will simply return? So my last will be pointing to what? The previous one. Let's just see how it is. So what we have done in this case is we have created, so first of all we have been passed a head, right? Let's say this is the linked list that we have 1, 2, 3, 4, 5 and null, right? I have made 3 pointers P, C and N. P is here, C is here, N is here, right? C is at the head, N is at heads next, and P is at the null, right? Now we'll run this until C reaches here, until current reaches here. So what we are doing, C's next is equal to P. C's next is equal to P. That is C's next. 1's next is equal to P. So it is null. 1's next becomes null, and what happens next is previous equals to current. Previous becomes current. So previous comes here. Current becomes next. So now current becomes next. And if null is n is not equal to null, n becomes n's next. So this n becomes n's next, that is n comes here, right? Now again we'll move on to the loop. C is not equal to null now also. So what we'll check, C's next is equal to P. Now C's next is equal to P. So what is P? 1. So we'll make this connection. That is 2's next. So 2's next is pointing to 1 now. This is we have done. P equal to C again. So now this becomes P. This becomes C. N is equal to N arrow next. So this becomes N. Again we'll simply run. We'll move here. We'll move these three things one step forward. This becomes N. Now again for this it becomes like this. We'll move again. This becomes P. This becomes C. N becomes null. Now at this point N becomes null. So we'll not be moving. We'll not be performing this step any forward, right? And we will simply now in the next step C is still not equal to null. We'll again run the loop. C's next become equals to P. C's next, matlab 5's next becomes equal to P. 5 starts pointing to 4. Present becomes current. So now this becomes P. This becomes C. So now 5 is pointing to P, right? P is pointing to 5. That is the last node. That is the head node. We need to return this only. We need to return this linked list, right? 5, 4, 3, 2, 1 and null. Now P is pointing to 5. So we'll simply return this 5 in this case, right? I hope this is a little more clear. I would say try to dry run it on your own on a piece of paper. You will understand it a lot better, right? Let's just try to run this code. So yeah, so 1, 2, 3, 4, 5 linked list was given to us, and we have successfully reversed this linked list as 5, 4, 3, 2, 1. So this was the iterative method of reversing a linked list. Now let's see how we can do it using recursion. So recursive method is also very, very simple. You just need to understand a little bit the steps of recursion basically, right? So which all steps of recursion do we know? So in every recursion question, we first we take care of the base case, we take care of the small calculation, and we take care of the recursive call, right? So in this question also, let's just say, yeah. So in this question also, recursive solution, right? So we have this linked list 1, 2, 3, 4, 5 and null. So what happens is we try to break our problem in recursion, right? So if we'll break our problem from here, now this is one part, this is one part, right? So this part basically is something that will pass on to recursion, and we expect recursion to give the correct answer. What we expect from recursion is recursion will give us this 5 4 3 2 and null with this as the answer, that is this is the answer that is coming from recursion. तो हमने सोचा कि recursion should give us this, right? After this is done, now what is the thing that is left on us? Now we have this head, right? We want to point this 2 to this head. We want to point this 2 to this head and this head to null. So these are the two steps that we need to perform, right? So what is 2? So 2 stands for, matlab, if this is the head, currently this is pointing to head. So 2 is what? What is 2? So we want to make 2, we want to point this 2 to 1, right? So now head points to 1. So what is heads next? Heads next is 2. So we want to point this 2 to 1, right? We want to point this 2 to 1. We want to point this heads next to well, heads next is 2, and we want to point 2's next to 1 again. So heads next is 2. We want to point 2's next to head again. That is 1. So now this connection is made. This is a very, very important line. Heads next is equal to head. This line is very, very important. What we are doing in this is heads next is 2. 2's next is 1. This is what we are putting. 2 ke next mein we are putting 1. 2 ke next mein we are putting 1. Right? After this, head. So head should point to null. So we'll write head is equal to null. These are the steps that we need to perform. Also, there should be one base case. So what should be the base case? Like this recursive call, when it should return, when the value of head ka next becomes equal to null. When heads next become equals to null, we simply return head, right? This will be my base case. Now let me just try to submit this recursive code also and see how it goes, right? So let me just create one more function, list node star reverse list node star head, right? What we'll put inside this is, we'll make a check, like this is the base condition. Let's just write this base condition afterwards. First thing is, we will call upon the recursive function list node star x. So we want that answer should be stored in x, that is the head that should come after this recursive call should be stored in x. So we'll say reverse and we'll pass on head ka next in this, right? Now x is having the entire linked list, like x is having what? It is having 5 4 3 2 1 with x pointing to 5. Now my task is heads next ka next should be equal to head, like the last second step. I'm pointing this 2 to 1, right? And head should point to null. This is what I want to have. And what should I return? I should return this x only, right? This x only should be returned because it is pointing to 5 and I want to have a linked list with 5 4 3 2 1. So what should be the base case? Base case will be, if heads next is not equal to null, I'll simply return head. ठीक है जी? Let me just remove this iterative code from here. Here also we'll put a check. If let's say if head is equal to null initially only, then we'll simply return null, right? And else we'll return reverse of head. We'll call upon the function reverse of head. I hope this should work fine. Let's just try to run and see how it goes. Okay. There is a little bit of problem. It should not, it is equal to null. When heads next becomes equal to null, then only we were returning. Now this should be the base case, right? Okay, so there is some error. Let me just try to debug what is the error. It should be head itself, right? Just a minute. So it should be head ka next is equal to null. This was the problem, I guess. So not to make the head equal to null, we want to make the heads next equal to null, right? What actually I'm trying to say in this case is, like, we had this 1 2 3 4 5 and null, right? This part was handled by recursion. We get the answer in x is pointing to 5, and we have this linked list 5 4 3 2, right, and null. This is the linked list that recursion gives us, and x is pointing to this 5. So now I want to point this 2 to this one. So this is the step that does that. Heads next ka next equal to head. So this is done. Now 1, this is head. Heads next should point to null. So heads next should point to null, and we should return x. So this is the step that we were missing. Let me try to run it again and see how it goes. Probably it should pass. Let's see. So yeah, so it is passing. We have 1 2 3 4 5, and we have the expected output as 5 4 3 2 1. I hope this code is clear to you, and now you can successfully reverse a linked list using both iteration and recursion. If somebody asks you to what is the time complexity in both the cases, right? This is something that can be asked in our interviews. So what will be the time complexity? Time complexity in both the cases will be almost similar, right? Because we are moving at n nodes of a linked list. So it will be O of n. Space complexity in iteration case will be O of 1, right? Because we are just making 3 pointers, nothing else. But space complexity will be there in the recursive case because we create a recursive stack internally. So space complexity wise, iterative solution is a little better, right? So make sure you check with this point as well in your interviews. So the next question that we have is basically merge two sorted linked lists, right? So what is given to us in the question is, the problem statement is like this. We have a list 1. Let's say this is the linked list 1. We have list 2. We have a second linked list, and both of them are sorted. This is given in the question. Let's say we take an example of 3, let's say 5, 8 and null. Let's say another linked list 1, 4, 9 and null. So we have the situation, we have been given two linked lists, linked list 1 and linked list 2, and we need to merge both of them. That is, our answer should be something like 1, 3, 4, 5, 8 and 9 null. This is what we are looking forward to as an answer in our merge two sorted lists, right? This is the answer that we need. So how can this be done in the best possible way, right? So there are two approaches again for this particular question, and we'll discuss both of these approaches. One is a recursive approach, a pretty simple one. The second is basically an iterative approach. Firstly, I'll help you understand the recursive approach, right? So let's say we have two pointers L1 and L2 pointing to list 1 and list 2, right? So now you see in this particular given linked list, like it is the sorted list. So the smallest element will lie at this, the head of the list L1, and the smallest of the list 2 will lie at the head of list 2, right? So out of both these lists, which will be the minimum element? The smallest one, right? So how we can get that? We will get, it can be either the smallest of L1 or the smallest of L2, right? So we'll compare L1 and L2. Let's say out of L1 and L2, 1 is the smallest, right? So now I know that I have got the smallest element, that is 1, right? So I'll pick this up. So this will be my list 2. List 2 comes out to be the smallest. Like I'll compare list 1 value and list 2's value.
So now list 1 value is greater than list 2. So list 2 is the smallest element, right? So list 2, I'll start from here, and the rest of the part, like the rest of the part, I will say to recursion, ki recursion, this is the list I am passing, this is the list I am passing, merge both of them and give me the final answer, right? So what recursion will do, recursion will pass this also and this also, and it will give us the final answer, that is X. So now this X will be having a merged sorted linked list containing the complete list L1 and the remaining part of L2. Now our next task would be, we just need to attach list 2's next with X. So as soon as we attach this, we will say that our lists are sorted. Pretty simple, right? What all test cases, base cases we need to solve upon? Let's say we are given list 1 is equal to null. If list 1 is given equal to null, what we can do is we can simply return list 2, right? Second thing can be, if list 2 is equal to null. If list 2 is given equal to null, we can simply return list L1, right? Let's just try to code it a bit and then we'll dry run it so that you can understand it a little more better, right? So this is the problem that is given to us, that is merge two sorted lists. You are given heads of two sorted lists, list 1 and list 2. Merge the two sorted lists in one sorted list. The list should be made by splicing together the nodes of the first two lists, right? So let's say, so we are given this particular function merge two lists, list 1 and list 2 we are given, right? Let's create our own merge function, list node star merge. In this we have list node star L1 and list node star L2, right? So the base cases were, if at all L1 is equal to null, then what we'll do, we'll simply return L2, right? And if L2 is equal to null, then what we'll do, we'll simply return L1. So these are the two things, these are the two base cases that we have, right? After that, what we are going to do is we're going to compare. If L1's value, let's say L1's value is less than L2's value, so that means the first element, the work that we are doing is on L1, that is L1 is the smallest element or the minimum of both the lists, right? So what we'll simply do, L1's next may I will put what I will get from the recursion. So what I'll put in recursion, now I know L1 is the smallest element, so instead of L1 I'll pass L1's next, right? And along with that I'll pass L2, right? So now list 1, this recursive function, that is list 1 ka next and list 2, this merge function, I am expecting that it will give me the combined merged results of both of these lists, list L1's next and L2, right? After that I don't need to do anything, I just need to return this L1 and we are done. But what about the second case, right? Else part. Let me write down the else part. So what happens in the else part is, I will do L2's next is equal to merge. If L1 is not smaller, then it's obvious that L2's value is smaller from both of these sorted linked lists. So I'll merge here L1 complete and L2's next. What I'll return in this case is, I'll return L2. Right? So now we have L1 returned, we have L2 returned, and this function I believe is done. Let's just try to return and call this merge here. We could have done it here only. That would not have been a problem. We can do it here also. Let's just do it like this. List 1, list 2, and let's try to run the code. So we have successfully merged both of these two linked lists, 1 2 4 1 3 1 3 4 as 1 1 2 3 4 4 1 1 2 3 4 4, right? So now you can see what is happening is, if L1 is equal to null, we return L2 simply. Like let's say if list 1 is not there, then we simply return list 2.
Similarly, if list 2 is not there, we simply return list 1. So both of these things are done, right? After that, the first case, we'll compare the first element of both of these: 1, 2, 4, 1, 3 and 4. We'll compare the first element of both of these. So the first element of both of these is same, so we can take any one. Let's say we take this one, right? So L1's next. So now this is what I am passing on to recursion, and I believe that recursion will give me the correct answer after merging. So what recursion gives me is 1, 2, 3, 4, 4. This is what recursion has given me, and this is stored in merge. Now what I just need to do is L1's next I need to put this one. So I get this final answer as 1, 1, 2, 3, 4, 4. Right? Similarly, if we take the second case, if L2 is smaller, then we'll take this case and we simply merge. This is how recursion works here. Right? If let's say we don't use recursion and I want to do it by iteration, right? So how we'll do that? Let's just discuss the approach for that as well. Right? So now what we're doing here again is, so yeah, so here again, now let's just take that same example: 1, 4, 8, null. This is list 1, this is list 2. List 2 is 2, 3 and 5, null. Right? Again, what we have to do is we'll have to compare this first element of L1 and L2, L1's value and L2's value. So I'll compare both of them. If L1's value is less than L2's value, right? So in this case, I'll take a dummy node. Let's say I create a dummy node and I initialize it as -1. Also, I'll maintain a tail variable which will point to this dummy node. Let's say dummy node is answer. Let me name it as answer, and this tail is pointing to answer. Again, we'll point the same base. For here, what I will do is I'll compare L1's value with L2's value. If L1's value is less than L2's value, then I'll point tails next to L1 and I'll update my tail so as to keep a track of that how far we have gone. This tail variable is due to that, right? Tails next is equal to L1. So now this is done. What I will do is I'll move L1 here and L2 is still here. Again, these both will be compared, L1's value and L2's value, which is smaller. So now 2 is smaller. So what I will do is tails next will be equal to L2, right? Then again L2 will move, L2 will come here. Now we'll compare this L1 and L2. Again L2 will again put tails next is equal to L2. Now this is done, L2 will be here. Now we'll compare L1 and L2 again. So now 5 and 4, which is smaller? L1. So we'll put tails next is equal to L1 and we'll move L1 here. Now we'll again compare L1 and L2, which is smaller. L2 is smaller, we'll put tails next is equal to L2. Now L2 becomes null. As soon as any of these linked list becomes null, then the second linked list as such we'll have to attach in our linked list, right? 8 is left. Let's say we had 9 or we had 12 also. So now we have reached a null here. So the remaining elements of the first linked list will attach as it is, right? So I believe this also, when we'll code it, right, you will be able to understand it a little more better, right? So let's try to code this as well. Let me just comment down this code. Right, so merge to sorted linked lists, merge to lists. So here also the first thing is, if at all I know that list 1 is equal to null, so what will happen is I'll simply return list 2, right? If list 2 is equal to null, I'll simply return list 1, right? I'll maintain a dummy node. Let's say list node star answer is equal to new list node, and let me just initialize it to anything we can initialize. It can be 0, it can be anything. Let's say we initialize it to something as -3, right? This is something that I have initialized. After that, I'll maintain a tail variable, list node star tail is equal to answer. So this is pointing to answer. This is just to maintain ki where we are reaching in our linked list. This is basically a tracker, you can say, right? Again, this loop I'll run until and unless either of my list 1 is complete or my list 2 is complete. Until L1 is not equal to null and L2 is not equal to null. Either of them is not equal to null. So now I'll see if L1's value is less than L2's value. Right? If L1's value is less than L2's value, then what we are going to do is tail ke next mein we attached L1, right? And now tail becomes equal to L1 and L1 increases. So L1 here is like in the previous question we took it as L1 and L2. Here we are taking it as list 2 and list 1. So let me just rename it as list 2 and list 1. So tails next, it's list 1, tail is equal to list 1 and list 1 is equal to list 1's next, right? So this is the if statement, the first if statement. Else if this is not the case, that is list 1 ka value is greater than list 2, then same thing we'll do with the list 2. Tails next is equal to list 2, tail is equal to list 2 and list 2 is equal to list 2's next, right? So this is something that we have done, and we'll have to check those two cases if at all one linked list is complete, and then the rest of the linked list will be as such. So for that, if L1 is equal to null, then what we can do is we can use tails next is equal to L2, right? Else tail ka next will be equal to L1 to L1. Again, it's L1, L2 is list 1 and list 2. Right? After that, what we are going to return is we are going to return the next of the dummy node, right? Let me just explain it to you. Once we write the code, answers next are going to return. Let's just run this code. Okay, so it is list 2. So we've successfully submitted and the solution has been accepted. So what we are doing in this particular case is let's just try and see again. So firstly, we are making the checks. If list 1 is null, we'll simply return list 2. If list 2 is null, we'll simply return list 1. After that, what we have done is we have created a dummy node answer, right? This is the dummy node answer, and we have made our tail pointer to point to this answer. Initially its value is -3. It does not matter. You can give it as -1, -5, -10, anything, right? After that, we have put a check. We have two lists, list 1 and list 2, right? Let's say it is 1, 3, 5, it is 2, 4, 6, and then it is null, right? So what is happening is until and unless list 1 is not equal to null and list 2 is not equal to null, right? So we'll perform these operations. First thing is we'll check this. If list 1 ka value is less than list 2 ka value, that is if 1 is less than 2, yes, it is true. So what I will do is tail ke next mein I'll put tail ke next mein answer mein I'll put list 1, matlab I'll put 1. So this is what is happening, right? Answer ke next mein sabse pehle 1 chala gaya. After that, tail is equal to list 1. Now tail is updated here and list 1 moves forward. Now list 1 becomes here. Now again this is done. So if statement we have gone to, again we'll move into the while loop. Is list 1 null? No. List 2 null? No. We'll again compare L1 and L2. Which is smaller, 2 or 3? 2 is smaller. So what we'll do is now 2 is smaller, right? So we'll not go in the if part, we'll go in the else part. So tails next is equal to list 2. So tails next is equal to list 2, that is 2 will attach here. Now tail is increased to here and list 2 becomes here. Now again we'll compare L1 and L2, which is smaller, 3 or 4? 3 is smaller. What we'll do, tails next is equal to list 1, so it will become 3. Tail is equal to list 1, so tail becomes list 1, tail is here, and list 1 is equal to list 1 connects. We'll move L1 here. We'll again compare this 4 and 5 and so on. We'll go till the end and we'll have a sorted linked list 1, 2, 3, 4, 5 and 6. So this completes this particular line of codes. Right? So after this, let's say why these two lines are there. Let's say I have this linked list 1, 2, I have something of this particular sort 1, 3, 5, 7, 9 and null, and second linked list is 2 and 4 null. Right? We compare this and this, we attach 1, 2, then we attach 3, then we attach 4. Now after 4, this has become null. As soon as list 1 becomes null or list 2 becomes null, so is it that I'll stop doing anything? No. What I will do is after 1, 2, 3, 4, I'll put all the elements 5, 7, 9 in the complete list. This is what I'm doing in these two steps. Right? So at the end, what we are doing is we are returning answers next. That is, initially answer was -3 के next से ही हमारी linked list was starting, and that is what we are returning. I hope this is clear, right? So we have successfully solved this problem using recursive approach also and using iterative approach also. Now let's see another problem. So the next thing that we're going to see in this particular video is the question. It's also an easy problem. Remove duplicates from a sorted list. Right? You are given the head of a sorted linked list and you need to delete all the duplicates such that each element appears only once, and you need to return the linked list sorted as well. Right? So this is the linked list that you have 1, 2, 2, 3, 3. This is the sorted linked list that is given, and you need to return a linked list by removing all the duplicates. 1 is occurring 2 times, so we need to remove this for once. 2 is occurring 1 time, that's fine. 3 is occurring 2 times, we need to remove 1, so we need to return 1, 2, 3. This is the problem statement. Right? Now let's discuss the approach, how we can solve this particular problem. So remove duplicates. Right? So this is the problem statement that is given to us. So let's say this is the example 1, 1, 2, 3, 3 and null. So again, for solving this particular problem, I have two approaches. One is recursive and one is iterative. Let's first understand the recursive approach, then we'll go on to the iterative approach and we'll see how we can solve it in the best possible way. So this is the list that is given to you and you need to remove all the duplicates. What happens in recursion is we take a small part and we tell recursion to solve the larger part for us, right? So we break this linked list here, we pass this entire thing to our recursion, and I believe that recursion will return me the list after removing all the duplicates. That is, recursion will return me 1, 2 and 3. Right? So this is the result after I pass on to the recursive function. So now the next thing that is my turn, what I need to do is I need to check this head and the first element of the recursive result. So if they are same, that means one is here also, one is here also. So I need to remove this. So I'll simply return my recursive head. Else, if they both are different, right? This head is different and recursive head is different. So I'll have to attach this recursive head to heads next. So heads next will be equal to my recursive head and I'll return this head in that case, right? You will be able to understand it better when we'll code it. So let's just move up onto the IDE and try to code it, right? So we are given the head of the linked list. So the first thing, that is the basic thing, that what we need to check is we need to check if head is equal to null or heads next is equal to null. If both of them, that means it's just one number, so it can't be duplicate. So we need to simply return head in this case, right? Next thing is I'll call upon recursion list node star x. So I will store the answer of that recursion in x. So what I will do is I'll call delete duplicates heads next, right? So the entire result after recursion will be stored in this x, right? Now I need to check if the heads value
is equal to the value of x. If this is the case, then what is the next step? We'll simply skip the head and we'll return x as such, right? Else what we'll do, else I will attach the heads next to x and will return this head. I hope this is clear to you. There's nothing very difficult to understand. So what we are doing in this particular case is, let's say we have this example 1 1 2 3 3 and null, right? So initially we are checking if head is equal to null or heads next is equal to null. So we have checked both of them, they are not equal to null, else we would have returned head simply, right? Next we are calling upon recursion for this part. We are passing upon heads next and we are expecting the answer in x. So what will x have? X after recursion will have 1 2 and 3 and null. Now next case is, I'll compare if the value of head is equal to value of x, that is this value, if it is equal to this value. Yes, this is true in our case, so we'll simply return x. So we'll simply return this x as my answer. Else if they both would not have been same, then what? Let's say it would have been 0, then I'll compare 0 and 1. Else part will go on, we'll put on heads next as x, matlab 0 ka next I'll put this x and I'll return this head. So now my answer would be in that case 0 1 2 3, right? I hope this is also clear, right? Now let's discuss the iterative approach on how we can solve this particular problem. Just think upon how the iterative approach would be, right? So how the iterative approach would be, so let's say we have this 1 1 2 3 3 and null, right? So in the iterative approach also, this step is going to remain the same. We'll check for if head is equal to null or heads next is equal to null. We'll simply return head. What will change in iterative approaches, we'll run a while condition until and unless this head is not equal to null. What we'll do is, we'll simply compare the data of head with heads next, right? We'll compare the value of head if it is equal to head के next की value, right? If both of these values are same, so what I need to do is, I need to simply skip this part, right? So for skipping this part, what I need to do is, I need to make this connection. So for making this connection, I need to have the address of this. Let's store the address of this in a variable a. List star a will be equal to temp के next का next. So temp is this, temp or head you can say. Head के next का next, head is this, head का next is this, next का next is this. So we stored the address in a variable. Next, what thing I'm going to do is, temp का next I'm going to make it as a, that is इसका next I'm going to make it as a, and this will be removed. Else what I'll do, if this is not the case, like both of them are different, 2 and 3 are different, so what I will do is, I'll simply move temp to temps next. So this is going to be the code for this particular question. Let's just try to see the approach. Let's just try to see the code so that you can understand it in a more better way, right? So what happens in the code part is, this head is equal to null or head का next is equal to null remains the same. Again, let me just remove this code part. So instead of using head, I'll create a temporary variable, list node star temp is equal to head. Fine. So what I am going to do after this, so after this I'll check for I'll put a while loop, right? While temps next is not equal to null. So we'll check for if temp का value is equal to temp के next का value, right? So that means both are same, so we need to skip that number. How we were skipping that number was, list node star a is equal to temp के next का next, right? And we were simply putting temp का next is equal to a, that is we have skipped the middle node directly. else part में I was simply moving temp, temp is equal to temp का next, right? Let me just try and run this as well. Okay, there's one extra bracket. There's some problem with the brackets. Let me just check. Right, this is for this is for this is for this. There's no problem with the brackets. Let's just try and run this again. Oh, so we haven't returned anything in this case. Okay. Sorry. Yeah, so we are to return head itself. Yeah, so we have finally got the answer. This is correct answer, 112. The list with all the duplicates removed is 12, and let's just submit this and see how it goes. So we successfully submitted this as well. So now I hope you have understood the recursive as well as the iterative solution of remove duplicates from a sorted list. This can also be asked in your interviews. So now let's move up on to the next problem. In this video, we are basically going to discuss a new problem, that is add new two numbers. So what you're given is you are given two non-empty linked lists representing two non-negative integers. So this is the condition that is given. The digits are stored in reverse order. Basically, the digits that you are given, they are stored in reverse order. Each of their nodes contain a single digit. Add the two numbers and return the sum as linked list. So you will be given two heads of two linked lists, and they will be representing two numbers present in reverse order, and you need to add these two numbers. You need to add these two individual elements of linked list separately, and then you need to return the answer in the form of head of the linked list only, right? So let's see with this with an example, and then we'll try to see how we can code this better, right? So let's take an example where we have something of the sort. Let's say we have 4. Let's say we have 4. We have 6. We have 2, and we have null. Second, like we have this linked list L1. We have this linked list L2. In this we have 2. Let's say we have 8. We have again 8, and let's say we have 1. So we are given this L1 and L2 that points to the head of linked list L1, L2 points to the head of linked list L2, and we need to return our result. So the result would be in such a way that these numbers are given to us in the reverse order as per the mentioned. So the original numbers will be 264 and 1882. So when I add these two numbers, so it will be 4 plus 2 6, it will be 8 plus 6 14. So 4 will be here and 1 will be given as carry. So 8 9 10 and 1 11, 1 and 1 will be again carry. 1 and 1 when added will give us 2. So the answer is going to be 2146. So we need to return, let's say we need to return result, and the result should look something like 6 4 1 and 2. So this is something that I want to return. I want to point this result to this head of the answer, and I need to return this result. So this is something that we're looking forward to in this particular question. So for solving this question, let me take a dummy node. Let's say I'm taking a dummy node D. So this is the dummy node, and let's start pointing it to let me just take this as L1, this as L2. We'll take two variables, sum and carry, right? So we'll try to add individual L1 and L2. We'll first of all, I'll go and check if L1 is empty or L1 has something. So if L1 is not empty, I'll go to L1 and I'll add L1 and L2 together. So when I'll add L1 and L2, I'll put that thing in the sum. So 4 plus 2 comes out to be 6. So I'll have 6 in the sum, and also I'll make a new node with 6, that is sum. I'll insert into this list and I'll point this to this, let's say it's pointing to temp, and I'll point this dummy node to 6. Now temp will move on to this 6 as of now. This is what is happening till now, right? And carry is 0 in this case, right? So what we're going to see in the next, like, we'll move L1 one step forward, we'll move L2 one step forward. Now again, we'll once 6 is written here, we'll remove 6 from here, and it again turns out to be 0. So now we'll add 8 plus 6. We'll check if L1 is empty or L2 is empty. As soon as any one of them is empty, we'll not do anything, but they are not empty, so we'll add 8 and 6. Adding 8 and 6 will give us 14, so we'll put 14 in the sum, right? And we'll create a new node, and inside this new node, what we'll put, we will be putting sum modulo 14. This is something that we'll put in sum modulo 10. So what is the sum now? It's 14 modulo 10, that is 4. So we're going to put 4 in our new node, and we'll point this temp to this. And inside our carry, what we are going to put inside our carry, we are going to put 14 divided by 10. So when I say 14 divided by 10, it gives out to be 1. So my carry becomes 1 now, right? So now again, 14 is gone and 14 turns out to be 0, right, with carry 1. So now this carry is also there, right? So now this carry is also there. So what happens is, as soon as I move L1 to here, L2 to here, now while calculating sum, I'll add this carry also, right? Once I'll add this carry, so it becomes 8 plus 2 plus 1. So it is 11. So 11 is there in the sum, carry becomes 0. Now what I'll be putting in the next node? In the next node, I'll be putting sum modulo 10, right? So that is 11 modulo 10, that gives 1. So I'll be putting 1 here. And in the carry, what we'll put? Again, 11 divided by 10. So 11 divided by 10 is again 1. So I'll put 1 in the carry again, right? As soon as this is done, so we'll put sum is equal to 0 again, and we'll move L1 and L2 further. Now L1 is not there, right? So we'll not take L1 now, but L2 is there, and along with that a carry is there. So carry is 1, L2 is 1. When I'll add L2 and L1, when I'll add L2 and carry, so it comes out to be 2. So I'll have 2 in the sum. So what will be there in the carry? That is 2 divided by 10. 2 divided by 10 and 2 modulo 10. 2 modulo 10. So 2 modulo 10 will give me 2 again. So I'll add 2. I'll move the temp here. Earlier also I'll move the temp here, and 2 will be pointing to 2. I'll create a new node and I'll add 2 into it. 2 divided by 10 gives me 0. So I'll make carry equal to 0. So in this way, now my L1 is also empty. Now, like, till how long I'll have to run this loop? Either we'll check for L1 whether it's empty or not, we'll check for L2 whether it's empty or not, and also we'll check for carry if it is empty or not. If there is only carry left, then also we'll add only carry to our new we'll make a new node and we'll put that carry into our new node and we'll point that to null. So that is basically what we are trying to do in this particular question. We'll point this to null at the end and we'll return the dummies next. Dummy ka next is basically the head of our new answer, so we'll return dummies next as the output. So this is going to be the approach. Talking about the time complexity, so it will be O of m or n, the length of the longer linked list, right? If it's L1 or L2, so it's basically the time complexity goes according to that. Also, let's now discuss the code part. Like, if we are trying to code this particular solution, then how this is going to actually work and what all things we need to do. Basically, we will be doing the same what I have explained to you here in the explanation part. Right now, let's move on to the code part and see how we can code this. So basically what we are given
L1 and L2. So L1 and L2 points to the head of two linked lists, L1 and L2. So firstly, I'll create a dummy node as per I have explained you. It's list node. Dummy is equal to new list node. Then what I'll do, I'll create a temp variable that is pointing to this dummy. So this temp will be taking forward when we add a new node to our result dummy linked list, right? So temp will point to dummy. After that, we'll initialize a carry variable which is equal to 0, right? So we'll run this while loop until and unless we discuss about three conditions. Firstly, L1 should not be equal to null, or L2 should not be equal to null, or carry should not be equal to null. So these three conditions these should satisfy until and unless this loop will run, right? So int sum is equal to 0. Initially I have initialized the sum is equal to 0. Its value will be what we are what will be going to see from L1 plus L2 plus carry, right? So we are going to do this. So inside this we'll check two other conditions. If L1 is not equal to null, until and unless L1 is not equal to null, what we'll do, we'll add the value of L1 in sum is equal to L1's value, right? And then we'll move on L1 further. L1 is equal to L1's next, right? Again, if L2 is not equal to null, then what we'll do, we'll do sum plus equals to L2's value, right? And we'll do L2 is equal to L2's next, right? So we have done these two things. After that, what I was doing is I was adding the value of carry in sum. That's the third thing, right? And what was the value of carry? Carry was equal to sum divided by 10. What after this, we were creating a new node, list node, in which we are storing the answer. Node is equal to new list node, and what will this list node have? List node will be having sum modulo 10, right? Why this sum modulo 10? Because like we saw that the last part was like let's say we have 14 as the sum, so 4 will be there in the list node and 1 will be given to the carry. So we have given carry as sum divided by 10 and the number in the list as sum modulo 10. Next thing is we'll be moving apart our temps next is equal to this node that we have created, and then we'll move on temp further. Temp is equal to temps next, right? At the end, what will return? Will return dummies next, and we are done. This is basically what we have done and what we have understood in that particular solution. Let's try to run this code and see if it is working. So we were to create list node here. I think everything else should be fine, or if there is some typo. Okay, so it's val, not value. Okay, so for this particular case, like 2, 4, 3, 5, 6, 4, we should have 5 plus 2, 7, 6 plus 4, 10, 0, 1 is carry, 4, 5, 6, 7, and 8 should be the answer. 8708 is what we are getting as the reverse number. So exact answer should be 807, but we need to return the reverse, so it is 708. Hi, so the next question that we have, So the next question that we're going to discuss is basically to detect a cycle in a linked list, right? We have discussed some of the problems in linked list. Now it's also a very, very important problem from the point of view of interviews. So linked list cycle detection, right? So what exactly does this mean? Let's say you know what is the structure of a linked list, right? We have something known as nodes, in which first node is connected to the second node is connected to the third node is connected to the fourth node, and fifth node, let's say this is connected to null. This is a kind of a linked list that you are aware of. We have something known as head, from where we can access the complete linked list, right? But let's say you have an example in which you have linked list of this particular form: 1, 3, right? Or it can be 1, 3. It can be of this form. So now what happens in this linked list is there's no null, right? You don't find any null here. Or it can be something like this also, right? So now you move from 1 to 2, 2 to 3, 3 to 4, 4 to again 2, 2 to 3, 3 to 4, 4 to again 2, and this continues forever. This is a linked list with a loop, or a linked list with a cycle. So here this cycle exists, right? Similarly here also, you start from 1, you go to 2, you then go to 3, and again go to 2, go to 3, again go to 2, again go to 3, 3 2 3 2 3 2 3, and it again forms a cycle. So what we are supposed to do in this particular problem is we need to detect these cycles, right? So when I say detect these cycles, so from the point of view of cycle detection, you need to return a true or a false to confirm whether a cycle exists or not. And if it exists, you have to return which is the first node where it meets, right? You'll have to tell which is the first node where it meets. So this is basic cycle detection part. So what can be the approach, how we can solve this particular problem, or how we can approach to this particular problem? There can be various methods, right? So the first and the most important thing that comes to our mind is, let's say I have something of this sort: 1 2 3 4 5, and we have this particular cycle, right? So we have nodes like 1 2 3 4 and 5, and 4 traces back to 2, then 2 to 3, 3 to 4, and it's in this fashion, right? So what can be done? So the first thing that comes to my mind is, let's say I create a hash map. So hash map is a data structure in which I put all the nodes along with their frequencies, right? Let's say 1 is there, 1, and I put its frequency as 1 again. Or you can say, like, I have a hash map, like let's say 1, then 2 with an entry 1, then 3 with an entry 1, 4 with an entry 1. As soon as it moves from 4 to 2 again, so I can see 1 is already present in the 2's column. That means 2 already exists in this linked list. So as soon as this conditions occur, what we can say is that this linked list contains a loop or contains a cycle, right? This part is done. Now at which node the cycle exists? So the cycle exists at this node 2. So the first number that exists more than once is the node where the cycle exists, right? So this can be one simple approach that we can follow for solving this particular problem, right? But what is the problem in this particular approach? When I say problem, so there can be a problem with respect to this hash map. So to create a hash map, we need space, right? So this accounts for a space complexity of O of n. So I have this extra space complexity. So I need to reduce this at any cost, right? So this is a very I would say lovely method that we have already used when we are finding the middle of the linked list, right? We found the middle of the linked list by some method. I'll just make you revise that as well. But for discussing this problem, we are discussing a very, very important algorithm that is known as Floyd-Warshall cycle detection algorithm. So what happens in this particular algorithm is, and it's very, very magical. Look, you will love this way that we solve this particular problem, right? So how we are going to do this actually? Let's say you have this linked list 1, 2, 3, 4, 5 and 5 traces back to 2, right? So what you are going to do in this case is you take 2 pointers. कौन से pointers? You take 2 pointers, slow pointer and fast pointer. So both slow pointer and fast pointer are initially at this point, right? Slow pointer is also here, fast pointer is also here. Both slow and fast pointer are pointing to this. Now make the slow pointer point move 1 step at a time. Make the fast pointer move 2 steps at a time, right? So what I'm trying to say in this particular thing is, like, let's say if slow is moving here, fast will move here. This slow is here, fast will move here at the same point. Then both fast and slow will be cut. Slow will be here, then fast will be here. Slow will be here, then fast will be here. Then slow will be here and fast will be here. So this is a point where both slow and fast meet. So this thing suggests that cycle exists. So at any point in a linked list, if at all I find that slow and fast pointers, this is logically correct also, right? Pointers meet. At any point where slow and fast pointers meet with each other, that is the point where we can say that cycle exists in a linked list, because that thing is something that is occurring twice, right? This tells us that that thing is occurring twice. And let's take it as let's just take one more example. So let's say you have this kind of a situation in which it is 1, 2, 3, 4, 5, 6, 7 and back to 3. So let's say this is the linked list that is given to you, right? And you have your slow and fast pointers here, right? Now you know that slow moves by 1 step at a time, fast moves 2 steps at a time, right? This is something that you know. So now slow moves here, fast moves here. Then if slow moves here, then fast moves here. 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 Now this is the point where both slow is equal to fast, right? So this suggests that cycle exists in the linked list. So this is the point that cycle exists in the linked list. And how to detect that first node? तो फर्स्ट नोड कैसे डिटेक्ट कर सकते हैं? हाउ वी कैन डिटेक्ट दैट फर्स्ट नोड? सो द पॉइंट वेयर बोथ ऑफ दीज नोड्स मीट, keep your slow pointer there and make a new pointer start which should point at the first. Now move start by 1 step and slow by 1 step. 1 step start moves from here to here, slow moves from here to here, start moves from here to here, slow moves from here to here. So they will ultimately meet at the first node. मतलब यहाँ से if you'll start, मतलब the point where both of these meet, यहाँ से इतना distance will be equal to this distance.
थोड़ा अजीब लग रहा होगा ना, आई थिंक यू माइट नॉट हैव अंडरस्टूड. इसका प्रूफ देखते हैं, राइट. व्हाई आई एम सेइंग ऑल दिस, व्हाट इज द लॉजिक बिहाइंड दिस. So what I'm saying is, let's say if we have something of this particular sort, let's say this is the cycle that is existing, this is a certain distance a that I am traveling, and this is the point, let's say, where both slow and fast pointer are meeting, right? So let me just name this point as p, right? So let's say this is the starting of the linked list, this is the pointer p, this is the distance b, and this is the distance c. So we have three different distances a, b and c, right? And what we want to see is, like, this is the point where both of them meet, and I am saying that if we start a pointer from this p and you start a pointer from this start, both of them will meet at the starting node, right? So let's see what the proof looks like and why I'm claiming all this, right? So now this let's calculate the distance that is traveled by the slow pointer and the distance that is traveled by the fast pointer. Obviously the distance that is traveled by the slow pointer into 2 will be equal to what is the distance traveled by fast pointer. This is by logic, because slow is moving at single pace, fast is moving at double pace. Let's say what is the distance that slow travels. So slow pointer travels this a distance, then let's say it covers some rounds of this circle and it covers this distance b again, and it meets fast pointer here, right? So what I will write this as, it will be a plus b plus c, that means complete circle. Let's say it covers some m number of rounds, plus this b again, right, into 2 will be equal to fast. How many rounds will fast take? It will take a plus b plus c, that is the number of rounds, into n. N is the, let's say fast pointer takes n different rounds, plus b again, right? Am I clear? So now this is the equation that we have. Let's just try to solve this particular equation and see what are the results that we are getting, right? So it will be 2a plus it will be 2m b plus c plus 2b is equal to a plus n into b plus c plus b, right? So if at all I solve this, I will get this a is cut with a, b is cut with b, I'll get something like a plus b is equal to n minus m times b plus c, n minus 2m times b plus c. So this is again a constant, because let's say a takes n number of rounds, b takes m number of rounds, so this overall terms comes out to be a constant. So let's say a plus b will be equal to lambda times b plus c. This is the relation we have. Let's try for different values of lambda, lambda equal to 1 and lambda equal to 2, right? Now let's say I have lambda equal to 1. So what will be the case? If lambda is equal to 1, so this becomes a plus b is equal to b plus c, that means a is equal to c. So what were a and c? We had something like this. We had a point k, this was a, this is b, and this is c, right? I hope this is fine. So now a is equal to c, that means this distance is equal to this distance, is what I was saying. But you will say, sir, you have taken lambda equal to 1. Now let's say I take lambda equal to 2, what will happen? It will become something like a plus b is equal to 2 times b plus c, is it? It will become a equals to b plus c plus c. So this b plus c is the repetition, right? B plus c is the circle repetition. So no matter how many times the circle repeats from here to here, so this will again be of no value. मतलब circle तो कितनी बार भी वो कर सकता है ना, मतलब it can do infinite number of times. So I'll neglect this circle also, right? Because
at the end goal यहाँ से यहाँ तक he has to reach, यहाँ से यहाँ तक he has to reach. So this A will become equal to C ultimately. So A will be equal to C in any case, right? So this is what we have proved. Let's just dig into the code part and then we'll move on to how we are coding. जिसमें हम basically कर क्या रहे होंगे, detect cycle, right? What we will be given list node star head and हमें cycle detect करना है, right? So the first thing that I did was I took a slow pointer equals to head, I took a fast pointer equals to head, then I took a what I say while loop, while this fast is not equal to null and fast ka next is not equal to null. What I do is I move the slow by one step ahead. Slow is equal to slow ka next and fast equals to fast ke next ka next, right? At any point if slow becomes equal to fast, that means they are meeting at some point. So what we did in that case, we returned true. That means cycle exists in my linked list, else when we come out of this loop I'll return false. That means there is no cycle in the linked list. Linked list में कोई cycle नहीं है, right? How will detect the first node where both of where the loop starts? Detect the first node where the loop starts. Now you have the proof, right? Proof of where the loop starts is, if this is the case, this is some point P, this is some point A, this is the distance A, this is the distance B, this is the distance C, right? So now you know that once you get this point, that is the midpoint, right? In here, in case of true, let's say I return the original value. Instead of true I return slow, and at the last I return null. मतलब the point I am returning कि यहाँ पे they both are meeting. So now for detecting the first loop, what I need is I need to have a pointer that starts from the start. Let's say I have one start pointer and I should have a pointer from this mid. That is the mid pointer. How I can get this mid? I'll simply pass my head to this function that we have made above. So I have start, I have mid. Now I'll move both start and mid by one point, and the point where start becomes equal to mid is the point that is the starting of the loop, right? Now let's just try to code. Well, this is something that I believe you would have understood. If you still have doubts, make sure you watch this video again. It will clear a lot of your doubts. Now, this is the problem that is there in front of us, linked list cycle. So you'll have to return key whether this linked list contains a cycle or not. So the first step that we did was list node star slow pointer, it's pointing to head. List node star fast pointer, it is also pointing to head, right? So these two things we have. While fast is not equal to null and fast ka next is not equal to null. Now I have two things. What I will do is I'll move slow equals to slow ka next and fast equals to fast ke next ka next, right? Now if at any point slow becomes equal to fast, what I will do is I will return true. Once I come out of this loop, I'll return false. So this was the basic code behind this particular linked list function. Similarly, we can implement a little bit of change in the second part that we discussed, and we can submit this problem. We are returning a true, so this contains a cycle. Yes, that's true. So that was it for this particular video. Let's move on to another problem, right? So the next question that we are going to discuss in the series of linked list is to remove linked list elements. right? So you'll have to remove linked list elements. What I mean to say by this is, let's say you have this kind of a linked list in which the nodes are connected 1 3 6 2 6 4 8 and null, right? Let's say you have this linked list and you are given a value, let's say 6. You need to remove 6 from this linked list entirely, and you need to have a resultant linked list of this form. Your output that is expected should be of the sort of 1 3 2 4 8 and null. So this is the output that is expected, right? So you will have to remove this 6, you will have to remove this 6. So how can we do that? Maybe we can directly connect this particular node to this particular node. That's one thing. We can connect this particular node to this particular node. So we need to move to a node that is behind that particular node, right? So after removing this node, what we'll have is 1 is connected to 3, then 6 is removed, 3 is connected to 2, now 6 is removed, 2 is connected to 4, 4 is connected to 8 and null. So we get something of this particular sort, right? So how we can change, or how we can do this? Maybe there can be some more cases. Let's say if 6 is present at the first place, right? Like the linked list is something like 6 3 6 2 6 4 8 and null. So what you will do in this case, you don't have anything behind this, so it will again be a problem. Should we handle this case separately, or rather than handling the case separately, what we generally prefer to do in questions related to linked list is we create something known as a dummy node, right? So how this dummy node will help, we'll try to see it in this particular question, right? So let's say I create a dummy node. This is dummy node D. Let's say its value is -1. Dummy node with a value -1, right? And I connect it with the head. So it will be 2 -1 6 3 6 2 6 4 8 and null, right? I create this dummy node and I attach it with my head, right? So now what I will be doing is I need to ignore this, or I need to remove this. What can be done in this case is I'll directly connect the next value of this to 3. I'll directly connect the next value of this to 2. I'll directly connect the next value of this to 4, right? So this is what I'm currently looking forward to do in this particular question. So this is the same question that is available on LeetCode. Let's just go to the question and see what is the possibility, right? So the question states that you need to remove linked list. It's an easy marked problem, similar to what we have discussed. They have given an example. You need to remove 6 from the linked list, right? So you are given this function, you are given the head of the linked list, you are given the value that you need to remove. So the first thing that we did in this particular question is to check the base case. If at all, let's say the head is equal to null. So what we'll do is we'll simply return null, right? This is one thing. After that, the second thing is we created a new dummy node, list node star dummy is equal to new list node, and we initialize it with -1, right? So we have created this dummy node and we connect this dummy node to the dummy nodes next to the head of our original linked list. That is dummy ka next is equal to head of my original linked list. So our normal linked list has a new node that is dummy, and it is attached at the front of my linked list, right? I also create a new node by the name of list node star tail, right? And I initialize this tail to dummy. So now I'll iterate over this linked list using this tail pointer. I'll move tail one step ahead every time, and we'll continue this loop until we traverse the entire linked list. So while tail is not equal to null and tail ka next is not equal to null, right? So this is the format that, like,
for used for traversing, because we'll traverse until and unless this tail is not equal to null or tail ka next is not equal to null. What we'll check is if tail's next key value is equal to the given value. If this becomes equal to 6, let's say in this case, so what are the steps that we are going to do? We'll create a new node, list node star temp, to store the address of tail ka next. Then what we'll do is we'll change tail ka next to tail ke next ka next, tail ke next ka next. What does this means, right? So tail ke next ka next means ki this, let's say if I have tail ke next की value equal to 6, so tail, let's say this 2, it comes upon to 2, so 2 ke next, that is 6 key value is equal to value. Yes, this is true. So what I will do is I'll create a temporary variable temp which will store the value of tail ka next. It will store the value of this temp, right? And what I will do is tail ke next mein I'll put tail ke next ka next. So this is what I'm going to put. This is the connection that I'm going to make between 2 and 3, right? So this is the case, and after that what I will do is I'll explicitly delete, because they have been created dynamically. So I'll delete temp, and that's it, I guess. I'll create an else case. If the value doesn't matches, what we'll do, we'll simply move tail is equal to tail ka next. Bas. This is what is expected out of this particular question. And at the end, what we are going to return is we are going to return dummy ka next, right? Because our head starts from after dummy. Dummy is the node that we provided. So this is the case. This is the question that we have done, right? So we are getting the correct answer. Let me just try and submit. So we'll be able to submit this problem, and I hope this is clear. Also, there's one more solution to this. We can do this using recursion as well. Recursion can help us solve this problem in a much, I would say, in a cleaner fashion. If not help us in reducing the complexity or so, but it will help us in solving it in a cleaner manner, right? So what exactly I am looking forward to if I'm saying recursion is, let's say what I'm saying. So now let's say we again have this linked list 1, let's say I have 6, I have 3, 2, 6, null again, right? So what I will do is, what happens in recursion, we solve a smaller problem, we break the problem and we solve a smaller part, and we want recursion to solve a bigger part, right? So we'll break the problem from here. Now this part of the problem will be solved by recursion, and I will do a small part. I'll check for this particular node whether this is equal to value or not. If it is equal to value, then I'll simply return this what I have got from recursion. Else I'll add this head and I'll return, right? So what the code will generally look like, the base condition will be same. So first thing is I will recursively call and I'll pass head ka next along with value. So this I believe will give me this as the answer, 3, 2 and null. So this is the answer that I'll get from recursion, and then I'll put a check on my head. If the value of head is equal to value, that means if it is equal to 6, then what I will do, then I'll simply return this. Else what I will do is I'll attach head ka next, and head ka next equal to the recursive answer, and I'll return this head. So this is the question, this is the approach that can be followed if you are keen on using recursion here. Let me just clean this code and see this upper line will be the same. If head is equal to null, we need to return null in this case also. So this serves as the base case for this particular question, right? And yeah, so what I would be doing is I will create head ka next is equal to, I'll recursively call remove elements, I'll pass head ka next
and I will pass this value. So now I have a linked list in which head is not checked, but rest of the linked list is checked whether it contains the same element or element with the same value or not. Right now I'll need to check with my head if at all head ka value is equal to my original value. Then what I'll do is I'll create a list node star answer is equal to head ka next, right? And I will delete this head explicitly. Maybe I'll return the answer, right? In this case, if the value is equal to same, so I simply return head connects. This step I am doing just because I need to explicitly delete. We can skip this step also, it will not create much difference, but we should be completely correct, else we'll simply return head. This is the case. Let me just try and submit this as well. Yeah, so this is also getting submitted. I hope this is clear to you now. Now let's see how we can solve the next problem. So now let's read another question. In this question they are asking us to design browser history, right? How our browser history is made and how it is used in a particular browser, let's say in Google Chrome. Right, so what they want us to do is you have a browser of one tab where you start on the home page and you can visit another URL, get back in the history number of steps, or move forward in the history number of steps. Implement the browser history class. Right, we need to implement the browser history class. So browser history class initializes the object with the home page of the browser, correct? Visit URL from the current page, it clears up all the forward history. Back, move steps back in the history if you can only return X steps in the history, and if steps are greater than X, then you will return only X steps. You return the current URL after moving back in the history, and similarly you'll have to create string forward. So what they're trying to say in this particular question is, I'll try to make this statement pretty simple for you, right? So what they want us to do in this particular question is they want us to design browser history. Right, browser history is how our browser actually works. Let's say you all might have used Google Chrome, or you might have used Mozilla Firefox, right? So let's say we are on first site. Let's say I have opened my LinkedIn. Then from my LinkedIn, I move on to another site, that is LeetCode. I type in the URL of LeetCode and I land it on LeetCode. Then from LeetCode, let's say I want to go to InterviewBit. And from InterviewBit, let's say I want to go to Instagram. So these are the 4 sites that I'm visiting from my browser. First, I was on LinkedIn. I typed the URL LeetCode. I was on LeetCode. I typed the URL InterviewBit. I was on InterviewBit. I typed the URL Instagram. I am on Instagram. Now using the back functionality, there's a back button on our browser. Using the back button, I can move from Instagram to InterviewBit. I can move from InterviewBit to LeetCode. I can move from LeetCode to LinkedIn. Right? Again, let's say again I want to move to LeetCode. So again I'll do the next, I'll move a step forward and I'll go to LeetCode. Now let's say I am on LeetCode, and in between there I felt that there's a very important mail that I have got. So I want to go from LeetCode to Gmail, right? I want to go from LeetCode to Gmail, and I'll put the URL of Gmail on the same LeetCode page. Then I'll move on to Gmail. And now once Gmail is opened, this entire history is lost. This is lost. Now I have this chain formed. The new chain that is formed is LinkedIn, LeetCode, and Gmail. Right, so this is the new chain formed. So how can we implement this functionality particularly in our code? So this is what they want us to implement. Firstly, like once we open any browser page, once we open LinkedIn, we need to initialize that page first thing. Secondly, we want to move from one site to another. Let's say I want to move from LeetCode to Gmail. So this entire thing is to be deleted. That is after LeetCode. So visit function I need to create. Third function that I need to create is back function if I want to move from interview bit to LeetCode or LeetCode to LinkedIn. Fourth thing is forward function if I want to move from LinkedIn to LeetCode or LeetCode to interview bit or interview bit to Instagram. So this is the functionality that I need to implement, and as you can see, we are going backward and forth at the same time, right? We are moving ahead also, we are moving back also. So which data structure provides us this functionality? Isn't it a doubly linked list? Doubly linked list is of this form only now. We can move back also, we can move front also. It has 2 pointers, previous and next, previous and next, previous and next for each node, right? It is of this particular format. It's of this particular format. So I will create a doubly linked list. Right? So using this doubly linked list, what I will be doing is I will be implementing this functionality, right? So I'll quickly take you to the code, but before that I was just want to remind you one thing. Like we have already discussed STL, right? In STL, how we used to write a doubly linked list, we used to write it by the name of list, and here the type of list, like what type of elements I want to insert in that list. So I'll create list using STL, and we will try to solve this problem, right? So now this is the problem that I have in hand. So I need to first, these are the 4 functions that I need to implement. First is browser history. I have been given a home page. I just need to open that home page. That is, I want to start, right? And next I need to visit a particular URL and remove all the URLs or all the pages that are in front of that. If I want to move from one node to the previous node, or if I want to move from first node to the like forward button and backward button, that I need to implement, right? So the first thing is I'll create a list, and the type of list will be string because will be passing URLs. So list string. What is the name of this list? Let me name it as browser page, right? I'll also create an iterator that will help us iterate over these pages. So how we generally create an iterator? List of string, let's say it iterator it. So this is how we have initialized our iterator. Now the first page is browser history. So this is the first page, and they have given us this home page. Now I simply need to push this home page in my browser page, right? So for this, what I will do is browser page dot push back home page, right? And I will make my iterator point to homepage dot begin, right? So this is, sorry, it's not homepage, it's browser page. Sorry, homepage is so something that we have added. It will be browser page dot begin, right? So this is done, I guess. Like we just need to push that particular home page in our browser page. That's it. Now if I need to visit a new URL from the middle, right, what I will do is I'll delete all the nodes which are next to that particular URL where we are currently are, right? So how to find where we are currently are? We'll find it using the iterator, because that iterator will point to the current page, right? So let me just name it as auto current is equal to it. So this will give me the current page iterator. What I will do is I will increase this iterator, sorry, current plus plus, right? After that, what I will do is from this browser page, I will erase all the elements starting from this current to browser page dot end, right?
After this is done, now the new URL that I have, I want to visit that. Simply I'll push back in my browser page, browser page dot push back, and what I will push back is URL, and I will do IT++. So this is the visit function we have created. Now back function, if I want to go to the previous pages using the bag functionality, right? So what I will do is, and they have given us how many steps you need to move back. So until these steps are decreasing, we'll simply use a while loop, while steps minus minus. What I can do is, I will do IT minus minus, that is my iterator is pointing one step behind, and I'll simply return star IT. That means I am returning that particular string, right? But I think this is not sufficient. Like at a certain point we need to stop, right, when we are at the first page, because before the first page there is null, after the last page there is again null. So we need to stop at some point. So for that stopping condition I need to put one more condition, and IT is not equal to browser page dot begin, right? So this is the back functionality implemented. So what we'll be doing in front functionality is, the code is going to be almost similar, just we need to move it forward. So I'll do steps minus until steps are decreasing, how many steps we need to move forward, right, until this it dot end is equal to browser page dot begin की जगह पे end आ जाएगा, right? And this end will be browser page dot end. This is the internal functionality. This will give us the page which is after the end browser page. So we need to be at a position which is the last browser page. So last browser page I'll get it by using minus minus of end, browser page dot end, right? Simply here also we'll return and here we are increasing rather than decreasing. I'll return star IT, and this is it. I hope this is clear now. Let me just take you through how we have implemented this. Okay, so now if you see, so we have been given this browser history function to be completed, and we are given this home page. So what we are simply doing is, inside this list initially, which is empty, which is null, I am adding this first home page, and I'm pointing my iterator to the starting of this particular browser page linked list, right? Then they have given us a function to complete, that is visit, and inside this they are given a URL. So let's say I am here, first page that I've opened is lead code, then it's interview bit. Now from interview bit I want to go to Gmail. Interview bit se pehle I have opened already Facebook, right? Now I moved back to interview bit, and now I want to move to Gmail. So for this, what I will do is, I'll firstly take my current pointer, that is IT. This will be pointing to the current. I'll increase the current pointer. Then I'll erase all the pages which are after interview bit, like Facebook and all this. These will be deleted, and then I'll push back my new URL, that is Gmail. So it will become like lead code, interview bit, and Gmail. Then again increase the iterator, and in this way this function is complete. Next, while moving back, these many steps we need to move back, steps minus minus, and until and unless IT is not equal to browser page dot begin, we'll keep decreasing this IT, and we'll return star IT. Last function, similar to what we have done in the previous function, we are increasing, we are moving ahead, we are moving in the forward direction. So if we are moving in the forward direction, again we are increasing the iterator, in this case iterator plus plus, and we are returning star IT. So I hope this is clear to you. Try implementing this particular problem yourself. You will understand a lot of things, and these kind of questions can also be asked in the interview from application point of view, right? So the next question that we are going to discuss is basically LRU cache. So LRU cache, it's a very, very important question from the point of view of interviews. Like, this is the mostly asked interview question of Amazon. If you haven't heard of this question, so make sure you watch this very, very seriously. We'll try to demystify what this problem they're trying to say. And
then we'll go ahead with the solution part, right? So what they're trying to say is they're saying that you need to design a data structure that follows the constraints of a least recently used cache. So what is cache? We'll discuss about this as well. What they actually want us to do is they want us to implement the LRU cache class, and LRU cache, initialize the LRU cache with positive size capacity, then int get, that will return the value of the key if the key exists, otherwise return -1. Update the value of the key if the key exists, otherwise add key value pair to the cache. If the number of keys exceeds the capacity from this operation, evict the least recently used key, right? So this is the question. Let me just try to explain you what they're trying to say, right? So what is a cache, right? It's a form of a memory, right, where we store some databases, right? Consider a situation, you have a large database, right? There are a lot of users, thousands and lakhs and millions of users. So from those users, if at any point you want to search something, so there are million users, if you want to search something from those million users, so it will take time, right? It won't be that efficient, how much efficient sorting algorithm you use, but it will take some time to search from those million or billion of entries, right? So instead of that database, there is a special memory known as cache memory that is maintained, and that contains the elements which are most recently used, the elements which we are using frequently, right? So they are stored in the cache, and it's a smaller memory, smaller space, and searching inside a smaller space becomes easy. Searching inside a smaller space becomes easier. This is very layman terms explanation of what is a cache. If you're not aware of, once you will understand operating systems as a subject, maybe you will or databases as a subject, so you will understand this concept in a more clear and precise way. Now coming upon to our question, right? So what we are trying to say is they have told us to implement least recently used cache algorithm, right? So least recently used cache algorithm. So what actually the question says is, that let's say we have database, they have given two functions, int get and int put, right? So from this get function, what they want is, they want you should search a database and return the value corresponding to the key. They will give a key here and they want us to return a value corresponding to this key. So this is the function for that. And there's a put function which has key and value as arguments. So this key and value arguments, if we want to add a new entry to our database, right? So let's just look at the function, how it looks like. So yeah, so this is the function that they have given us to complete. This is LRU cache with int capacity as one of the arguments. They want us to complete two functions, int get and void put, right? So first thing is, let's say if we don't consider anything, very simple approach. Let's say we can create a map. We all know how to create a map of let's say both integers. I name it as m. To get a function, what I will do is I'll search if m dot find this key is equal to m of n. If this key is not there at all, so what I will do is I'll simply return -1. This is given in the question. Else what I will do is, else I'll return the value that is corresponding to that key. Simple, right? And what will be there in the put? I'll in this m map, I'll put the value corresponding to the key as value, and it's done. So this is something very simple, right? But here we haven't taken care of a lot of things, so let's come on to that. So for solving this particular problem, I will be using the most efficient data structure that can help us solve this problem is a doubly linked list. Right, so doubly linked list, it's something of this form, right? You have a node going here, you have a node going here with previous and next pointers, previous and next pointers, previous and next pointers. Let's say this is pointing to null, this is pointing to null. Now this is the database, right? So once any new entry that comes up, we try to add here, right? So this, like in this complete database, this is the most recently used data. This is the most recently used, right? And the data that goes on to the last, this is the least recently used data. Now as soon as we perform any operation, be it get or be it put, right? As soon as I perform a get function or a get operation and a put operation, what I will see is, as soon as I perform a get operation, like I want this particular the value corresponding to this particular data, right? So this particular data becomes my most recently used data. So this should shift to here. So this will become the most recently used. So removing this from here, I will connect this to this and I'll connect this to this directly. And the data which is not used for quite long time, it will automatically reach the end. It will automatically go on to the end. And if at all we put some data, so if we want to add some data, what we'll do is we'll check for the database. If it already exists, what we'll do, we'll erase that data and we'll create a new data and add it in the front. That is, this will be the most recently used. So this is something that we are trying to achieve, and they have given us a capacity, right? So we'll work according to this particular capacity. So let me just try to code in and try to explain you what we are actually going to do. Right, so we have already created this map. So let's go ahead with this. I'll create a list of integers, list L. I'll create integer capacity, capec. I'll create an integer size, siz. So capacity and sizes, capacity is the maximum available database, the maximum available storage capacity, and size is how much is it filled at that particular moment, right? So this LRU cache, basically I need to initialize this. So my capacity will be equal to capacity and my size initially will be equal to 0 because there's nothing in the database, right? Now going ahead, now if I want to get something from the database, first thing is if I'll make a check. If database doesn't exist, that particular key doesn't exist, I'll simply return -1. So this holds valid here also. But along with that, I can't simply return the key here. What I need to do is I'm performing a get operation. As soon as I'm performing a get operation, that particular key becomes my most recently used character. So to make that key to the most recently used character, I need to know which node is corresponding to this particular key. So to get which node is corresponding to this particular key, I'll have to traverse the linked list till this key so that I can get the address of that particular linked list. Let's say if this is the linked list, right? If I want to remove this particular, I want to get the address corresponding to this key, the key that is present here, right? So as per our understanding, we need to remove this from here and we need to move it here. So to do that, I will need the address of this. How we can get the address of a particular node whose key value we know? Maybe we can create one more map, and inside that map, what we can store is we can store key value pairs, key and along with their addresses. Like what is the address of this, so that I can simply attach this node here. It will be easier for me to attach this node here. So I'll create another map. So this was map of intended. This will be map of int, And how do we store addresses? We store addresses in the form of pointers, right? But we have already been using iterators. Iterator points to that particular memory address. So we'll be using iterator here as well. Iterator of the form list of integers, and it will be iterator iterator, right? And let me just name it as address. Right, so we have created another map from where we can get the corresponding address to a particular key value, right? So that we can simply erase that value, we can remove that value, we can delete that value from its current position, and we can put it in the front, that is, it becomes the most recently used thing. Right, now we have done till here. Now next step would be I'll calculate the iterator that is corresponding to this key. So to calculate that, I'll do list of integers, and what I was to do, iterator it is equal to address of this key, right? This will be the address that is corresponding to this particular iterator. So this iterator is corresponding to this particular key. So next is I will erase this entry from my already present linked list. So I'll erase this key. Next I will erase this key from the address map also. So address dot erase, I'll erase this key. So for removing from linked list, I need to provide the iterator to that particular point rather than providing the key. And also where we need to put it again, we need to put it in the front, because that becomes the most recently used. So what I will do is I'll do push front key. Right, after this, what is to be done? Now new position of address is to be assigned to this key. So new position of address will be address of key equals to L dot start, L dot begin, right? So we'll return M ka key. These steps basically were used to move this, remove this key from here and add it here. Right, so this is probably our corresponding get function. Now we'll try to see how put function works. What we actually do in put function is we try to create this new key value pair. Like firstly we'll check through this entire list if this key value pair is already present. If it is already present, then I'll erase that, and I'll add new. If it is not present, then I'll add new it, and will add it in the front. It will again be in L dot begin. So how we can do that? So the first thing that is very important that we will be doing here is firstly checking whether that particular key value pair is already present or not. So I will do that if m dot find key is not equal to m dot end. Right, so what I will do is, like, if we find that particular element, we'll erase L dot erase address corresponding to this key, basically the iterator, you can say. Right, next is from that address block also I'll erase this key. Also from the map we'll remove this, right, because we are trying to, we'll make it one more, we'll make it new. So m dot erase key, and I will reduce the value of size by 1 because we are removing something. ठीक है जी, I hope this is clear. And in the uppercase, why we didn't you do size plus first? Because we are not removing anything, we are just removing it from one side and we are adding it in the front, so size remains the same. Right, now here we have decreased the size. After that, what we are going to do is we want to add that key value pair in the front position. Right, so to add that key value pair in the front position, what I will do is L dot push front key. Right, I'll also add it in the address of key, is equal to L dot begin, because it's the front element of that list. Along with that, M of key is equal to value, right? So this is something that we have already done. Now also the size will increase because we are adding a new entry in the front, so size will be increased. There is still one problem. Let's say if size becomes equal to capacity, then what we should do? If let's say this is the linked list, this is the linked list, this is the most recently used, this is the least recently used, and there is a new entry, there's a new key value pair that you want to add into this particular list or this database or this cache. So what you will do? Will you remove this most recently used or this least recently used? So we'll remove this least recently used. Matlab in that particular database, we'll remove the last entry. When will this condition arrive? This condition will arrive whenever the size is equal to capacity, right? So let me just try to code this as well. So what we will do is, if size is equal to capacity, what we'll do is we'll take the last element of this list, that is, let me store it in k, L dot back, right? Then I'll remove that back element, L dot pop back. Then from address also will erase, address map also will erase, address dot erase k. From that M map also will erase, M dot erase k, and size minus. So if at all size becomes equal to capacity and we still want to add something, so we'll remove the least recently used scenario, right? Let me just try and erase this, and then we'll see what is left now. I hope this thing is clear, right? For most of you, this thing is clear, right? So what we are actually trying to do till here is, let us just revisit the code and try to see if you have understood or not, right? So we were to implement LRU cache. So you understood what is cache and what is LRU. So now what we say that we create a list that is in the form of a doubly linked list. So STL for doubly linked list is list, right? So this will point to null, this will point to null. So we have we try to implement in this particular fashion, right? Where capex denotes the capacity. That means what can be the capacity of my database. Size denotes the current number of objects, how many we have already added. This is the function where we initialize capacity and size. Initially the capacity is equal to the given capacity, size is equal to 0 because we haven't added anything. Then there are two functions, int get and void put. So what does this int get function means? This function says that I will give a particular key and you return the value corresponding to that key. But once we operate on any key value pair, so let's say this key, our functions call for this key. Once this key is called, you need to return the value corresponding to this key, but we are using this key, right? So this will remove from here and we will be adding it here, because now this becomes the most recently used, abhi we have used, now only we have used. So we need to remove this from here, we need to make this connection as this, we need to make this connection as this, right? And this will be added in the front. Yahan pe we'll add this node. So this becomes the most recently used. So this is only what we have done. So the first step is we try to find that if that number is not present in the list, then we'll simply return -1. Else what we'll do is we create an iterator. Now what we have created, the second thing is we have created a new map, because to get to this particular node, right? How I will reach this particular node, I know the key. right? But I don't know the address of this node so that I can remove it, or I can move this to this to this. So maybe first thing is I need to iterate, I need to traverse over this linked list from 0th position to this position and then get some answer or get some query, but that will be a tiresome process. Instead of that, I've created a map where I've stored the integers and their corresponding addresses in the form of iterators. Now I have this, so I have created this particular iterator, and from this particular map I am getting the value of the address corresponding to this key, right? Now what I will do is I'll try to erase if this is already available, so now we need to erase it. So I'll erase it from this list. Also I'll erase it from this address map, and I will put it in the front. L dot push front is equal to key. I'll put it in the front, right? Then address of key address of key also changes. If I put it here, so what will be its new address? Its new address will be corresponding to the address that is L dot begin, and I will return the value corresponding to it. I hope now it is a little more better, right? Cool. So the next thing is put, right? So put functions tells us to add a new key value pair. So if I want to add a new key value pair, like this is the current structure that we have. This is the current structure that we have, and they tell us to add a new key value pair. So where we'll add the new key value pair, we'll add it in the front for sure, right? But before that, before doing this, I will check whether this key value pair is already present or not. If at all this key value pair is present, so I will erase that key value pair, right? And then only I will add this. So this particular thing we are doing it for finding and erasing that particular key value pair from my already available database. If at all this does not work, well, this erases that particular key value pair from my already available linked list, and after that I try to push my key value pair in the front, and address corresponding to begin is mentioned, and we assign that key value the correct pair, right? But still one problem is there. If at all the size becomes equal to capacity, then what I'm going to do is, from this linked list, this is the most recently used, I know this is the most recently used, and this is the least recently used. So which one I should remove? Should I remove the most recently used, or should I remove the least recently used? Obviously this is something that we are not using from quite some time, so I will be removing this. So here also what I have taken is, I have taken the last element, I have removed that last element, erased that from the address, and size I have decreased. So this is what is being done, right? I hope things are clear to you now. So what I want you to do is try to dry run this particular question, because some of you might face difficulties in understanding it for the very first time if you're doing it for the very first time, right? Make sure you try to dry run it on your own on a piece of paper, right? After that, try to submit your code on platform and try to analyze what is its time complexity and space complexity. You can comment the time complexity and space complexity if you are doing this question on your own. I'll try to reply to all the comments that you do on this video, right? Now I hope this question is clear. If you still have doubts, make sure you ping your doubts in the comment section. I'll be more than happy to take it from there, right? So moving on to the next question. So the next question that we're going to discuss is basically a palindrome linked list. So you might have heard this term before also. What is a palindrome number, right? Palindrome number is such that, let's say we have 1, 2, 1, 1, right? You read it from the front, you read it from the back, it is one and the same thing, right? 1, 2, 3, 2, 1. It is also a palindrome number. And you might have also done this question in arrays or vectors, right? You are given an array and you need to check whether this is a palindrome array or not. Let's say if an array has these numbers 1, 2, 3 4 3 2 1. So this is a palindromic array, right? So you need to check and return whether it's true or false. That means the array is palindrome or not, right? So you have done this in arrays. How we do it in arrays? We use two pointers approach. We take a pointer, a left pointer here, we take a right pointer here, and we start comparing left and right. As soon as any of them mismatches, we return false, else we return true. So this is a very efficient and a good approach. But now the case is not like that. We are given a linked list, right? We are given a linked list of this particular form. Let's say 1 2 3 2 1 null. So this is the linked list that is given to us, and we need to return whether this linked list is palindromic or not, right? So how can this be done? The first way that comes to your mind may be, let's say I convert this linked list in the form of arrays or vectors, and I use two pointer approach. But in this case there will be a lot of space complexity involved again. So we'll avoid this, we'll not use this space complexity wali cheese. Instead there is something else. Like what can be done is, let's say we have this linked list, right? 1 2 3 4 3 2 1 and null. Let's say we have this linked list, right? So what we can do is, maybe we can divide the linked list into two parts. This is one part and this is another part, right? Or we can have we can divide the linked list into two parts and reverse the second part. So this becomes something like 1 2 3 4. If we reverse, 1 will come here, 1 2 3. So we'll make a pointer here, we'll keep a pointer here, and we'll start comparing. 1 is equal to 1, true. 2 is equal to 2, true. 3 is equal to 3, true. So this is what I can say is a palindromic linked list, right? This can be one way. So, and let's say this is for the case when the number of elements are odd. Let's say we are doing it for when the number of elements are even, right? 1 2 3 3 2 1, right? So for this we'll divide it from here, we'll have it like this, 1 2 3. We'll reverse this list, we'll get 1 2 3 again, and then we'll compare both of these. Take a start pointer, take a mid pointer, we'll move start pointer one step, mid pointer by one step, and compare at each point. As soon as any of these mismatches, what we'll do is we will return false, else we'll return true, right? And make sure, like, if the elements are odd, then we need to return the middle. We need to find out the middle and then reverse the next linked list. An element prior to the middle we need to find, right? And similarly in even case also we need to find the first middle, and the rest linked list is to be reversed, right? Let's just move on to the code and see if we are able to code this particular problem. Then you will be able to understand it a little more better way, right? So let's say this is a problem, right? So this is the problem that is given to us. We are given the head of a singly linked list. We need to return true if it is palindrome or not, right? So this is the head that is given to us. We need to check if it is palindrome. So the first thing that we will be doing in this particular question is we'll be finding out the middle and then reversing the middle. So how we generally find out the middle of a linked list? Using slow and fast pointers. We move slow pointer by 1 step, fast pointer by 2 steps. We have already done this question in the previous portion of this video, right? So what I will do is I will initialize a list node star slow is equal to head, list node star fast is equal to head, right? While fast का next is not equal to null and fast के next का next is not equal to null. Why I'm doing this? Because I want the first middle element. Try to dry run this and you will get the answer of this. Why fast ka next is not equal to null and fast ka next is not equal to null. Earlier we were doing fast while fast is not equal to null and fast ka next is not equal to null. Now we have changed the condition because we want the first middle, right? Slow will be equal to slow ka next, fast will be equal to fast ke next ka next, right? So both of these are done. After that what we are trying to do is slow. Now we have got, now the slow pointer carries the middle element and after slow ka next we need to reverse. So how we reverse a linked list? We have already written the code for reverse a linked list. I'll just copy paste this same reverse the linked list code and I'll use it in this particular problem, right? So what I can do is I can simply say slow ke next mein what you can put is reverse list starting from slow ka next, right? Reverse list true. So now we have half linked list as straight and half linked list as reversed, right? Now what we need to do is we need to compare. How we'll be comparing these two linked lists is we'll have two pointers. One is again a slow a start pointer, one is again a mid pointer, and we'll compare both of them. How we can compare both of them is let's say I take a new node, list node star start is equal to head, list node star mid is equal to slow ka next, right? While mid is not equal to null, what I will do is if mid value is not equal to start value, will return false, right? At any point if this doesn't happen, will return false and we'll move start equals to start ka next and mid equals to mid ka next, right? And we'll simply return true after that. After coming out of the linked list, we'll return true. That means the linked list is a palindromic linked list, right? Try to submit. Yeah, so we have successfully, has been successfully implemented, right? So what we are doing in this particular question is I hope you can understand it now with the help of code as well. So let's say we have this, now it is better, 1 2 3 3 2 1. So what we did here is we took a slow pointer, we took a fast pointer, both keeping here fast pointer, and we tried to move fast when it in a while loop until fast ka next is not equal to null and fast ka next is not equal to null, so that as soon as my slow reaches here I get the mid of my linked list. Now what I've done is in slow ka next, after this I am attaching reverse list slow ka next. This entire list is what I am passing out in the reverse function, and this list becomes something like this. This becomes my new list. Now this becomes my new list. It is 1 2 3 1 2 3 and null. This becomes my new list. Now what I did was I made a start pointer that was pointing to head. I made a mid pointer that was pointing to slow connects, that is this. Now I start comparing mid key value with start key value. This value is being compared with this. Yes, if at any point they don't match, this is not matching this, this is not matching this, this is not matching this, I'll return false and I'll keep on moving. Else, if this comes out from this loop, we'll return true. So this is how we check whether a linked list is palindrome or not. I hope this question is also clear. It's also one of the important questions, you can say, from the point of view of linked list. So make sure you do it on your own once. And let me know if you have any confusions, any doubts. Please type it down in the chat box, in the comment section. I'll be more than happy to take all your queries, right? So the next problem that we're going to see is basically intersection of two linked lists. What we are given in this particular question is you are given the heads of two singly linked lists, head A and head B. You need to return the node at which the two lists intersect. If the two linked lists have no intersection at all, then we can return null. For example, the following two linked lists begin to intersect at node, like we are given A1, A2, B1, B2, B3, C1, C2, C3. So we need to know the intersection point of both these linked lists. We have been given two linked lists with head A and head B, right? Let's just see how what can be the approach. So the question, the lead code example was A1, A2, C1, C2, C3, null. Here it was, I guess, B1, B2, B3, right? So this was the problem that was given on lead code, and they wanted us to get the intersection of linked lists, right? So this is the intersection point and we need to return this, know this, right? So what can be the first way? What can be the brute force approach, right? Maybe I'll choose this one and I'll traverse B, linked list B, right? I'll move from B1 to B2 and I'll match it with A1, whether it is matching or not. I'll move from B1, B2, B3, C1, C2, C3. If at no point they don't meet at any point, so we'll move to A2. Then I'll check match with every node of B, whether it is matching or not. If it is not matching, we'll move to this. Now in this case, if we'll traverse the linked list B, so they both will match, hence we'll return true or we'll return this node. But this will take the time complexity of O of M into N. If M is the length of this this linked list and N is the length of this linked list, then O of M into N time complexity, which is very, very expensive, right? So we'll not prefer this. Instead, what can be done is, let's say there's a set, set data structure, right? Set in SQL we have seen. So what we can do is, for one linked list, we traverse and put all the nodes in a set, unordered set or map, you can say. And like A1 will be here, A2 will be here, C1 will be here, C2 will be here, C3 will be here, and so on. Now we'll start traversing linked list B and we'll see if B1 is already present in set or not, B2 is present in set or not, B3 is present in set or not, C1 is present in set or not. We have significantly improved upon our complexity, but again we are using an extra data structure that can be a problem at any point. So what can be a little more better approach? Let's discuss once again, like, what is the solution? A1, A2, C1, C2, C3, null. In this case it is B1, B2, B3, right? These are the two linked lists. Now the next thing that I want to do is, what I will do is I'll calculate the length of both, length of A and length of B. Now length of A is 1, 2, 3, 4, 5. Length of A is 5. Length of B is 1, 2, 3, 4, 5, 6. Length of B is 6. Now to make them both move in a synchronized fashion, what I will do is I'll traverse the longer one. Well, I'll take the difference of both the nodes, 1, and I'll traverse the longer one by the difference, right? So I'll traverse it till here. So this is the starting point. Now I'll move both of the linked list from here. they'll see if they're equal, no. If they are equal, no. At this point, they meet each other. So this synchronization can help us in understanding that how we can improve the time complexity. Now this synchronization concept, if we try to implement in one more way, how can that be done? Right, let's say I have this linked list again, A1, A2, C1, C2, C3 and null. Here it is B1, B2, B3 and so on. Right, so let's say this is list 1, this is list 2. Right, I start from this list, A1 starts from this list, list 2 starts from this. Let me just consider this distance as hypothetical x, this distance is hypothetical y, this distance is hypothetical z. Right, so total distance that list 1 covers is x plus y, total distance that list 2 covers is z plus y. Right, let's say I want them to cover the distance of both of these linked lists, like list 1 covers first x plus y, then it covers z plus y. Similarly, list 2 covers its own distance z plus y, then it covers list 1's distance, that is x plus y. So again, these both distances become equal, or they are in sync, I can say. As soon as they are in sync, we'll traverse, like I'll traverse list 1 from A1 to A2 to C1, C2, C3. As soon as it reaches null, I'll start traversing it from this side, B1, B2, B3, C1, C2, C3. So what happens in this case is they both will be in sync at this point. They both will meet at this point and we don't need to do anything. This is the best possible solution that is available. Let's just try to dry run and see if this works. Right? Let me just use an eraser. Okay, so what I tried to say was, like, A is here, B is here, right? A moves to this, B moves to this, A moves to this, B moves to this, A moves to this, B moves to this, A moves to this, B moves to this. Now after this, A moves to this and B moves to this, A moves to this, B moves to this. Now they both are in sync again, right? They both are at the same place. Now B moves to this, A moves to this, B moves to this, A moves to this. Now again both B and A are equal. As soon as they are equal, we got our point. This is something that we wanted to know in this particular question. So this is the approach, this is the best approach that you should give to the interviewer once, like, if this particular question is asked to you in an interview, right? So let's see how this code works, how we can code this particular approach. So yeah, so the first thing that you should do is list node star, let's say A is equal to head of A, star B is equal to head of B. So I have two nodes A and B. I'll run a loop until A is not equal to B. While A is not equal to B, what I will do is the point at which A equals to B, so that means that is the intersection point, right? So we'll run this loop until and unless A is not equal to B. So I'll see if at all A is equal to null. A becomes null, then A should point to head of B, right? We'll start traversing from B if A equals to null, else A equals to A connects, the A moves forward. Similar is the case with B. What we'll do in case of B, if B equals to null, B equals to head of A, else B equals to B connects, right? So as soon as they come out of this loop, we can return A. Let me just try and run this code if this works. Okay, So there is a declaration problem. Let's just run this again. Yeah, so both of them are intersecting at 8, so we have got the correct output and it has been accepted. So what we are doing in this particular case is, let me just explain it to you again. So let's say we have this particular linked list 1 2 3 4 5. Here I have 6 7 8 and this null. So I need to tell at which point they intersect. Now this is list 1, this is list 2, right? I make it point to as A, this I make it point to as B. Now I check for if A is not equal to B, if at all A is not equal to B. So if A is not equal to B, I'll see if A equals to null. No, A is not equal to null, then I'll move A forward. Similarly, I'll see if B equal to null. No, B is not equal to null. I'll move B forward, and we'll do this until both of them are at the same position. A is here, B goes here, A is here, B goes here, A is here, B goes here, A is here. Now A becomes null, so B goes here. As soon as A is equal to null, we move it to B. Now it starts from head of B. So now A is here, B goes to null. A is here, B goes here. Now both A and B are in sync, right? So as soon as they are in sync, now again we'll start moving. B is here, A is here. Now B is here, A is here. B and A both match at this point. We'll simply return A, or we can say we return B. As soon as they become equal, so they'll move out of this while loop and we'll return the answer. So this is what we are doing in this problem. I hope you are amazed by the solution, and if you have any doubts still, so do comment in the comment box. I'll be more than happy to take all your queries, right? Now let's move on to the next problem. So the next question that we're going to discuss is basically a partition list. Now let's read the problem first and see what they're trying to say. Given a head of the linked list and a value x, partition it in such a way that all the nodes less than x comes before the nodes that are greater than or equal to x. You should preserve the original relative order of the nodes in each of the two partitions. This line is very, very important. So what they're trying to say is, like, this is the example given in which we have linked list with nodes as 1, 4, 3, 2, 5 and 2. And they have given us the value of x as 3. All the nodes which are less than 3 should come at the front and rest of the nodes should be after that. So how we'll be doing that? Like what exactly they want is, like, the number given is 3. So 1 is less than 3. Yes, 1 is here. 4 is not less than 3. Will not take it. 3 is not less than 3. Will not take it. 2 is less than 3. So 2 is here. 5 is not less than 3. 2 is less than 3. Then 2 is here. So we have all the numbers which are less than 3 as the first elements, and after that, maintaining the relative order of the nodes, like 4, 3 and 5, we have 4, 3 and 5 here. So we need to solve this problem. Let's just discuss the approach on how we can think upon this particular problem and how we can come to the solution after that, right? So yeah, so the question that we are going to discuss now is partition list. So the question name is partition list. What you are given in this particular problem is, you are given, let's say 1, 3, 5, 7. Let's take another example, right? Let's take an example 7, 5, 9, 1, 8, 3, right? So x value that is given is 4. So for all the nodes which are less than 4 should come in the front, and all the nodes which are greater than 4 should come at the end, right? So we'll start comparing the first node with 4. Is it greater than or less than? No, it is not it is greater than, right? So it should come in the end wala node. 7 should come here. We'll compare 5. 5 is also greater, so 5 should come here. Next is 9. 9 is also greater, so 9 should come here. 1 is smaller, so 1 should come here. 8 is greater, so 8 should come here. 3 is smaller, so 3 should come here, right? So our output should look something like this: 1 3 7 5 9 and 8. And you can see this order is preserved, like 7 ke baad we get 5, ke baad we get 9, ke baad we get 8. So this order is very, very important. We need to maintain this order only. So this is a very, very peculiar approach that we are going to solve this question with. Let's say the same question I have: 6 5 3 1 2 9 and null, and I am given value of x is equal to 3. What I will do is I'll create a dummy node by the name of left. I'll create a dummy node by the name of right, and I'll start traversing this linked list from the head pointer until head becomes null. I'll compare this with the value of x. If it is greater than the value of x, I'll put it in my right list. If it is greater than, I'll put it in my right list. If it is smaller than, I'll put it in my left list. 1 is smaller, I'll put it in my left list. 2 is smaller, I'll put it in my left list. 9 is greater, I'll put it in my right list. Now once I have the left and the right lists, I'll combine both of them, right? And here along with that, we'll maintain a tail pointer that will move to the last pointer, because we need this at the end, because once we need to join this along with this, so this tail of left should join to right. Tail of left ka next should be equal to the right, because we need to combine both of them together, and the tail of right should point to null. So we need to do this at the end after creating a left and the right list, right? So once we'll code it, I think you will be able to understand it better, right? So this is the problem statement that is given to us. We are given the head node and we are given a value x. So we'll be this value of x decides the number of nodes should, how many number of nodes should be present in the front. So we'll create two list nodes. List node star left equals to new of list node. Let's say we start it with -1. We create another node, list node -1 again. Let me just name it as right, and also we'll maintain their tail pointer so that we can easily connect both of them after we make them. List node star l tail, list node star r tail. Initially l tail is pointing to left and r tail is pointing to right. ठीक है जी. So l tail and r tail are done. So I'll move while my head is not equal to null, and I'll compare the values of x with the head key values. If head key value is less than x, then what I will do is I'll put that term in the left wali linked list with the dummy pointer. So l tail ka next will become equals to head, and l tail equals to l tail ka next, but the l tail moves forward, right? What will come in the else part? Else, if this is not the case, r tail ka next will become equal to head, and r tail equals to r tail ka next. So both our l tail and r tail are made, right? And we'll be moving our head forward, like we'll traverse the entire linked list. Head is equal to head ka next, right? After this is done, at the end what we need to do is r tail ka next should be equal to null, because r tail is the second list ka next is equal to null, and
L tail का next should be equal to the right pointer, मतलब जो dummy pointer है उसका next, right? At the end what will return is left का next. Why left का next? Because left is containing a dummy pointer. We don't need to return that dummy pointer of -1. Dummy pointer के आगे वाला number is what we are going to return. Let me just try and run this program and see how it goes. Okay, there is a spelling mistake. Yeah, so we have successfully solved this problem and the solution has been accepted also. So this was it. Let me just dry run through it once again. So what they have given us this example: 1, 4, 3, 2, 5, 2 and null, right? And they have given the value of x as 3. What we are doing is we have created a left dummy node and we have created a right dummy node. So I am moving it inside this while loop until and unless this head is not equal to null. Like this is currently head and I keep on traversing this linked list. If head की value is less than x, मतलब 1 is less than x, right? Then what I'll do is I'll join it in front of my left tail and tail moves forward. This is L tail. Now 4 is greater than 3. So if it is greater than 3, we'll move on to the else, but 4 is joined here and this is R tail. Again 3 is there, 3, it should be less than 3, strictly less than 3. So it will come in the R tail will move here. 2 will come in the L tail will come here. 5 will come in the R tail will come here. 2 will come in the L tail will come here, and it reaches null. We'll do it until and unless head does not reach head equals to null, right? So now we have two separate linked lists, left and right. What I need to do is I need to make this L tails next point to right ka next. This should point to this. This is what I am doing here. And R tail ka next to be null. R tail ka next is to be pointing to null. So my linked list will finally become 1, 2, 2, 4, 3, 5 and null. And this is pointing to left dummy node. So at the end what I will return, left ka next. I'll start returning from this and this is the answer that we'll get. Right? I hope this is clear. I hope you are able to solve this particular problem. Right? Now moving ahead, there is something known as circular linked list. I'll not go into the depth of circular linked list. That is something that you can explore upon. There are some problems that can be solved using a circular linked list, but if you have understood the concepts of singly linked list, then circular linked list is not a tough topic. It's completely almost similar, just some things you need to understand. Just from basic point of view, if I talk about what is a circular linked list, right? What is a circular linked list? So our singly linked list is something of this particular sort, right? We have nodes. This, let's say data is 1, 2, 3, 4. Address of this is 100. This is 200. This is 300. This is 400. This stores the address of next. It is 200. It is 300. It is 400. And it is null. This is my singly linked list. What happens in a doubly linked list? We have discussed doubly linked list as well. So doubly linked list में क्या होता है? Doubly linked list में this picture is something like this. Now you can visualize it something like this. This is pointing to null. This is pointing to null. They have two pointers, previous and next. Previous and next. Let's say the address of this is 100, 200, 300, 400. So this will store 200 here, the address of the next. This will store the address of the previous here and the address of the next here. This will store the address of the previous here, address of the next here. This will store the address of the previous here
address of the next here. These are the datas 1, 2, 3, 4, and this was something known as a doubly linked list. Now, what is the difference between what is a circular linked list? So it is similar to singly linked list. So what happens in a circular linked list is we have 1, 2, 3, 4, 5. This was singly linked list. So now instead of 5 pointing to null, if 5 points back to 1, right? There's no option of null in a circular linked list. Like there's no node that is pointing to null in a circular linked list. Like there is a head pointer that points to the start node. There is a tail pointer that points to the tail node, right? And tail, every time tail ka next is equal to head. So this is the condition for circular linked list, right? If you want to insert a new node in a circular linked list, what you will do is, you will store the address of the head. You know already the address of the head. You will make a new node, let's say 6. You will make tail ka next point to 6, and 6 becomes the tail, and tail ka next points to head again. This is what you will be doing, right? If you want to insert a new node. Similarly, you can perform all the operations that we have already done on different types of linked list, like insertion, deletion, searching. So all these operations can be performed on circular linked list as well, right? I want you all to try circular linked list on your own once. If you feel like solving problems on circular linked list is difficult, do let me know in the comment section. I will come up with a separate video for circular linked list as well, right? So that was all about linked list as a topic. We have extensively covered a lot of topics, and I believe you would have understood a lot of them, right? So from the point of view of understanding of linked list, now I believe all these things are clear to you. We have started with representation of a linked list, right? We've started with the which all topics we have covered in linked list. So we have started with the need for linked list, advantage over arrays, then we discussed about representation of a linked list, like printing linked list. We saw insertion, deletion, searching, size of a linked list. We found out the middle of the linked list. We did some different problems on LeetCode, on different other platforms. We solved problems like cycle detection. That was done using Floyd-Warshall algorithm. We did problems related to palindrome linked list. We did problems related to LRU cache. We did problems related to different other problems. We also discussed a doubly linked list, structure of doubly linked list. STL in linked list. Along with that, some more topics we have discussed. So this covers all your fundamental concepts of linked list. Now what I advise you to do is, once you have watched this video till the end, go to any of the sites, be it InterviewBit, be it LeetCode, or any other site that you want, and try practicing some random questions based upon linked list. Now I feel that you are ready for this topic and you can solve all the problems, be it from easy category, medium category, or hard category. So make sure you utilize your time well and practice more questions. It's not just about viewing these videos, it's more about practicing a lot of questions. That is ultimately going to help us in the longer run. So make sure you watch this video. If some concepts are not clear, do comment in the comment box.
If concepts are clear, make sure you hit the like button and subscribe to this channel as well. And let me know which all more tutorials you're looking forward to in the series. I'll come up with the complete tutorials on any of the topics that you are looking forward to, that you are facing problems in currently. So this was all for this particular video. I thank you all for keeping the patience and being till the end of this video. This was amazing to teach all of you the concepts of linked list. Soon some more videos are going to be uploaded on this channel as well. Till then, all the best. See you.